Hi everyone, welcome to this Data Science 2022 full course video by Simplilearn. In this video, you will learn all the necessary skills that will help you become a data scientist in 2022. Our highly experienced instructors will take you through this course. Data scientists are some of the highly paid professionals in the world. They work on data from multiple sources to derive insights. Now let's look at the topics that we'll be covering in this video. So we will start by looking at the basics of data science from a short animated video. Then you will learn the data science process steps, their applications, and then look at the top 5 Python libraries for data science. Next, you will understand the top algorithms that data scientists use to build predictive models. So you will learn about linear regression, logistic regression, ensemble learning methods, KNN, clustering, principal component analysis, and other techniques. After that, we will touch upon some of the crucial concepts in deep learning using TensorFlow and Keras. Finally, you will get an idea about the top data science interview questions that are frequently asked in the interviews. So let's get started.
Are you one of the many who dreams of becoming a data scientist? Keep watching this video if you're passionate about data science, because we will tell you how does it really work under the hood. Emma is a data scientist. Let's see how a day in her life goes while she's working on a data science project. Well, it is very important to understand the business problem first. In her meeting with the clients, Emma asks relevant questions, understands and defines objectives for the problem that needs to be tackled. She is a curious soul who asks a lot of whys, one of the many traits of a good data scientist. Now, she gears up for data acquisition to gather and scrape data from multiple sources like web servers, logs, databases, APIs, and online repositories. Oh, it seems like finding the right data takes both time and effort. After the data is gathered comes data preparation. This step involves data cleaning and data transformation. Data cleaning is the most time-consuming process as it involves handling many complex scenarios. Here, Emma deals with inconsistent data types, misspelled attributes, missing values, duplicate values, and whatnot. Then, in data transformation, she modifies the data based on defined mapping rules. In a project, ETL tools like Talent and Informatica are used to perform complex transformations that helps the team to understand the data structure better. Then understanding what you actually can do with your data is very crucial. For that, Emma does exploratory data analysis. With the help of EDA, she defines and refines the selection of feature variables that will be used in the model development. But what if Emma skips this step? She might end up choosing the wrong variables, which will produce an inaccurate model. Thus, exploratory data analysis becomes the most important step. Now, she proceeds to the core activity of a data science project, which is data modeling. She repetitively applies diverse machine learning techniques like KNN, decision tree, naive Bayes to the data to identify the model that best fits the business requirement. She trains the models on the training dataset and tests them to select the best performing model. Emma prefers Python for modeling the data. However, it can also be done using R and SAS. Well, the trickiest part is not yet over: visualization and communication. Emma meets the clients again to communicate the business findings in a simple and effective manner to convince the stakeholders. She uses tools like Tableau, Power BI, and ClickView that can help her in creating powerful reports and finally maintains the model. She tests the selected model in a pre-production environment before deploying it in the production environment, which is the best practice, right? After successfully deploying it, she uses reports and dashboards to get real-time analytics. Further, she also monitors and maintains the project's performance. Well, that's how Emma completes the data science project. We have seen the daily routine of a data scientist is a whole lot of fun, has a lot of interesting aspects, and comes with its own share of challenges. Now, let's see how data science is changing the world. Data science techniques along with genomic data provides a deeper understanding of genetic issues in reaction to particular drugs and diseases. Logistic companies like DHL, FedEx have discovered the best routes to ship, the best suited time to deliver, the best mode of transport to choose, thus leading to cost efficiency. With data science, it is possible to not only predict employee attrition, but to also understand the key variables that influence employee turnover. Also, the airline companies can now easily predict flight delay and notify the passengers beforehand to enhance their travel experience. Well, if you're wondering, there are various roles offered to a data scientist, like data analyst, machine learning engineer, deep learning engineer, data engineer, and of course, data scientist. The median base salaries of a data scientist can range from $95,000 to $165,000. So that was about the data science. Are you ready to be a data scientist? If yes, then start today. The world of data needs you. That's all from my side today. Thank you for watching. Comment below the next topic that you want to learn and subscribe to Simplilearn to get the latest updates on more such interesting videos. Thank you and keep learning.
So what are the prerequisites for data science? There are 3 essential traits required to be a data scientist. One is curiosity. You need to be able to ask questions. The first step in data science is asking questions. What is the problem we are trying to solve? If you ask the right question, only then you'll get the right answer. Very often, this is a very crucial step where a lot of data science projects fail because you may be asking the wrong question. And then obviously when you get the answer, that's not the answer you're looking for. So it is very important that you ask the right question. Needless to say, then the second part or the second trait is common sense. So you need to be creative. You need to come up with ways to use the data that you have and try to solve the business problem on hand. In many cases, you may not have all the data that you need. In many cases, the data may be incomplete. So that is where you need to come up with ways, what are the best ways to fill these gaps wherever this is missing. And that's where common sense comes into play. Last but not least, after doing all this analysis, if you're unable to communicate the results in the right way, the whole exercise will fail. So communication is a key trait for a data scientist. Maybe technically you may be a genius, but then if you are unable to communicate those results in a proper way, once again, that will not help. So these are the 3 main traits: curiosity, common sense, and communication skills. In a way, you can say these are the 3 C's. Okay, so what are the other prerequisites? The first one, so machine learning. Machine learning is the backbone of data science. Data science involves quite a bit of machine learning in addition to the basic statistics that we do. So a data scientist needs to have a good hang or need to be very good at data science. The second part is modeling. So modeling is also a part of machine learning in a way, but you need to be good at identifying what are the algorithms that are most suitable to solve a given problem, what models can we use, and how do we train these models, and so on and so forth. So that is the second component. Then statistics. Statistics is like the core foundation of data science. So you need to understand statistics and you need to have a good hang of statistics in order to be a good data scientist. And this will also help in getting good results. Programming is to some extent required. At least some program or the other would be required as a part of executing a data science project. The most common programming languages are Python and R. Python especially is becoming a very popular programming language in data science because of its ease of learning, because of the multiple libraries that it supports for performing data science and machine learning and so on. So Python is by far one of the most popular languages in data science. If any one of you is wanting to learn a new language, that should be Python. And then of course you need to understand databases, how databases work, and how to handle databases, how to get data out of databases, and so on. So these are some of the key components of data science. Now, coming to the tools and skills that are used in data science. These are some of the skills from a language perspective. It is Python or R. And from a skills perspective, in addition to some of the programming languages, it would help if you have a good knowledge or good understanding of statistics. And what are the tools that are used in data analysis? SAS is one of the most popular tools. It's been there for a very long time, and that's the reason it is very popular. And however, this is compared to most of the other tools, it is a proprietary software, whereas Python and R are mostly open source. The other tools are like Jupyter Notebooks. You have RStudio. These are more development environments and development tools. So Jupyter Notebooks is a interactive development environment. Similarly, RStudio is for performing or writing R code and performing analytics and performing data analysis and machine learning activities you can perform in RStudio. It has a very nice UI, and initially R was not so popular primarily because it did not have user interface, and RStudio is a relatively new addition, and after the advent of RStudio, R became extremely popular. And there are other tools like MATLAB, and of course some people do with Excel as well. As far as data warehousing is concerned, some of the skills that are required are ETL. So in order to extract data and transform load, ETL stands for extract, transform, load. So you have data in the databases like your ERP system or a CRM system. You need to extract that and then do some transformations and then load it into your warehouse so that all the data from various sources looks uniform. Then you need some SQL skills, which is basically querying the data, writing SQL queries. Hadoop is another important skill, especially if you're handling large amounts of data. And also one of the specialities of Hadoop is it can be used for handling unstructured data as well. So it can be used for large amounts of structured and unstructured data. Then Spark is an excellent computing engine for performing data analysis or machine learning in a distributed mode. So if you have a large amount of data, the combination of Spark and Hadoop can be extremely powerful. So you store your data in Hadoop HDFS and use Spark as your computation engine. It works in a distributed mode similar to Hadoop in like a cluster. So those are excellent skills for data warehousing. And there are some standard tools that are available like Informatica, DataStage, Talent, and also AWS Redshift if you want to do some on the cloud. I think AWS Redshift is again a good tool. Data visualization tools. For data visualization, some of the skills that would be required are, let's say, R. R provides some very good visualization capabilities, especially for developing during development. And then you have Python libraries, Matplotlib, and so on, which provides very powerful visualization capabilities. And that is from skills perspective. Whereas tools that can be used are Tableau is a very, very popular visualization tool. Again, that's a proprietary tool, so it's a little expensive maybe, but excellent capabilities from a visualization perspective. Then there are tools like Cognos, which is an IBM product which provides very good visualization capabilities as well. And then coming to the machine learning part of it, the skills required there are Python, which is more for programming part, and then you will need some mathematical skills like algebra, linear algebra especially, and then statistics and maybe a little bit of calculus and so on. And the tools that are used for machine learning are Spark MLlib and Apache Mahout. And on cloud, if you want to do something, you can use Microsoft Azure ML Studio as well. So these are by no means an exhaustive list. There are actually many, many tools and probably a few more skills also maybe there. But this gives a quick overview, like a summarization of the tools and skills. Now, moving on to the life of a data scientist. What does a data scientist do during the course of his work? So let's see. So typically, a data scientist is given a problem, a business problem that he needs to solve. And in order to do that, if you remember from the previous slide, he basically asks the question as to what is the problem that he needs to solve. So that is the first thing. He has got the problem. Then the next thing is to gather the data that is required to solve this problem. So he goes about looking for data from anywhere. It could be the enterprise. Very often the data is not provided in the nice format that he would like to have it or we would like to have it. So first step is to get whatever data that is possible, what is known as raw data in whatever format. So it could be enterprise data, it could be, there is probably a requirement to go and get some public data in some cases. So all that raw data is collected and then that is processed and analyzed and prepared into a format in which it can be used. and then it is fed into the analytics system, be it a machine learning algorithm or a statistical model, and we get the output, and then he puts these output in a proper format for presenting it to the stakeholders and communicating those insights or the results to the stakeholders. So this is a very high level view of like a day in the life of a data scientist. So gathering data, raw data, performing some quick analysis on that, and maybe processing or manipulating this data to bring it into a certain good format so that it can be used for the analysis, feeding this into that analysis system that has been designed, be it mathematical models, machine learning models, and then get the results, the insights, and then present it in a nice way so that the stakeholders can understand. How about machine learning algorithms? So let's see what are the various machine learning algorithms that would be required for a data scientist. So these are a few of the algorithms. Again, this is not an exhaustive list. We have regression is one of the supervised learning models or techniques. So in case of regression, you try to, let's say, come up with a continuous number. So the difference between regression and, let's say, a classification is that in case of classification, those are discrete values. Whereas here we are talking about regression where let's say you are trying to predict the temperature, which is a continuous value, or the share price, which is a continuous value. So that is regression. So you need to know what is regression, how to perform regression, and we need to understand clustering. So clustering is one of the unsupervised learning techniques. In this case, there is no label data that is available, and you get some data and then you want to put this into some shape so that you can analyze it and you try to make sense out of it. Let's say you have, one example is you have a list of cricketers and they have not been marked as bowlers and batsmen or all-rounders or whatever, right? So you just have their names and maybe how many runs they scored, how many wickets they have taken, and so on. But there is no readily available information saying that, okay, this person is a batsman, this person is a bowler, and so on. So I'm talking about cricket. Hopefully, most of you are familiar with the game of cricket. So how do we find out? So then we put this into a clustering mechanism, and then the system will say that, okay, these are the people who have all scored good amount of runs. So they belong to one cluster. These are all the people who have taken good amount of wickets. So they belong to one cluster. And maybe here are some people who have taken good amount of wickets and they have made good amount of runs. So they may be belonging to one group. And then we take a look at it and then we label them as, okay, people who have all together and those who have, scored many runs, we label them as batsmen. People who have taken a lot of wickets, we label them as bowlers, and people who have taken good amount of wickets and also made some good runs, we label them as all-rounders. But the system will just say, okay, this is cluster 1, cluster 2, cluster 3. The names we human beings have to give the names. Now, decision tree is used for what is known as classification. Primarily, it can also be used for regression, but by and large, it is used for classification. And here again, it's a very logical way in which the algorithm goes about classifying the various inputs. One of the biggest advantages of decision tree is that it's very easy to understand and it's very easy to explain why a certain object has been classified in a certain way compared to maybe some of the other mechanisms like, say, support vector machines or logistic regression and so on. So that's the advantage of decision tree, but that is also a very popular algorithm. Then we have support vector machines primarily for classification purpose, and then we have naive Bayes. This is again a statistical probability based classification method. So these are a few algorithms. There are a few more that are not listed here, but there are some more algorithms as well. And by the way, there are detailed videos about each of these algorithms available. You can check in the playlist. So now let's talk about the life cycle of a data science project. Okay, the first step is the concept study. In this step, it involves understanding the business problem, asking questions, get a good understanding of the business model, meet up with all the stakeholders, understand what kind of data is available, and all that is a part of the first step. So here are a few examples. We want to see what are the various specifications, and then what is the end goal, what is the budget, is there an example of this kind of a problem that has been maybe solved earlier. So all this is a part of the concept study. And another example could be a very specific one to predict the price of a 1.35 carat diamond, and there may be relevant information, inputs that are available, and we want to predict the price. The next step in this process is data preparation, data gathering and data preparation, also known as data munging, or sometimes it is also known as data manipulation. So what happens here is the raw data that is available may not be usable in its current format for various reasons. So that is why in this step, a data scientist would explore the data. He will take a look at some sample data, maybe pick, if there are millions of records, pick a few thousand records and see how the data is looking. Are there any gaps? Is the structure appropriate to be fed into the system? Are there some columns which are probably not adding value, may not be required for the analysis? Very often these are like names of the customers. They will probably not add any value or much value from an analysis perspective. The structure of the data, maybe the data is coming from multiple data sources and the structures may not be matching. What are the other problems? There may be gaps in the data. So the data, all the columns, all the cells are not filled. If you're talking about structured data, there are several blank records or blank columns. So if you use that data directly, you'll get errors or you'll get inaccurate results. So how do you either get rid of that data, or how do you fill these gaps with something meaningful? So all that is a part of data munging or data manipulation. So these are some additional subtopics within that. So data integration is one of them. If there are any conflicts in the data, data may be redundant. Yeah, data redundancy is another issue. There may be, you have, let's say, data coming from two different systems and both of them have customer table, for example, customer information. So when you merge them, there is a duplication issue. So how do we resolve that? So that is one. Data transformation. As I said, there will be situations where data is coming from multiple sources, and then when we merge them together, they may not be matching. So we need to do some transformations to make sure everything is similar. We may have to do some data reduction. If the data size is too big, you may have to come up with ways to reduce it meaningfully without losing information. Then data cleaning. So there will be either wrong values or null values, or there are missing values. So how do you handle all of that? A few examples of very specific stuff. So if there are missing values, how do you handle missing values or null values? Here in this particular slide, we are seeing three types of issues. One is missing value. Then you have null value. You see the difference between the two, right? So in the missing value, there is nothing, blank. Null value, it says null. Now the system cannot handle if there are null values. Similarly, there is improper data. So it's supposed to be numeric value, but there is a string or a non-numeric value. So how do we clean and prepare the data so that our system can work flawlessly? So there are multiple ways, and there is no one common way of doing this. It can vary from project to project. It can vary from what exactly is the problem we are trying to solve. It can vary from data scientist to data scientist, organization to organization. So these are like some standard practices people come up with. And of course, there will be a lot of trial and error. Somebody would have tried out something and it worked and will continue to use that mechanism. So that's how we need to take care of data cleaning. Now, what are the various ways of doing, if values are missing? How do you take care of that? Now, if the data is too large and only a few records have some missing values, then it is okay to just get rid of those entire rows, for example. So if you have 1 million records and out of which 100 records don't have full data, so there are some missing values in about 100 records. So it's absolutely fine because it's a small percentage of the data. So you can get rid of the entire records which have missing values. But that's not a very common situation. Very often you will have multiple, or at least a large number of data set. For example, out of million records, you may have 50,000 records which are like having missing values. Now that's a significant amount. You cannot get rid of all those records. Your analysis will be inaccurate. So how do you handle such situations? So there are again multiple ways of doing it. One is you can probably, if a particular values are missing in a particular column, you can probably take the mean value for that particular column and fill all the missing values with the mean value, so that first of all you don't get errors because of missing values, and second, you don't get results that are way off because these values are completely different from what is there. So that is one way. Then a few other could be either taking the median value or depending on what kind of data we are talking about. So something meaningful we will have put in there. If we are doing some machine learning activity, then obviously as a part of data preparation, you need to split the data into training and test data set. The reason being, if you try to test with a data set which the system has already seen as a part of training, then it will tend to give reasonably accurate results because it has already seen that data, and that is not a good measure of the accuracy of the system. So typically you take the entire data set, the input data set, and split it into two parts. And again, the ratio can vary from person to person, individual preferences. Some people like to split it into 50-50. Some people like it as 63.33 and 33.3 is basically 2/3 and 1/3. And some people do it as 80-20. 80 for training and 20 for testing. So you split the data, perform the training with the 80%, and then use the remaining 20% for testing. All right. So that is one more data preparation activity that needs to be done before you start analyzing or applying the data or putting the data through the model. Then the next step is model planning. Now these models can be statistical models, this could be machine learning models. So you need to decide what kind of models you're going to use. Again, it depends on what is the problem you're trying to solve. If it is a regression problem, you need to think of a regression algorithm and come up with a regression model. So it could be linear regression. Or if you're talking about classification, then you need to pick up an appropriate classification algorithm like logistic regression or decision tree or SVM, and then you need to train that particular model. So that is the model building or model planning process, and the cleaned up data has to be fed into the model. And apart from cleaning, you may also have to, in order to determine what kind of model you will use, you have to perform some exploratory data analysis to understand the relationship between the various variables and see if the data is appropriate and so on, right? So that is the additional preparatory step that needs to be done. So a little bit of details about exploratory data analysis. So what exactly is exploratory data analysis? It's basically to, as the name suggests, you're just exploring. You just receive the data and you're trying to explore and find out what are the data types and what is the data clean in each of the columns. What is the maximum minimum value? So for example, there are out of the box functionality available in tools like R. So if you just ask for a summary of the table, it will tell you for each column, it will give some details as to what is the mean value, what is the maximum value, and so on and so forth. So this exercise or this exploratory analysis is to get an understanding of your data. And then you can take steps to, during this process, you find there are a lot of missing values. You need to take steps to fix those. You will also get an idea about what kind of model to be used and so on and so forth. What are the various techniques used for exploratory data analysis? Typically, these would be visualization techniques, like you use histograms, you can use box plots, you can use scatter plots. So these are very quick ways of identifying the patterns or a few of the trends of the data and so on. And then once your data is ready, you've decided on the model, what kind of algorithm you're going to use. If you're trying to do machine learning, you need to pass your 80% the training data, or rather you use that training data to train your model. And the training process itself is iterative. So the training process you may have to perform multiple times. And once the training is done and you feel it is giving good accuracy, then you move on to test. So you take the remaining 20% of the data. Remember, we split the data into training and test. So the test data is now used to check the accuracy or how well our model is performing. And if there are further issues, let's say, and model is still during testing, if the accuracy is not good, then you may want to retrain your model or use a different model. So this whole thing again can be iterative. But if the test process is passed, or if the model passes the test, then it can go into production and it will be deployed. All right. So what are the various tools that we use for model planning? R is an excellent tool in a lot of ways, whether you're doing regular statistical analysis or machine learning or any of these activities. R, along with R Studio, provides a very powerful environment to do data analysis, including visualization. It has a very good integrated visualization or plot mechanism which can be used for doing exploratory data analysis, and then later on to do analysis, detailed analysis and machine learning and so on and so forth. Then of course you can write Python programs. Python offers a rich library for performing data analysis and machine learning and so on. MATLAB is a very popular tool as well, especially during education. So this is a very easy to learn tool. So MATLAB is another tool that can be used. And then last but not least, SAS. SAS is again very powerful. It is a proprietary tool and it has all the components that are required to perform very good statistical analysis or perform data science. So those are the various tools that would be required for, or that can be used for model building. And so the next step is model building. So we have done the planning part. We said, okay, what is the algorithm we are going to use? What kind of model we are going to use? Now we need to actually train this model, or build the model rather, so that it can then be deployed. So what are the various ways, or what are the various types of model building activities? So it could be, let's say in this particular example that we have taken, you want to find out the price of 1.35 carat diamond. So this is, let's say, a linear regression problem. You have data for various carats of diamond and you use that information, you pass it through a linear regression model, or you create a linear regression model which can then predict your price for 1.35 carat. So this is one example of model building. And then a little bit details of how linear regression works. So linear regression is basically coming up with a relation between an independent variable and a dependent variable. So it is pretty much like coming up with equation of a straight line which is the best fit for the given data. So like for example here, y is equal to mx plus c. So y is the dependent variable and x is the independent variable. We need to determine the values of m and c for our given data. So that is what the training process of this model does. At the end of the training process, you have a certain value of m and c, and that is used for predicting the values of any new data that comes. All right, so the way it works is we use the training and the test data set to train the model and then validate whether the model is working fine or not using test data. And if it is working fine, then it is taken to the next level, which is put in production. If not, the model has to be retrained. If the accuracy is not good enough, then the model is retrained, maybe with more data, or you come up with a newer model or algorithm and then repeat that process. So it is an iterative process. Once the training is completed, training and test, then this model is deployed and we can use this particular model to determine what is the price of 1.35 carat diamond. Remember, that was our problem statement. So now that we have the best fit for this given data, we have the price of 1.35 carat diamond, which is 10,000. So this is one example of how this whole process works. Now, how do we build the model? There are multiple ways. You can use Python, for example, and use libraries like Pandas or NumPy to build the model and implement it. This will be available as a separate tutorial, a separate video in this playlist. So stay tuned for that. Moving on, once we have the results, the next step is to communicate these results to the appropriate stakeholders. So which is basically taking this results and preparing like a presentation or a dashboard and communicating these results to the concerned people. So finishing or getting the results of the analysis is not the last step, but you need to, as a data scientist, take these results and present it to the team that has given you this problem in the first place and explain your findings, explain the findings of this exercise and recommend maybe what steps they need to take in order to overcome this problem or solve this problem. So that is the pretty much once that is accepted, and the last step is to operationalize. So if everything is fine, your data scientist presentations are accepted, then they put it into practice and thereby they will be able to improve or solve the problem that they stated in step 1. Okay, so quick summary of the life cycle. You have a concept study, which is basically understanding the problem, asking the right questions, and trying to see if there is enough data to solve this problem. And then even maybe gather the data. Then data preparation, the raw data needs to be manipulated. You need to do data munging so that you have the data in a certain proper format to be used by the model or our analytics system. And then you need to do the model planning, what kind of a model, what algorithm you will use for a given problem. And then the model building. So the exact execution of that model happens in step 4, and you implement and execute that model and put the data through the analysis in this step, and then you get the results. These results are then communicated, packaged and presented and communicated to the stakeholders, and once that is accepted, that is operationalized. So that is the final step. Now, in the end, let's take a quick look at the demand for data scientists. Data science is an area of great demand. The demand for data scientists is currently huge and the supply is very low. So there is a huge gap. So what are some of the industries with high demand for data scientists? I think gaming is definitely one area where it's an industry which is consumer-facing industry, and a lot of people play games and growing industry, and it requires a lot of data science. So that is an area where data scientists are in demand. Then we have healthcare. For example, data science is used for diagnosis and several other activities within healthcare, predicting, for example, a disease. So healthcare is definitely finance, definitely banks, insurance companies, all of these, there is a huge demand for data scientists. Marketing is like a horizontal functionality across all industries. There's a demand for data scientists there. Then, of course, in technology area. So pretty much all of these areas, there is a lot of demand. Globally, there is a huge demand. So this is a very, very critical skill that would be required currently as well as in the future.
So when we talk about solving problems with data science, we have to ask possible questions and the desired algorithms. And these really are kind of an overview of some of the terminology you'll want to know in data science. So when we talk about that, how much or how many? We're talking about regression. Regression basically means a number. If you've ever seen stock charts, you see the guess at what the next sales price is or buy price is. That's all on your regression side. Is it A or B? Classification. Is that a dog or a cat that my photo took a picture of? How is this organized? Clustering. This is where we take things that look alike and put them together so that we can then make predictions on it. How different is this? Just like you have clustering, you have the opposite, anomaly detection. How do we find things that don't fit in? Where are the outliers? What are things we might need to look at that aren't in our model? And what to do next? Reinforced learning. This is probably the newest market, is how do we set something up where as the data comes in, it learns from the new data as to what the next action is going to take. Most of these are combined. So when we talk about regression, classification, clustering, anomaly detection, reinforced learning, a lot of times when you put your model together, you might have multiple parts of this. We might look at the clustering of data and then feed it into a classification. Is this a bad loan to make at the bank, or is this a good loan to give? And from there we might start looking at, when we start clustering these things as good and bad and what kind of setup is, We then might run it through a regression model to say, hey, what is the dollar amount this person should be allowed to take a loan out? And you can see that all of these start coming in, and then a lot of the models, reinforced learning, we talk about like bank loans and things like that, once a year they have to rerun those algorithms. And so that's like a human run reinforced learning. Now we're starting to automate that so that as the data comes in real time, the models start updating themselves. They start figuring out a way to solve new problems as they occur. And of course, in robotics, reinforced learning is one of the biggest growing fields. Algorithms used in data science: linear regression, logistic regression. When you're looking at both of these, think numbers. We're talking regression models. And so linear regression figures out the best line through the data. Maybe it's looking for a curved line. Logistic regression starts looking at data on a continuum so that it goes to an exponential. You have a spot where it might be one or the other, and then you know what it is as it goes to one side or the other. Decision tree, wonderful tool. If you they used to call it a hack, now it's becoming mainstream, to look at the back end, what made the decision. So it's really easy to trace back to how you arrived at the decision. Decision trees are kind of nice that way. Nearest neighbors. K nearest neighbors is your clustering. K means clustering. Hierarchical clustering. So hierarchical starts dividing them and builds a hierarchy where the k-means and the k-nearest neighbor look for things that kind of connect each other. How close are they in data format? DB scan, another form of clustering your data. Principal component analysis. So we start breaking up and looking at the different components in our data coming in. These are all algorithms used in data science, and there are more. These are kind of the mainline ones. And each one of these has many settings which you can play with to build a better model to predict your data and where you want it to go.
Python is the most widely used programming language today. When it comes to solving data science tasks and challenges, Python never ceases to surprise its audience. Most data scientists out there are already leveraging the power of Python every day. Hi, I'm Apeksha from Simplilearn, and well, after some thought and a bit more research, I was finally able to narrow down my choice of top Python libraries for data science. What are they? Let's find out. So let's talk about this amazing library, TensorFlow, which is also one of my favorites. So TensorFlow is a library for high performance numerical computations with around 35,000 GitHub commits and a vibrant community of around 1,500 contributors, and it's used across various scientific domains. It's basically a framework where we can define and run computations which involves tensors. And tensors, we can say, are partially defined computational objects again, where they will eventually produce a value. That was about TensorFlow. Let's talk about the features of TensorFlow. So TensorFlow is majorly used in deep learning models and neural networks, where we have other libraries like Torch and Theano also. But TensorFlow has hands down better computational graphical visualizations when compared to them. Also, TensorFlow reduces the error largely by 50 to 60% in neural machine translations. It's highly parallel in a way where it can train multiple neural networks and multiple GPUs for highly efficient and scalable models. This parallel computing feature of TensorFlow is also called pipelining. Also, TensorFlow has the advantage of seamless performance. As it's backed by Google, it has quicker updates, frequent new releases with the latest of features. Now, let's look at some applications. TensorFlow is extensively used in speech and image recognition, text-based applications, time series analysis and forecasting, and various other applications involving video detection. So, favorite thing about TensorFlow that it's already popular among the machine learning community, and most are open to trying it, and some of us are already using it. Now, let's look at an example of a TensorFlow model. In this example, we will not dive deep into the explanation of the model as it is beyond the scope of this video. So here we're using Amnes dataset, which consists of images of handwritten digits. Handwritten digits can be easily recognized by building a simple TensorFlow model. Let's see how. When we visualize our data using Matplotlib library, the inputs will look something like this. Then we create our TensorFlow model. To create a basic TensorFlow model, we need to initialize the variables and start a session. Then after training the model, we can validate the data and then predict the accuracy. This model has predicted 92% accuracy. Let's see, which is pretty well for this model. So that's all for TensorFlow. If you need to understand this tutorial in detail, then you can go ahead and watch our deep learning tutorial from Simplilearn as shown in the right corner. Interesting, right? Let's move on to the next library. Now let's talk about a common yet a very powerful Python library called NumPy. NumPy is a fundamental package for numerical computation in Python. It stands for Numerical Python as the name suggests. It has around 18,000 commits on GitHub with an active community of 700 contributors. It's a general purpose array processing package in a way that it provides high performance multi-dimensional objects called arrays and tools for working with them. Also, NumPy addresses the slowness problem partly by providing these multi-dimensional arrays that we talked about, and then functions and operators that operate efficiently on these arrays. Interesting, right? Now let's talk about the features of NumPy. It's very easy to work with large arrays and matrices using NumPy. NumPy fully supports object-oriented approach. For example, coming back to NdArray once again, it's a class possessing numerous methods and attributes. NdArray provides for larger and repeated computations. NumPy offers vectorization. It's more faster and compact than traditional methods. I always wanted to get rid of loops, and vectorization of NumPy clearly helps me with that. Now let's talk about the applications of NumPy. NumPy along with pandas is extensively used in data analysis, which forms the basis of data science. It helps in creating the powerful n-dimensional array. Whenever we talk about NumPy, the mention of the array, we cannot do it without the mention of the powerful n-dimensional array. Also, NumPy is extensively used in machine learning when we are creating machine learning models, as in where it forms the base of other libraries like SciPy, scikit-learn, etc. When you start creating the machine learning models in data science, you will realize that all the models will have their base as NumPy or pandas. Also, when NumPy is used with SciPy and Matplotlib, it can be used as a replacement of MATLAB. Now let's look at a simple example of an array in NumPy. As you can see here, there are multiple array manipulation routines. Like there are basic examples where we can copy the values from one array to another. We can give a new shape to an array from maybe one-dimensional to we can make it as a two-dimensional array. We can return a copy of the array collapsed into one dimension. Now let's look at an example where this is a Jupyter notebook and we will just create a basic array, and for detailed explanation you can watch our other videos which targets on these explanations of each libraries. So first of all, whenever we are using any library in Python, we have to import it. So now this np is the alias which we will be using. Let's create a simple array. Let's look what is the type of this array. So this is an NdArray type of array. Also, let's look what's the shape of this array. So this is a shape of the array. Now here we saw that we can expand the shape of the array. So this is where you can change the shape of the array using all those functions. Now let's create an array using arrange functions. If I give arrange 12, it will give me a 1D array of 12 numbers like this. Now we can reshape this array to 3, 4, or we can write it here itself. So this is how arrange function and the reshape function works for NumPy. Now let's discuss the next library, which is SciPy. So this is another free and open source Python library extensively used in data science for high-level computations. So this library, as the name suggests, stands for Scientific Python, and it has around 19,000 commits on GitHub with an active community of 600 contributors. It is extensively used for scientific and technical computations. Also, as it extends NumPy, it provides many user-friendly and efficient routines for scientific calculations. Now, let's discuss about some features of SciPy. So SciPy has this collection of algorithms and functions which is built on the NumPy extension of Python. Secondly, it has various high-level commands for data manipulation and visualization. Also, the ndimage function of SciPy is very useful in multi-dimensional image processing. and it includes built-in functions for solving differential equations, linear algebra, and many more. So that was about the features of SciPy. Now let's discuss its applications. So SciPy is used in multi-dimensional image operations. It has functions to read images from disk into NumPy arrays, to write arrays to disk as images, resize images, etc., solving differential equations, Fourier transforms, then optimization algorithms, linear algebra, etc. Let's look at a simple example to learn what kind of functions are there in SciPy. Here I'm importing the constants package of SciPy library. So in this package, it has all the constants. So here I'm just mentioning C or H or NA, and this library already knows what it has to fetch, like speed of light, Planck's constant, etc. So this can be used in further calculations. Data analysis is an integral part of data science. Data scientists spend most of the day in data munging and then cleaning the data also. Hence, mention of pandas is a must in data science lifecycle. Yes, pandas is the most popular and widely used Python library for data science, along with NumPy and Matplotlib. The name itself stands for Python data analysis, with around 17,000 commits on GitHub and an active community of 1,200 contributors. It is heavily used for data analysis and cleaning as it provides fast, flexible data structures like data frames, series, which are designed to work with structured data very easily and intuitively. Now let's talk about some features of pandas. So pandas offers this eloquent syntax and rich functionalities. Like there are various methods in pandas like drop NA, fill NA, which gives you the freedom to deal with missing data. Also, pandas provides a powerful apply function, which lets you create your own function and run it across a series of data. Now forget about writing those for loops while using pandas. Also, this library's high-level abstraction over low-level NumPy, which is written in pure C. Then it also contains these high-level data structures and manipulation tools, which makes it very easy to work with pandas, like their data structures and series. Now let's discuss the applications of pandas. So pandas is extensively used in general data wrangling and data cleaning. Then pandas also finds its usage in ETL jobs for data transformation and data storage, as it has excellent support for loading CSV files into its data frame format. Then pandas is used in a variety of academic and commercial domains, including statistics, finance, neuroscience, economics, web analytics, etc. Then pandas is also very useful in time series specific functionality like date range generation, moving window linear regression, date shifting, etc. Now let's look at a very simple example of how to create a data frame. So data frame is a very useful data structure in pandas, and it has very powerful functionalities. So here I'm only enlisting important libraries in data science. You can explore more of our videos to learn about these libraries in detail. So let's just go ahead and create a data frame. I'm using Jupyter Notebook again, and in this, before using pandas, here I'm importing the pandas library. Let me go and run this. So in data frame, we can import a file, a CSV file, Excel file. So there are many functions doing these things, and we can also create our own data and put it into data frame. So here I am taking random data and putting in a data frame. Also I'm creating an index and then also giving the column names. So PD is the alias we've given for pandas, random data of 6x4, index which is taking a range of 6 numbers, and column name I'm giving as ABCD. Now let's go ahead and look at it. So here it has created a data frame with my column names at ABCD, my list as 6 numbers 0 to 5, and a random data of 6x4. So data frame is just another table with rows and columns where you can do various functions over it. Also, I can go ahead and describe this data frame to see. So it's giving me all these functionalities where count and mean and standard deviation, etc. Okay, so that was about pandas. Now let's talk about the next library and the last one. So Matplotlib for me is the most fun library out of all of them. Why? Because it has such powerful yet beautiful visualizations. We'll see in the coming slides. Plot and Matplotlib suggests that it's a plotting library for Python. It has around 26,000 commits on GitHub and a very vibrant community of 700 contributors. And because of such graphs and plots that it produces, it's majorly used for data visualization. And also because it provides an object-oriented API which can be used to embed those plots into our applications. Let's talk about the features of Matplotlib. The PyPlot module of Matplotlib provides MATLAB-like interface. So Matplotlib is designed to be as usable as MATLAB with an advantage of being free and open source. Also, it supports dozens of backends and output types, which means you can use it regardless of which operating system you're using or which output format you wish. Pandas itself can be used as wrappers around Matplotlib's API so as to drive Matplotlib via cleaner and more modern APIs. Also, when you start using this library, you will realize that it has a very little memory consumption and a very good runtime behavior. Now let's talk about the applications of Matplotlib. It's important to discover the unknown relationship between the variables in your dataset. So this library helps to visualize the correlation analysis of variables. Also in machine learning, we can visualize 95% confidence interval of the model just to communicate how well our model fits the data. Then Matplotlib finds its application in outlier detection using scatterplot, etc. and to visualize the distribution of data to gain instant insights. Now let's make a very simple plot to get a basic idea. I've already imported the libraries here. So this function matplotlib inline will help you show the plots in the Jupyter notebook. This is also called a magic function. I won't be able to display my plots in the Jupyter notebook if I don't use this function. I'm using this function in NumPy to fix random state for reproducibility. Now I'll take my n as 30 and will assign random values to my variables. So this function is generating 30 random numbers. Here I'm trying to create a scatter plot. So I want to decide the area. Let's put this. So it's just multiplying 30 with random numbers to the power 2 so that we get the area of the plot, which we will see in just a minute. So using the scatter function and the alias of matplotlib as plt, I've created this. If I don't use this, then I have very small circles as my scatter plot. It's colorful, it's nice. So that's one very easy plot. I suggest that you explore more of matplotlib and I'm sure you will enjoy it. Let's create a histogram. So I'm using the style as ggplot and assigning some values to these variables, any random values. Now we are assigning bars and colors and alignment to the plot. And here we get the graph. So we can create different type of visualizations and plots and then work upon them using Matplotlib, and it's just that simple. So that was about the leading Python libraries in the field of data science. But along with these libraries, data scientists are also leveraging the power of some other useful libraries. For example, like TensorFlow, Keras is another popular library which is extensively used for deep learning and neural network modules. Keras wraps both TensorFlow and Theano backends, so it is a good option if you don't want to dive into details of TensorFlow. Then Scikit-learn is a machine learning library. It provides almost all the machine learning algorithms that you need, and it is designed to interpolate with NumPy and SciPy. Then we have Seaborn, which is another library for data visualization. We can say that Seaborn is an enhancement of Matplotlib as it introduces additional plot types.
And let's understand linear regression and dig into the theory. Understanding linear regression. Linear regression is a statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, remember that from before, and x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield, which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that, we put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle, a good estimate. Here we're going to dig deeper into the math behind the regression line. Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half, you can see where we've broken that down into pieces. And as it goes through the first 2 points, it computes the squared value of x, the squared value of y, and x times y. And then it takes all of x and adds them up, all of y adds them up, all of x squared adds them up, and so on and so on. And you can see we have the sum of equal to 15, the sum is equal to 20, all the way up to x times y, where the sum equals 66. This all comes from our formula for calculating a straight line, where y equals the slope times x plus the coefficient c. So we go down below, and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute, and where that information comes from is called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part, if you read through the brackets, you have the number of data points times the sum of x times y, which we computed one line at a time there, and that's just the 66. And take all that and you subtract it from the sum of x times the sum of y. And those have both been computed. So you have 15 times 20. And on the bottom, we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your c coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1, plus 2.2 equals 2.8, so on and so on. And here, the blue points represent the actual y values, and the brown points represent the predicted y values, based on the model we created. The distance between the actual and predicted values is known as residuals or errors. The best fit line should have the least sum of squares of these errors, also known as e-square. If we put these into a nice chart where you can see x and you can see y, what the actual values were, and you can see y predicted, you can easily see where we take y minus y predicted and we get an answer. What is the difference between those two? And if we square that, y minus y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1, all the way down until we have a summation equals 2.4. So, the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least e-square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, x and y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic, multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have y equals m1 times x1 plus m2 times x2, so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that, and we're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import NumPy as NP. And then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The NumPy, which stands for NumPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT, and then Seaborn as SNS. Seaborn works with the matplot library, so you have to always import matplotlibary, and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplotlibary inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplilearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/Simplilearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row, that's what the first colon is, comma, except for the last column. That's what the second part is, where we have a :-1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what pandas, one of the things pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the pandas. You could also open this up in an Excel and it would separate it since it is a comma separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is pandas. As you can see, we imported the matplotlibary.pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplotlibary inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot And let's just take a look at what this plot means. If you look at this plot, on mine the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any two of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in two steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the sklearn pre-processing, where we're going to import the label encoder and the one hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. We have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the third row. And in there we're going to take the label coder and we're going to fit and transform the X, also the third row. So we're going to take that third row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally we need to do a one hot encoder, which equals one hot encoder categorical features equals 3. And then we take the X and we go ahead and do that equal to one hot encoder fit transform X to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print X and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have X equals X colon comma 1 colon. All this is doing is removing that one extra column we put in there when we did our one hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or two so it all fits on one line. So from the sklearn module selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit, because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train, test, split, we take X and we take Y. We've already created those. X has the columns with the data in it, and Y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to just put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn .linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom and we were doing all this summization? And then we also looked at setting it up with the different lines, and then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case, we do X train and Y train, because we're using the training data, X being the data in and Y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy X equals true, fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a yPredict variable, and we're going to put in the X test. And let's see what that looks like. Scroll up a little bit, paste that in here, predicting the test set results. So here we have yPredict equals regressor.predict X test going in, and this gives us yPredict. Now because I'm in Jupyter inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print yPredict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print yPredict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. And we can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m into the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works, and understand how good it works. So, calculating the R-squared value. That's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the R-squared value. And we're looking at the error. So, in the R2 score, we take our y-test versus our y-predict. Y-test is the actual values we're testing. That was the one that was given to us, so we know are true. The Y-predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if R-squared value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression.
So where does logistic regression fit into the overall machine learning process? Machine learning is divided into two types, mainly two types. There is a third one called reinforcement learning, but we will not talk about that right now. So one is supervised learning and the other is unsupervised learning. Unsupervised learning uses techniques like clustering and association, and supervised learning uses techniques like classification and regression. Now, supervised learning is used when you have labeled data. You have historical data, then you use supervised learning. When you don't have labeled data, then you used unsupervised learning. In supervised learning, there are two types of techniques that are used, classification and regression, based on what is the kind of problem we are solving. Let's say we want to take the data and classify it. It could be binary classification, like a 0 or a 1. An example of classification we have just seen, whether the passenger has survived or not survived. It's like a 0 or 1. That is known as binary classification. Regression, on the other hand, is you need to predict a value, what is known as a continuous value. Classification is for discrete values. Regression is for continuous values. Let's say you want to predict the share price, or you want to predict the temperature that will be there. What will be the temperature tomorrow? That is where you use regression. Whereas classification are discrete values. Will the customer buy the product or will not buy the product? Will you get a promotion or you will not get a promotion? I hope you're getting the idea. Or it could be multi-class classification as well. Let's say you want to build an image classification model. So the image classification model would take an image as an input and classify into multiple classes, whether this image is of a cat or a dog or an elephant or a tiger. So there are multiple classes, so not necessarily binary classification. So that is known as multi-class classification. So we are going to focus on classification because logistic regression is one of the algorithms used for classification. Now, the name may be a little confusing. In fact, whenever people come across logistic regression, it always causes confusion because the name has regression in it, but we are actually using this for performing classification. Okay, so yes, it is logistic regression, but it is used for classification. And in case you are wondering, is there something similar for regression? Yes, for regression, we have linear regression. Keep that in mind. So linear regression is used for regression. Logistic regression is used for classification. So in this video, we are going to focus on supervised learning, and within supervised learning, we are going to focus on classification, and then within classification, we are going to focus on logistic regression algorithms. So first of all, classification. So what are the various algorithms available for performing classification? The first one is decision tree. There are of course multiple algorithms, but here we will talk about a few. Decision trees are quite popular and very easy to understand, and therefore they are used for classification. Then we have k nearest neighbors. This is another algorithm for performing classification. And then there is logistic regression, and this is what we are going to focus on in this video, and we are going to go into a little bit of details about logistic regression. Alright, what is logistic regression? As I mentioned earlier, logistic regression is an algorithm for performing binary classification. So let's take an example and see how this works. Let's say your car has not been serviced for quite a few years, and now you want to find out if it is going to break down in the near future. So this is like a classification problem. Find out whether your car will break down or not. So how are we going to perform this classification? So here's how it looks. If we plot the information along the x and y axis, x is the number of years since the last service was performed, and y is the probability of your car breaking down. And let's say this data was collected from several car users. It's not just your car, but several car users. So that is our labeled data. So the data has been collected, and for the number of years and when the car broke down and what was the probability, and that has been plotted along x and y axis. So this provides an idea, or from this graph we can find out whether your car will break down or not. We'll see how. So first of all, the probability can go from 0 to 1. As you all are aware, probability can be between 0 and 1. And as we can imagine, it is intuitive as well. As the number of years are on the lower side, maybe 1 year, 2 years, or 3 years till after the service, the chances of your car breaking down are very limited, right? So for example, chances of your car breaking down, or the probability of your car breaking down within 2 years of your last service are 0.1 probability. Similarly, 3 years is maybe 0.3 and so on. But as the number of years increases, let's say if it was 6 or 7 years, there is almost a certainty that your car is going to break down. That is what this graph shows. So this is an example of an application of the classification algorithm, and we will see in little details how exactly logistic regression is applied here. One more thing needs to be added here is that the dependent variables outcome is discrete. So if we are talking about whether the car is going to break down or not, so that is a discrete value, the y that we are talking about, the dependent variable that we are talking about. What we are looking at is whether the car is going to break down or not, yes or no. That is what we are talking about. So here the outcome is discrete and not a continuous value. So this is how the logistic regression curve looks. Let me explain a little bit what exactly and how exactly we are going to determine the outcome rather. So for a logistic regression curve, a threshold has to be set, saying that because this is a probability calculation, remember this is a probability calculation, and the probability itself will not be 0 or 1, but based on the probability we need to decide what the outcome should be. So there has to be a threshold, like for example 0.5 can be the threshold, let's say in this case. So any value of the probability below 0.5 is considered to be 0, and any value above 0.5 is considered to be 1. So an output of let's say 0.8 will mean that the car will break down. So that is considered as an output of 1, and let's say an output of 0.29 is considered as 0, which means that the car will not break down. So that's the way logistic regression works. Now let's do a quick comparison between logistic regression and linear regression, because they both have the term regression in them, so that can cause confusion. So let's try to remove that confusion. So what is linear regression? Linear regression is a process, is once again an algorithm for supervised learning. However, here you're going to find a continuous value. You're going to determine a continuous value. It could be the price of a real estate property. It could be your hike, how much hike you're going to get, or it could be a stock price. These are all continuous values. These are not discrete compared to a yes or a no kind of a response that we are looking for in logistic regression. So this is one example of a linear regression. Let's say the HR team of a company tries to find out what should be the salary hike of an employee. So they collect all the details of their existing employees, their ratings and their salary hikes, what has been given, and that is the labeled information that is available, and the system learns from this. It is trained and it learns from this labeled information, so that when a new employee's information is fed based on the rating, it will determine what should be the hike. So this is a linear regression problem and a linear regression example. Now, salary is a continuous value. You can get 5,000, 5,500, 5,600. It is not discrete like a cat or a dog or an apple or a banana. These are discrete, or a yes or a no. These are discrete values, right? So this where you're trying to find continuous values is where we use linear regression. So let's say, just to extend on this scenario, we now want to find out whether this employee is going to get a promotion or not. So we want to find out, that is a discrete problem, right? A yes or no kind of a problem. In this case, we actually cannot use linear regression, even though we may have labeled data. So this is the labeled data. So based on the employee rating, these are the ratings, and then some people got the promotion, and this is the ratings for which people did not get promotion. That is a no. And this is the rating for which people got promotion. We just plotted the data about whether a person has got, an employee has got promotion or not. Yes, no, right? So there is nothing in between. And what is the employee's rating? Okay. And ratings can be continuous. That is not an issue. But the output is discrete in this case. Whether employee got promotion, yes, no. Okay. So if we try to plot that and we try to find a straight line, this is how it would look. And as you can see, it doesn't look very right, because it looks like there will be a lot of errors. Thus, root mean square error, if you remember, for linear regression would be very, very high. And also the values cannot go beyond 0 or beyond 1. So the graph should probably look somewhat like this, clipped at 0 and 1. But still, the straight line doesn't look right. Therefore, instead of using a linear equation, we need to come up with something different. And therefore, the logistic regression model looks somewhat like this. So we calculate the probability, and if we plot that probability, not in the form of a straight line, but we need to use some other equation. We will see very soon what that equation is. Then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process. And this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening. And this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0. And when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this. And the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression, it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function, and the shape of the curve is S. It's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values, like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to be rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? Is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images. We can display using matplotlib some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix, the heat map, and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. Alright, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting. So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 93-94%, because the diagonals should have the maximum numbers, and the others other than diagonals, the cells other than the diagonals, should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0, and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and 1 has been predicted as number 8, and another one has been predicted as number 9. So these are 2 misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's the gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information, or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has there are, I think, 37 plus 5, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7, and 2 of them have been predicted as number 8, and so on and so forth. Okay, alright, so with that, let's go into Jupyter Notebook and see how the code looks. So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like NumPy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code, and so that it becomes easy to understand. So these are about 5 images, sample images, that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number, what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test, so that the training data set is used to train the system. So we pass this probably multiple times, and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of the entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x_train and y_train for the training data set. And what is x_train? These are the features, right, which is like the independent variable, and y_train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x_train, and since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2. So this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this, right? So this is the label. So the same way, x_train, y_train is for the training data set, x_test, y_test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of these. So x_train, the shape is 1383 by 64, and y_train has 1383 because there is nothing like the second part is not required here. And then x_test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that. so that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these two lines, so the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right? This is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this, in this case the data is not large, but by and large the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose we use the fit method. There is a method called fit which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method, and we pass this particular image, and we see that the shape is, or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So this confusion underscore matrix method takes two parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set, and then out of that the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations that will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So let me run this piece of code, and this is how the heat map looks. And as you can see here, the diagonals again are all the values are here, most of the values, so which means this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. Alright, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value, and also the predicted value. Both are 4. This is an image of 0, so the predicted value is also 0. Actual value is of course 0. Then this is the image of 9. So this has also been predicted correctly, 9, and actual value is 9. And this is the image of 1, and again this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
Need for confusion matrices. Classification models have multiple output categories. Most error measures will tell us the total error in our model, but we cannot use it to find out individual instances of errors in our models. So you have your input coming in, you have your classifier, it measures the error and it says, 53 of these are correct. But we don't know which 53% are correct. Is it 53% correct on guessing on the spam? Is it 23% guessing on spam and 27% guessing on what's not spam? This is where the confusion matrix comes in. So during the classification, we also have to overcome the limitations of accuracy. Accuracy can be misleading for classification problems. If there is a significant class imbalance, a model might predict the majority class for all cases and have a high accuracy score. And so you can see here we have our email coming in, and there's 2 spams. The classifier comes in and goes, hey, it only catches one of those spams and it misclassifies one that's not spam. So our model predicted 8 out of 10 instances and will have an accuracy of 80%. But is it classifying correctly? A confusion matrix represents a table layout of the different outcomes of prediction and results of a classification problem, and helps visualize its outcomes. And so you see here we have our simple chart, predicted and actual. The confusion matrix helps us identify the correct predictions of a model for different individual classes, as well as the errors. So you'll see here that the values predicted by our classifier are along the rows. This is what we're going to guess it is, or our model is guessing what this is based on its training. So we've already trained the model to guess whether it's spam or not spam or whatever it is you're working on. And then the actual values of our data set are along the columns. So this is the actual value it's supposed to be. People who can speak English will be classified as positives. So, because they have remember 0 or 1. Do you speak English? Yes, no. And you could extend this that they might have, do you speak French? Do you speak whatever languages? And so you might have a whole lot of classifiers that you would look at each one of these. People who cannot speak English will be classified as negatives. So there'll be a 0. So, 0 ones. The number of times our actual positive values are equal to predicted positive values gives us true positive, TP. The number of times our actual negative values are equal to predictive negative values gives us true negative, TN. The number of times our model wrongly predicts negative values as positives gives us a false positive, FP. And you'll see when you're working with these a lot, memorizing that it's false positive, you can easily figure out what that is, and pretty soon you're just looking at the FP or the TP, depending on what you're working on. And the number of times our model wrongly predicts positive values as negatives gives us a false negative, FP. Now, I'm going to do a quick step out here. Let's say you're working in the medical and we're talking about cancer. Do you really want a bunch of false negatives? You want 0 under false negative. So when we look at this confusion matrix, if you have 5% false positives and 5% false negatives, it'd be much better to even have 20% false positives because they go in and test it and 0 false negatives. The same might be true if you're working on, say, a car driving. Is this a safe place for the car to go? Well, you really don't want any false positives. Yes, this is safe right over the cliff. So again, when you're working on the project or whatever it is you're working on, this chart suddenly has huge value. We were talking about spam email. How many important emails, say from your banking overdraft charge coming in, that you want to be a true false negative? You don't want it to go in the spam folder. Likewise, you want to get as much of the spam out of there, but you don't want to miss anything really important. Confusion matrix metrics are performance measures which help us find the accuracy of our classifier. There are 4 main metrics: accuracy, precision, recall, and F1 score. The F1 score is the one I usually hear the most, and accuracy is usually what you put on your chart when you're sending in front of the shareholders. How accurate is it? People understand accuracy. F1 score is a little bit more on the math side, and so you got to be a little careful when you're quoting F1 scores in the when you're sitting there with all the shareholders, because a lot of them will just glaze over. So confusion matrix metrics are performance measures which help us find the accuracy of our classifier. There are 4 main metrics. Accuracy. The accuracy is used to find the portion of the correctly classified values. It tells us how often our classifier is right. It is the sum of all true values divided by the total values. And this makes sense. Again, it's one of those things. I don't want to, it depends on what you're looking for. Are you looking for not to miss any spam mails? Are you looking to drive down the road and not run anybody over? Precision is used to calculate the model's ability to classify positive values correctly. It answers the question, when the model predicts a positive value, how often is it right? It is the true positive divided by the total number of predicted positive values. Again, this one depends on what project you're working on, whether this is what you're going to be focusing on. So recall, it is used to calculate the model's ability to predict positive values. How often does the model actually predict the correct positive values? It is the true positives divided by the total number of actual positive values. And then your F1 score. It is the harmonic mean of recall and precision. It is useful when you need to take both precision and recall into account. Consider the following 2 confusion matrices derived from 2 different classifiers. To figure out which one performs better, we can find the confusion matrix for both of them. And you can see we're back to does it classify whether they can speak English or non-speaker. They don't know the English language. And so we put these 2 confusion matrices out here. We can go ahead and do the math behind that. We can look up the accuracy. That's the TPN plus TN over the TF plus TN plus FP plus FN. And so we get an accuracy of 0.8125. And we have a precision. If you do the precision, which is your TP, truth positive, over TP plus FP, we get 0.891. And if we do the recall, we'll end up with the 0.825. That's your TP over TP plus FN. And then, of course, your F1 score, which is 2 times precision times recall over precision plus recall. And we get the 0.857. And if we do that with another model, let's say we had 2 different models and we're trying to see which one we want to use for whatever reason, we might go ahead and compute the same things. We have our accuracy, our precision, and our recall, and our F1 score. And as we're looking at this, we might look at the accuracy, because that's really what we're interested in, is how many people are we able to classify as being able to speak English. I really don't want to know if I really don't want to know if they're non-speakers. I'd rather miss 10 people speaking English instead of 15. And so you can see from these charts, we'd probably go with the first model because it does a better job guessing who speaks English and has a higher accuracy, because in this case, that is what we're looking for. So with that, we'll go ahead and pull up a demo so you can see what this looks like in the Python setup and in the actual coding. For this, we'll go into Anaconda Navigator. If you're not familiar with Anaconda, it's a really good tool to use as far as doing display and demos. And for quick development. As a data scientist, I just love the package. Now, if you're going to do something heavier lifting, there's some limitations with Anaconda and with the setup. But in general, you can do just about anything in here with your Python. And for this, we'll go with Jupyter Notebook. Jupyter Lab is the same as Jupyter Notebook. You'll see they now have integration with PyCharm if you work in PyCharm. Certainly, there's a lot of other integrations that Anaconda has. And we've opened up my Simplilearn files I work on and create a new file called Confusion Matrix Demo. And the first thing we want to note is the data we're working with. Here I've opened it up in a WordPad or Notepad or whatever. You can see it's got a row of headers, comma separated, and then all the data going down below. And then I saved this in the same file so I don't have to remember what path I'm working on. Of course, if you have your data separated and you're working with a lot of data, you probably want to put it into a different folder or file depending on what you're doing. And the first thing we want to do is go ahead and import our tools. We're going to use the pandas. That's our data frame. If you haven't had a chance to work with the data frame, please review pandas data frame and go into Simplilearn. You can pull up the pandas data frame tutorial on there. And then we're going to use the scikit framework, which is all denoted as sklearn. And I can just pull this in. You can see here's the scikit-learn.org with the stable version that you can import into your Python. And from here, we're going to use the train test split. For splitting our data, we're going to do some pre-processing. We're going to use the logistic regression model. That's our actual machine learning model we're using. And then what this particular setup is about is we're going to do the accuracy score, the confusion matrix, and the classifier report. So let me go ahead and run that and bring all that information in. And just like we opened the file, we need to go ahead and load our data in here. So we're going to go ahead and do our pandas read CSV. And then just because we're in Jupyter Notebook, we can just put data to read the data in here. A lot of times we'll actually, let me just do this. I prefer to do just the head of the data, or the top part. And you can see we have age, sex, I'm not sure what CP stands for, test BPS, cholesterol. So a lot of different measurements. If you were in this domain, you'd want to know what all these different measurements mean. I don't want to focus on that too much because when we're talking about data science, a lot of times you have no idea what the data means. If you've ever looked up the breast cancer measurement, it's just a bunch of measurements and numbers. Unless you're a doctor, you're going to have no idea what those measurements mean. But if it's your specialty in your domain, you better know them. So we're going to go ahead and create Y, and we're going to set it equal to the target. So here's our target value here. And it's either 1 or 0. So we have a classifier. If you're dealing with 1, 0, true, false, what do you have? You have a classifier. And then our X is going to be everything except for the target. So we're going to go ahead and drop the target. Axes equals 1. Remember, that's columns versus the index or rows. Axes equals 0 would give you an error, but you would drop like row 2. And then we'll go ahead and just print that out so you can see what we're looking at. And here we have Y data, X data. And you can see from the X data we have the X head. And we can go ahead and just do print the Y head data and run that. So this is all loading the data that we've done so far. If there's a confusion in there, go back and rewind the tape and review it. And then we need to go ahead and split our data into our X train, X test, Y train, Y test. And then keep in mind, you always want to split the data before we do the scalar. And the reason is that you want the scalar on the training data to be set on the training data or fit to it, but not on the test data. Think of this as being out in the field. It could actually alter your results. So it's always important to make sure whatever you do to the training data or whatever fit you're doing is always done on the training, not on the test. And then we want to go ahead and scale the data. Now, we are working with linear regression model. And I'll mention this here in a minute when we get to the actual model. So sometimes you don't need to scale it when you're working with linear regression models. It's not going to change your result as much as, say, a neural network where it has a huge impact. But we're going to go ahead and here's our X train, X test, Y train, Y test. We create our scalar. We go ahead and scale. The scale is going to fit the X train. And then we're going to go ahead and take our X train and transform it. And then we also need to take our X test and transform it based on the scale on here so that our X is now between that nice -1 to 1. And so this is all our pre-data setup. And hopefully all of that looks fairly familiar to you if you've done a number of our other classes and you're up to the setup on here. And then what we want to go ahead and do is create our model. And we're going to use a logistic regression model. And from the logistic regression model, we're going to go ahead and fit our X train and Y train. And then we'll run our predicted value on here. And so let's go ahead and run that. And so now we actually have like our X test and our prediction. So if you remember from our matrix, we're looking for the actual versus the prediction and how those compare. And if I take us back up here, you're going to notice that we imported the accuracy score, the confusion matrix, and the classification report. And there's, of course, our logistic regression, the model we're using for this. And I did mention I was going to talk a little bit about scalar and the regression model. The scalar, on a lot of your regression models, your basic math standard regression models, and I'd have to look it up for the logistic regression model. When you're using a standard regression model, you don't need to scale the data. It's already just built in by the way the model works. In most cases. But if you're in a neural network and there's a lot of other different setups, then you really want to take this and fit that on there. And so we can go in and do the accuracy. And this is, if you remember correctly, we were looking at the accuracy with the English speaking. So this is saying our accuracy as to whether this person is, I believe this is the heart data set. It's going to be accurate about 85% of the time as far as whether it's going to predict the person's going to have a heart condition, or the 1 as it comes up with the 0, 1 on there. Which would mean at this point that you have an 85% being correct on telling someone they're extremely high risk for a heart attack kind of thing. And so we want to go ahead and create our confusion matrix. And let me just do that. Of course, the software does everything for us. So we'll go ahead and run this. And you can see right here, here's our 25 correct predictions right here. And if you remember from our slide, I'll just bring this over so it's a nice visual. We have our true positive, false positive. So we had 25 which were true, that it said, hey, this person's going to be high risk at heart. And we had 4 that were still high risk that it said were false. So out of these 25 people, or out of these 29 people, and that makes sense because you have 0.85, out of 29 people, it was correct on 25 of them. And so here's our accuracy score. We were just looking at that. Our accuracy is your true positive and your true negative over all of them. So how true is it? And there was our accuracy coming up here, 0.85. And then we have our nice matrix generated from that. And you can see right here is a similar matrix we had going from the slide. And this should start asking questions at this point. So if you're in a board meeting or you're working with this, you really want to start looking at this data here and saying, well, is this good enough? Is this number of people and hopefully you'd have a much larger data set. Is my confusion matrix showing for the true positive and false positive, is that acceptable for what we're doing? And of course, if you're going to put together whatever data you're putting out, you might want to separate the true negative, false positive, false negative, true positive. And you can simply do that by doing the confusion matrix. And then, of course, the ravel part lets you set that up. So you can just split that right up into a nice tuple. And the final thing we want to show you here in the coding on this part is the confusion matrix metrics. And so we can come in here and just use the matrix equals classification report, the y-test and the predict. And then we're going to take that classification report and go ahead and print that out. And you can see here it does a nice job giving you your accuracy, your micro average, your weighted average, you have your precision, your recall, your F1 score, and your support all in one window, so you can start looking at this data and saying, oh, okay, our precision's at 0.83, 0.87 for getting a positive, and 0.83 for the negative side for a 0. And we start talking about whether this is a valid information or not to use. And when we're looking at a heart attack prediction, we're only looking at one aspect. What's the chances of this person having a heart attack or not? You might have something where we went back to the languages. Maybe you also want to know whether they speak English or Hindi or French. And you can see right here that we can now take our confusion matrix and just expand it as big as we need to, depending on how many different classifiers we're working on.
What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. Problems that decision tree can solve. So let's look at the two different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between 3 types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with the gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like and how do we split the data. We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is a measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I, would be the percentage of that animal, times the log base 2 of the same, the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or our calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as the condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here. We have to make a couple changes as we go through this first part of the import. The first thing we bring in is numpy as np. That's very standard when we're dealing with mathematics, especially with very complicated machine learning tools. You almost always see the numpy come in for your numbers. It's called NumPy. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this and it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and there's this very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is, and very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 1, 2, 3, 4, 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code, or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balance data from the Panda read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance underscore data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, and let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or OpenOffice Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into two groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our x and y. Where do x and y come from? Well, x is going to be our data, and y is going to be the answer or the target. You can look at it as source and target. In this case, we're using x and y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in x equals the balance of the data dot values. The first brackets means that we're going to select all the lines in the database. So it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, we always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into two different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have X going in, where we're going to train it, and we have to know the answer to train it with. And then we have X test, where we're going to test that data. And we have to know in the end what the Y was supposed to be. And that's where this train test split comes in, that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So I'll have at least 3 splits, or I'll have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it, let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created. And then you'll see .predict. And that's very common in the sklearn modules, that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X test data in here. Now, if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredict in to print it. I could just as easily have put the print and put brackets around yPredict in to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our y-predict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since Simplilearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y-test, that's the one we ran the predict on, and then we put in our y-predict en, that's the answers we got, and we're just going to multiply that by 100, because this is just going to give us an answer as a decimal, and we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We may not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not. How does a random forest work as a whole? So to begin our random forest classifier, let's say we already have built 3 trees. And we're going to start with the first tree that looks like this. Just like we did in the example, this tree looks at the diameter. If it's greater than or equal to 3, it's true, otherwise it's false. So one side goes to the smaller diameter, one side goes to larger diameter. And if the color is orange, it's going to go to the right, true. We're using oranges now instead of lemons. And if it's red, it's going to go to the left, false. We build a second tree, very similar, but it's split differently. Instead of the first one being split by a diameter, this one, when they created it, if you look at that first bowl, it has a lot of red objects. So it says, is the color red? Because that's going to bring our entropy down the fastest. And so, of course, if it's true, it goes to the left. If it's false, it goes to the right. And then it looks at the shape, false or true, and so on and so on. And tree 3, is the diameter equal to 1? And it came up with this because there's a lot of cherries in this bowl. So that would be the biggest split on there is the diameter equal to 1? That's going to drop the entropy the quickest. And as you can see, it splits it into true. If it goes false, and they've added another category, does it grow in the summer? And if it's false, it goes off to the left. If it's true, it goes off to the right. Let's go ahead and bring these 3 trees so you can see them all in one image. So this would be 3 completely different trees categorizing a fruit. And let's take a fruit. Now let's try this. And this fruit, if you look at it, we've blackened it out. You can't see the color on it, so it's missing data. Remember, one of the things we talked about earlier is that a random forest works really good if you're missing data, if you're missing pieces. So this fruit has an image, but maybe the person had a black and white camera when they took the picture. And we're going to take a look at this, and it's going to have, they put the color in there, so ignore the color down there. But the diameter equals 3. We find out it grows in the summer equals yes, and the shape is a circle. And if you go to the right, you can look at what one of the decision trees did. This is the third one. Is the diameter greater than or equal to 3? Is the color orange? Well, it doesn't really know on this one, but if you look at the value, it'd say true, and it'd go to the right. Tree 2 classifies it as cherries. Is the color equal red? Is the shape a circle? True, it is a circle. So this would look at it and say, oh, that's a cherry. And then we go to the other classifier and it says, is the diameter equal 1? Well, that's false. Does it grow in the summer? True. So it goes down and looks at as oranges. So how does this random forest work? The first one says it's an orange. The second one said it was a cherry. And the third one says, it's an orange. And you can guess that if you have two oranges and one says it's a cherry, when you add that all together, the majority of the vote says orange. So the answer is, it's classified as an orange, even though we didn't know the color and we're missing data on it. I don't know about you, but I'm getting tired of fruit. So let's switch. And I did promise you we'd start looking at a case example and get into some Python coding. Today we're going to use the case, the iris flower analysis. Ooh, this is the exciting part as we roll up our sleeves and actually look at some Python coding. Before we start the Python coding, we need to go ahead and create a problem statement. Wonder what species of iris do these flowers belong to? Let's try to predict the species of the flowers using machine learning in Python. Let's see how it can be done. So here we begin to go ahead and implement our Python code. And you'll find that the first half of our implementation is all about organizing and exploring the data coming in. Let's go ahead and take this first step, which is loading the different modules into Python, and let's go ahead and put that in our favorite editor, whatever your favorite editor is. In this case, I'm going to be using the Anaconda Jupyter Notebook, which is one of my favorites. Certainly there's Notepad++ and Eclipse and dozens of others, or just even using the Python terminal window. Any of those will work just fine to go ahead and explore this Python coding. So here we go. Let's go ahead and flip over to our Jupyter Notebook. And I've already opened up a new page for Python 3 code, and I'm just going to paste this right in there. And let's take a look and see what we're bringing into our Python. The first thing we're going to do is from the sklearn.datasets import load iris. Now this isn't the actual data, this is just the module that allows us to bring in the data, the load iris. And the iris is so popular, it's been around since 1936 when Ronald Fisher published a paper on it, and they're measuring the different parts of the flower and based on those measurements predicting what kind of flower it is. And then if we're going to do a random forest classifier, we need to go ahead and import a random forest classifier from the sklearn module. So sklearn.ensemble import random forest classifier. And then we want to bring in two more modules. And these are probably the most commonly used modules in Python and data science with any of the other modules that we bring in. And one is going to be pandas. We're going to import pandas as PD. PD is the common term used for pandas. And pandas is basically creates a data format for us where when you create a pandas data frame, it looks like an Excel spreadsheet. And you'll see that in a minute when we start digging deeper into the code. Panda is just wonderful because it plays nice with all the other modules in there. And then we have NumPy, which is our numbers Python. And the numbers Python allows us to do different mathematical sets on here. We'll see right off the bat, we're going to take our NP and we're going to go ahead and seed the randomness with it with 0. So np.random.seed is seeding that as 0. This code doesn't actually show anything. We're going to go ahead and run it because I need to make sure I have all those loaded. And then let's take a look at the next module on here. The next 6 slides, including this one, are all about exploring the data. Remember I told you half of this is about looking at the data and getting it all set. So let's go ahead and take this code right here, the script, and let's get that over into our Jupyter Notebook. And here we go. We've gone ahead and run the imports. And I'm going to paste the code down here. And let's take a look and see what's going on. The first thing we're doing is we're actually loading the iris data. And if you remember up here, we loaded the module that tells it how to get the iris data. Now we're actually assigning that data to the variable iris. And then we're going to go ahead and use the df to define data frame. And that's going to equal PD. And if you remember, that's pandas as PD. So that's our pandas. And panda data frame. And then we're looking at iris data. And columns equals iris feature names. And we're going to do the df head. And let's run this so you can understand what's going on here. The first thing you want to notice is that our df has created what looks like an Excel spreadsheet. And in this Excel spreadsheet we have set the columns. So up on the top you can see the 4 different columns. And then we have the data, iris.data, down below. It's a little confusing without knowing where this data is coming from. So let's look at the bigger picture. And I'm going to go print. I'm just going to change this for a moment. And we're going to print all of iris and see what that looks like. So when I print all of iris, I get this long list of information. And you can scroll through here and see all the different titles on there. What's important to notice is that first off, there's a brackets at the beginning. So this is a Python dictionary. And in a Python dictionary, you'll have a key or a label, and this label pulls up whatever information comes after it. So feature names, which we actually used over here under columns, is equal to an array of sepal length, sepal width, petal width. These are the different names they have for the 4 different columns. And if you scroll down far enough, you'll also see data down here. Oh goodness, it came up right towards the top. And data is equal to the different data we're looking at. Now there's a lot of other things in here like target. We're going to be pulling that up in a minute. And there's also the names, the target names, which is further down. And we'll show you that also in a minute. Let's go ahead and set that back to the head. And this is one of the neat features of pandas and panda data frames is when you do df.head or the panda data frame.head, it'll print the first 5 lines of the data set in there, along with the headers if you have it. In this case, we have the column headers set to iris features. And in here, you'll see that we have 0, 1, 2, 3, 4. In Python, most arrays always start at 0. So when you look at the first 5, it's going to be 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So now we've got our iris data imported into a data frame. Let's take a look at the next piece of code in here. And so in this section here of the code, we're going to take a look at the target. And let's go ahead and get this into our notebook, this piece of code, so we can discuss it a little bit more in detail. So here we are in our Jupyter notebook. I'm going to put the code in here. And before I run it, I want to look at a couple things going on. So we have df species. And this is interesting because right here you'll see where I have df species in brackets, which is the key code for creating another column. And here we have iris.target. Now these are both in the pandas setup on here. So in pandas we can do either one. I could have just as easily done iris and then in brackets target, depending on what I'm working on. Both are acceptable. Let's go ahead and run this code and see how this changes. And what we've done is we've added the target from the iris data set as another column on the end. Now what species is, this is what we're trying to predict. So we have our data, which tells us the answer for all these different pieces. And then we've added a column with the answer. That way, when we do our final setup, we'll have the ability to program our neural network to look for this different data and know what a setosa is, or a varicolor, which we'll see in just a minute, or virginica. Those are the 3 that are in there. And now we're going to add one more column. I know, we're organizing all this data over and over again. It's kind of fun. There's a lot of ways to organize it. What's nice about putting everything onto one data frame is I can then do a printout and it shows me exactly what I'm looking at. And I'll show you where that's different, where you can alter that and do it slightly differently. But let's go ahead and put this into our script up to date now. And here we go. We're going to put that down here. And we're going to run that. And let's talk a little bit about what we're doing. Now, we're exploring data, and one of the challenges is knowing how good your model is. Did your model work? And to do this, we need to split the data up. And we split it into 2 different parts. They usually call it the training and the testing. And so in here, we're going to go ahead and put that in our database so you can see it clearly. And we've set it df. And remember, you can put brackets. This is creating another column. Is train, so we're going to use part of it for training. And this equals np, remember that stands for numpy, .random.uniform. So we're generating a random number between 0 and 1. And we're going to do it for each of the rows. That's where the length df comes from. So each row gets a generated number. And if it's less than 0.75, it's true. And if it's greater than 0.75, it's false. This means we're going to take 75% of the data, roughly, because there's a randomness involved, and we're going to use that to train it. And then the other 25%, we're going to hold off to the side and use that to test it later on. So let's flip back on over and see what the next step is. So now that we've labeled our database for which is training and which is testing, let's go ahead and sort that into 2 different variables, train and test. And let's take this code and let's bring it into our project. And here we go. Let's paste it on down here. And before I run this, let's just take a quick look at what's going on here. Is we have up above, we created, remember there's our def.head, which prints the first 5 rows. And we've added a column is train at the end. And so we're going to take that, we're going to create 2 variables. We're going to create 2 new data frames. One's called train, one's called test. 75% in train, 25% in test. And then to sort that out, we're going to do that by doing df, our main original data frame with the iris data in it. And if df is train equals true, that's going to go in the train. And if df is train equals false, it goes in the test. And so when I run this, we're going to print out the number in each one. Let's see what that looks like. And you'll see that it puts 118 in the training module, and it puts 32 in the testing module, which lets us know that there was 150 lines of data in here. So if you went and looked at the original data, you could see that there's 150 lines. And that's roughly 75% in one and 25% for us to test our model on afterward. So let's jump back to our code and see where this goes. In the next 2 steps, we want to do one more thing with our data, and that's make it readable to humans. I don't know about you, but I hate looking at zeros and ones. So let's start with the features, and let's go ahead and take those and make those readable to humans. And let's put that in our code. Let's see, here we go, paste it in. And you'll see here we've done a couple very basic things. We know that the columns in our data frame, again this is a panda thing, the df columns, and we know the first 4 of them, 0, 1, 2, 3, that'd be the first 4, are going to be the features or the titles of those columns. And so when I run this, you'll see down here that it creates an index, SEPA length, SEPA width, petal length, and petal width. And this should be familiar because if you look up here, here's our column titles going across, and here's the first 4. One thing I want you to notice here is that when you're in a command line, whether it's Jupyter Notebook or you're running command line in the terminal window, if you just put the name of it, it'll print it out. This is the same as doing print features. And the shorthand is you just put features in here. If you're actually writing a code and saving the script and running it by remote, you really need to put the print in there. But for this, when I run it, you'll see it gives me the same thing. But for this, we want to go ahead and we'll just leave it as features because it doesn't really matter. And this is one of the fun thing about Jupyter Notebooks is I'm just building the code as we go. And then we need to go ahead and create the labels for the other part. So let's take a look and see what that. For our final step in prepping our data, before we actually start running the training and the testing, is we're going to go ahead and convert the species on here into something the computer understands. So let's put this code into our script and see where that takes us. Alright, here we go. We've set y equal to pd.factorize train species of 0. So let's break this down just a little bit. We have our pandas right here, PD. Factorize. What's factorize doing? I'm going to come back to that in just a second. Let's look at what train species is and why we're looking at the group 0 on there. And let's go up here, and here is our species. Remember this that we created this whole column here for species? And then it has Setosa, 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 and if you scroll down enough, you'd also see Virginica and Varicolor. We need to convert that into something the computer understands, zeros and ones. So the trained species of 0, because this is in the format of an array of arrays, so you have to have the 0 on the end. And then species is just that column. Factorize goes in there and looks at the fact that there's only 3 of them. So when I run this, you'll see that y generates an array that's equal to, in this case it's the training set, and it's 0s, 1s, and 2s representing the 3 different kinds of flowers we have. So now we have something the computer understands, and we have a nice table that we can read and understand. And now, finally, we get to actually start doing the predicting. So here we go. We have 2 lines of code. Oh my goodness, that was a lot of work to get to 2 lines of code. But there is a lot in these 2 lines of code. So let's take a look and see what's going on here and put this into our full script that we're running. And let's paste this in here. And let's take a look and see what this is. We're creating a variable CLF, and we're going to set this equal to the random forest classifier. And we're passing two variables in here, and there's a lot of variables you can play with. As far as these two are concerned, they're very standard. In jobs, all that does is to prioritize it. Not something to really worry about. Usually when you're doing this on your own computer, you do in jobs equals 2. If you're working in a larger or big data and you need to prioritize it differently, this is what that number does, is it changes your priorities and how it's going to run across the system and things like that. And then the random state is just how it starts. 0 is fine for here. But let's go ahead and run this. We also have clf.fit train features, y. And before we run it, let's talk about this a little bit more. clf.fit. So we're training it. We are actually creating our random forest classifier right here. This is the code that does everything. And we're going to take our training set. Remember, we kept our test off to the side. And we're going to take our training set with the features, and then we're going to go ahead and put that in, and here's our target, the y. So the y is 0, 1, and 2 that we just created, and the features is the actual data going in that we put into the training set. And let's go ahead and run that. And this is kind of an interesting thing because it printed out the random forest classifier and everything around it. And so when you're running this in your terminal window or in a script like this, this automatically treats this just like when we were up here and I typed in y and it printed out y instead of print y. This does the same thing. It treats this as a variable and prints it out. But if you were actually running your code, that wouldn't be the case. And what is printed out is it shows us all the different variables we can change. And if we go down here, you can actually see in jobs equals 2. You can see the random state equals 0. Those are the two that we sent in there. You would really have to dig deep to find out all these different meanings of all these different settings on here. Some of them are self-explanatory if you kind of think about it a little bit, like max features is auto. So all the features that we're putting in there is just going to automatically take all 4 of them. Whatever we send it, it'll take. Some of them might have so many features because you're processing words. There might be like 1.4 million features in there because you're doing legal documents, and that's how many different words are in there. At that point, you probably want to limit the maximum features that you're going to process. And leaf nodes, that's the end nodes. Remember we had the fruit and we're talking about the leaf nodes. Like I said, there's a lot in this. We're looking at a lot of stuff here. So you might have, in this case, there's probably only 3 leaf nodes, maybe 4. You might have thousands of leaf nodes, at which point you do need to put a cap on that and say, okay, you can only go so far, and then we're going to use all of our resources on processing this. And that really is what most of these are about, is limiting the process and making sure we don't overwhelm a system. And there's some other settings in here. Again, we're not going to go over all of them. Warm start equals false. Warm start is if you're programming it one piece at a time externally. Since we're not going to continually to train this particular learning tree. And again, like I said, there's a lot of things in here that you'll want to look up more detail from the sklearn. And if you're digging in deep and running a major project on here. For today though, all we need to do is fit or train our features and our target y. So now we have our training model. What's next? If we're going to create a model, we now need to test it. Remember, we set aside the test feature, test group, 25% of the data. So let's go ahead and take this code and let's put it into our script and see what that looks like. Okay, here we go. And we're going to run this, and it's going to come out with a bunch of 0s, 1s, and 2s, which represents the 3 types of flowers, the setosa, the virginica, and the versicolor. And what we're putting into our predict is the test features, and I always kind of like to know what it is I am looking at. So real quick, we're going to do test features. And remember, features is an array of sepal length, sepal width, petal width. So when we put it in this way, it actually loads all these different columns that we loaded into features. So if we did just features, let me just do features in here so you can see what features looks like. This is just playing with pandas data frames. You'll see that it's an index. So when you put an index in like this into test features, into test, it then takes those columns and creates a panda data frames from those columns. And in this case, we're going to go ahead and put those into our predict. So we're going to put each one of these lines of data, the 5.0, 3.4, 1.5, 0.2, and we're going to put those in and we're going to predict what our new forest classifier is going to come up with. And this is what it predicts. It predicts 0, 0, 0, 1, 2, 1, 1, 2, 2, 2. And again, this is the flower type, Setosa, virginica, and versicolor. So now that we've taken our test features, let's explore that. Let's see exactly what that data means to us. So the first thing we can do with our predicts is we can actually generate a different prediction model. When I say different, we're going to view it differently. It's not that the data itself is different. So let's take this next piece of code and put it into our script. So we're pasting it in here, and you'll see that we're doing predict, and we've added underscore proba for probability. So there's our clf.predict probability. So we're running it just like we ran it up here, but this time with this we're going to get a slightly different result, and we're only going to look at the first 10. So you'll see down here, instead of looking at all of them, which was 27, you'll see right down here that this generates a much larger field on the probability. And let's take a look and see what that looks like and what that means. So when we do the predict underscore proba for probability, it generates 3 numbers. So we had 3 leaf nodes at the end. And if you remember from all the theory we did, this is the predictors. The first one is predicting a 1 for Setosa. It predicts a 0 for virginica, and it predicts a 0 for versicolor, and so on and so on and so on. And let's, you know what, I'm going to change this just a little bit. Let's look at 10 to 20, just because we can. And we start to get in a little different of data, and you'll see right down here, it gets to this one, this line right here. And this line has 0, 0.5, 0.5. And so if we're going to vote, and we have 2 equal votes, it's going to go with the first one. So it says Setosa gets 0 votes, virginica gets 0.5 votes, versicolor gets 0.5 votes, but let's just go with the virginica since these 2 are equal, and so on down the list. You can see how they vary on here. So now we've looked at both how to do a basic predict of the features, and we've looked at the predict probability. Let's see what's next on here. So now we want to go ahead and start mapping names for the plants. We want to attach names so that it makes a little more sense for us. And that's what we're going to do in these next 2 steps. We're going to start by setting up our predictions and mapping them to the names. So let's see what that looks like. And let's go ahead and paste that code in here and run it. And this goes along with the next piece of code. So we'll skip through this quickly and then come back to it a little bit. So here's iris.targetNames. And if you remember correctly, this was the names that we've been talking about this whole time, the Setosa, virginica, versicolor. And then we're going to go ahead and do the prediction again. We could have just set a variable equal to this instead of rerunning it each time. But we're going to go ahead and run it again, clf.predict test features. Remember that returns the 0s, the 1s, and the 2s. And then we're going to set that equal to predictions. So this time we're actually putting it in a variable. And when I run this, it distributes, and it comes out as an array, and the array is Setosa, 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 Setosa. We're only looking at the first 5. We could actually do, let's do the first 25, just so we can see a little bit more on there. And you'll see that it starts mapping it to all the different flower types, the versicolor and the virginica in there. And let's see how this goes with the next one. So let's take a look at the top part of our species in here, and we'll take this code and put it in our script. And let's put that down here and paste it. There we go. And we'll go ahead and run it. And let's talk about both these sections of code here and how they go together. The first one is our predictions. And I went ahead and did predictions through 25. Let's just do 5. And so we have Setosa, 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 Setosa. That's what we're predicting from our test model. And then we come down here and we look at test species. I remember I could have just done test.species.head, and you'll see it says Setosa, 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 and they match. So the first one is what our forest is doing, and the second one is what the actual data is. Now, we need to combine these so that we can understand what that means. We need to know how good our forest is, how good it is at predicting the features. So that's where we come up to the next step, which is lots of fun. We're going to use a single line of code to combine our predictions and our actuals so we have a nice chart to look at. And let's go ahead and put that in our script in our Jupyter notebook here. Let's see, let's go ahead and paste that in, and then because I'm on the Jupyter notebook, I can do a Control minus so you can see the whole line there. There we go, resize it. And let's take a look and see what's going on here. We're going to create in pandas, remember PD stands for pandas, and we're doing a crosstab. This function takes two sets of data and creates a chart out of them. So when I run it, you'll get a nice chart down here. And we have the predicted species. So across the top, you'll see the Setosa versicolor virginica and the actual species, Setosa versicolor virginica. And so the way to read this chart, and let's go ahead and take a look on how to read this chart here. When you read this chart, you have Setosa where they meet, you have versicolor where they meet, and you have virginica where they meet. And they're meeting where the actual and the predicted agree. So this is the number of accurate predictions. So in this case, it equals 30. If you add 13 plus 5 plus 12, you get 30. And then we notice here where it says virginica, but it was supposed to be versicolor. This is inaccurate. So now we have two inaccurate predictions and 30 accurate predictions. So we'll say that the model accuracy is 93. That's just 30 divided by 32. And if we multiply it by 100, we can say that it is 93% accurate. So we have a 93% accuracy with our model. I did want to add one more quick thing in here on our scripting before we wrap it up. So let's flip back on over to my script. In here, we're going to take this line of code from up above. I don't know if you remember it, but predicts equals the iris.target_names. So we're going to map it to the names. And we're going to run the prediction, and we read it on test features. But, we're not just testing it, we want to actually deploy it. So at this point, I would go ahead and change this. And this is an array of arrays. This is really important when you're running these to know that. So you need the double brackets. And I could actually create data, maybe let's just do 2 flowers. So maybe I'm processing more data coming in. And we'll put 2 flowers in here. And then I actually want to see what the answer is. So let's go ahead and type in preds and print that out. And when I run this, you'll see that I've now predicted 2 flowers that maybe I measured in my front yard as versicolor and versicolor. Not surprising since I put the same data in for each one. This would be the actual end product going out to be used on data that you don't know the answer for. So that's going to conclude our scripting part of this. Today we're going to cover the k nearest neighbors, a lot referred to as KNN. And KNN is really a fundamental place to start in the machine learning. It's a basis of a lot of other things, and just the logic behind it is easy to understand and incorporated in other forms of machine learning. So today, what's in it for you? Why do we need KNN? What is KNN? How do we choose the factor K? When do we use KNN? How does KNN algorithm work? And then we'll dive into my favorite part, the use case. Predict whether a person will have diabetes or not. That is a very common and popular used data set as far as testing out models and learning how to use the different models in machine learning. By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values, our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws, how sharp are their claws, and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those two characteristics. Now tell me if it is a cat or a dog. An odd question, usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats. It must be a cat. sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or is not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put K equals 5. We'll talk about K in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose K? How do we know K equals 5? I mean, that was the value we put in there, so we're going to talk about it. How do we choose the factor K? KNN algorithm is based on feature similarity. Choosing the right value of K is a process called parameter tuning and is important for better accuracy. So at K equals 3, we can classify, we have a question mark in the middle, as either a square or not. Is it a square or is it, in this case, a triangle? And so if we set K equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put K equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the K changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of K? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right K? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other. And in terms of KNN, the number of K, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things and it's going to pick those things and you might get a skewed answer. And if your K is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing K, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your K value odd. That helps it select better. So, in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the K value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise-free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where, I mean, you might get into a gig of data if it's really clean, it doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work? Consider a data set having 2 variables, height in centimeters and weight in kilograms. And each point is classified as normal or underweight. So we can see right here we have 2 variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the two edges of a triangle. We're computing the third edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point, and we placed it there in red, and we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13, and distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer, and it's not a really complicated math, so you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the 3 closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal. Hence, as per KNN algorithm, the class of 57,170 should be normal. So a recap of KNN. Positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, you know, if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine learning packages, but for a very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. You know, at 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly you can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up here and click on Cell Actually, we want to go ahead and first insert a cell below, and then I'm going to go back up to the top cell, and I'm going to change the cell type to Markdown. That means this is not going to run as Python. It's a Markdown language. So if I run this first one, it comes up in nice big letters, which is kind of nice. Remind us what we're working on. And by now, you should be familiar with doing all of our imports. We're going to import the pandas as PD, import numpy as NP. Pandas is the pandas data frame, and numpy is a number array. Very powerful tools to use in here. So we have our imports. So we've brought in our pandas, our numpy, our two general Python tools. And then you can see over here we have our train test split. By now you should be familiar with splitting the data. We want to split part of it for training our thing and then training our particular model. And then we want to go ahead and test the remaining data just to see how good it is. Pre-processing, a standard scalar preprocessor, so we don't have a bias of really large numbers. Remember in the data we had like number of pregnancies isn't going to get very large, where the amount of insulin they take can get up to 256. So 256 versus 6. That will skew results. So we want to go ahead and change that so that they're all uniform between -1 and 1. And then the actual tool. This is the k-neighbors classifier we're going to use. And finally, the last three are three tools to test, all about testing our model. How good is it? We just put down test on there. And we have our confusion matrix, our F1 score, and our accuracy. So we have our two general Python modules we're importing, and then we have our 6 modules specific from the sklearn setup. And then we do need to go ahead and run this, so these are actually imported. There we go. And then move on to the next step. And so in this set, we're going to go ahead and load the database. We're going to use pandas. Remember, pandas is PD. And we'll take a look at the data in Python. We looked at it in a simple spreadsheet, but usually I like to also pull it up so that we can see what we're doing. So here's our data set equals pd.readcsv. That's a pandas command. And the diabetes folder I just put in the same folder where my IPython script is. If you put in a different folder, you'd need the full length on there. We can also do a quick length of the data set. That is a simple Python command, len for length. We might even, let's go ahead and print that. We'll go print. And if you do it on its own line, length.dataset in the Jupyter Notebook, it'll automatically print it. But when you're in most of your different setups, you want to do the print in front of there. And then we want to take a look at the actual data set. And since we're in pandas, we can simply do dataset head. And again, let's go ahead and add the print in there. If you put a bunch of these in a row, you know, the dataset 1 head, dataset 2 head, it only prints out the last one. So I usually always like to keep the print statement in there. But because most projects only use one data frame, pandas data frame, doing it this way doesn't really matter. The other way works just fine. And you can see when we hit the run button, we have the 768 lines, which we knew, and we have our pregnancies. It's automatically given a label on the left. Remember, the head only shows the first 5 lines. So we have 0 through 4. And just a quick look at the data, you can see it matches what we looked at before. We have pregnancy, glucose, blood pressure, all the way to age, and then the outcome on the end. And we're going to do a couple things in this next step. We're going to create a list of columns where we can't have 0. There's no such thing as 0 skin thickness or 0 blood pressure, 0 glucose. Any of those you'd be dead. So not a really good factor if they have a 0 in there because they didn't have the data. And we'll take a look at that because we're going to start replacing that information with a couple of different things. And let's see what that looks like. So first we create a nice list. As you can see, we have the values we talked about: glucose, blood pressure, skin thickness. And this is a nice way when you're working with columns, is to list the columns you need to do some kind of transformation on. Very common thing to do. And then for this particular setup, we certainly could use there's some Panda tools that will do a lot of this, where we can replace the NA. But we're going to go ahead and do it as a dataset column equals dataset column.replace. This is still pandas. You can do it direct. There's also one that you look for your NAN. A lot of different options in here. But the NAN, numpy NAN is what that stands for, doesn't exist. So the first thing we're doing here is we're replacing the 0 with a numpy none. There's no data there. That's what that says. That's what this is saying right here. So put the 0 in, and we're going to replace zeros with no data. So if it's a 0, that means the person's, well, hopefully not dead. Hopefully they just didn't get the data. The next thing we want to do is we're going to create the mean, which is the integer from the data set from the column dot mean, where we skip NAs. We can do that. That is a pandas command there, the skip NA. So we're going to figure out the mean of that data set. And then we're going to take that data set column and we're going to replace all the NP/NaN with the means. Why did we do that? And we could have actually just taken this step and gone right down here and just replaced 0 and skip anything where, except you could actually, there's a way to skip zeros and then just replace all the zeros. But in this case, we want to go ahead and do it this way. So you can see that we're switching this to a non-existent value. Then we're going to create the mean. Well, this is the average person. So if we don't know what it is, if they did not get the data and the data is missing, one of the tricks is you replace it with the average. What is the most common data for that? This way you can still use the rest of those values to do your computation, and it kind of just brings that particular value or those missing values out of the equation. Let's go ahead and take this and we'll go ahead and run it. Doesn't actually do anything, so we're still preparing our data. If you wanted to see what that looks like, we don't have anything in the first few lines, so it's not going to show up, but we certainly could look at a row. Let's do that. Let's go into our data set. Let's print a data set, and let's pick, in this case, let's just do glucose. And if I run this, this is going to print all the different glucose levels going down, and we thankfully don't see anything in here that looks like missing data, at least on the ones it shows. You can see it skipped a bunch in the middle. Because that's what it does. If you have too many lines in Jupyter Notebook, it'll skip a few and go on to the next in a data set. Let me go and remove this, and we'll just zero out that. And of course, before we do any processing, before proceeding any further, we need to split the data set into our train and testing data. That way we have something to train it with and something to test it on. And you're going to notice we did a little something here with the pandas database code. There we go, my drawing tool. We've added in this right here off the data set. And what this says is that the first one in pandas, this is from the PD pandas, it's going to say within the data set, we want to look at the I location and it is all rows. That's what that says. So we're going to keep all the rows, but we're only looking at column 0 to 8. Remember column 9, here it is right up here, we printed it in here, is outcome. Well, that's not part of the training data, that's part of the answer. Yes, column 9, but it's listed as 8, number 8. So 0 to 8 is 9 columns. So 8 is the value. And when you see it in here, 0, this is actually 0 to 7. It doesn't include the last one. And then we go down here to Y, which is our answer, and we want just the last one, just column 8. And you can do it this way with this particular notation. And then if you remember, we imported the train test split. That's part of the sklearn right there. And we simply put in our X and our Y. We're going to do random state equals 0. You don't have to necessarily seed it. That's a seed number. I think the default is 1 when you seed it. I'd have to look that up. And then the test size. Test size is 0.2. That simply means we're going to take 20% of the data and put it aside so that we can test it later. That's all that is. And again, we're going to run it. Not very exciting. So far, we haven't had any printout other than to look at the data. But that is, a lot of this is prepping this data. Once you prep it, the actual lines of code are quick and easy. And we're almost there, but the actual running of our KNN, we need to go ahead and scale the data. If you remember correctly, we're fitting the data in a standard scaler, which means instead of the data being from 5 to 303 in one column, and the next column is 1 to 6, we're going to set that all so that all the data is between -1 and 1. That's what that standard scaler does. Keeps it standardized. And we only want to fit the scaler with the training set, but we want to make sure the testing set is, the X test going in is also transformed, so it's processing it the same. So here we go with our standard scaler. We're going to call it sc_x for the scaler, and we're going to import the standard scaler into this variable, and then our X train equals sc_x dot fit transform. So we're creating the scaler on the X train variable, and then our X test, we're also going to transform it. So we've trained and transformed the X train, and then the X test isn't part of that training. It isn't part of training the transformer. It just gets transformed. That's all it does. And again, we're going to go ahead and run this. And if you look at this, we've now gone through these steps, all 3 of them. We've taken care of replacing our zeros for key columns that shouldn't be 0, and we replaced that with the means of those columns. That way that they fit right in with our data models. We've come down here and we split the data. So now we have our test data and our training data. And then we've taken and we've scaled the data. So all of our data going in. Now, no, we don't train the Y part, the Y train and Y test. That never has to be trained. It's only the data going in. That's what we want to train in there. Then define the model using k-neighbors classifier and fit the train data in the model. So we do all that data prep, and you can see down here we're only going to have a couple lines of code where we're actually building our model and training it. That's one of the cool things about Python and how far we've come. It's such an exciting time to be in machine learning because there's so many automated tools. Let's see, before we do this, let's do a quick length of, and let's do y. Let's just do length of y. And we get 768. And if we import math, we do math dot square root. Let's do y train. There we go. It's actually supposed to be x train. Before we do this, let's go ahead and do import math and do math square root length of y test. And when I run that, we get 12.409. I wanted to show you where this number comes from we're about to use. 12 is an even number, so if you're ever voting on things, remember the neighbors all vote, don't want to have an even number of neighbors voting, so we want to do something odd. And let's just take one away and we'll make it 11. Let me delete this out of here. That's one of the reasons I love Jupyter Notebook, because you can flip around and do all kinds of things on the fly. So we'll go ahead and put in our classifier. We're creating our classifier now, and it's going to be the k-neighbors classifier. N neighbors equal 11. Remember we did 12 minus 1 for 11, so we have an odd number of neighbors. P equals 2, because we're looking for are they diabetic or not, and we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of measure this, but the Euclidean is the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll jump into the F1 score, and finally accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, y test, y predict. So those are the two values we're going to put in there, and let me go ahead and run that and print it out. And the way you interpret this is you have the y predicted, which would be your title up here. Could do, let's just do PRED, predicted across the top, and actual going down. Actual. It's always hard to write in here, actual. That means that this column here down the middle, that's the important column. And it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like three different, if you're looking at this across three different variables instead of just two, you'd end up with the third row down here and the column going down the middle. So in the first case we have and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an sklearn and running the KNN, the K nearest neighbor on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and we can pretty much round that off and just say we have an accuracy of 80%. Tells us it is a pretty fair fit in the model. Why support vector machine? So in this example, last week my son and I visited a fruit shop. Dad, is that an apple or a strawberry? So the question comes up, What fruit did I just pick up from the fruit stand? After a couple of seconds, you can figure out that it was a strawberry. So let's take this model a step further, and why not build a model which can predict an unknown data? And in this, we're going to be looking at some sweet strawberries or crispy apples. We want it to be able to label those two and decide what the fruit is. And we do that by having data already put in. So we already have a bunch of strawberries, we know are strawberries, and they're already labeled as such. We already have a bunch of apples, we know are apples and are labeled as such. Then once we train our model, that model then can be given the new data, and the new data is this image. In this case, you can see a question mark on it, and it comes through and goes, it's a strawberry. In this case, we're using the support vector machine model. SVM is a supervised learning method that looks at data and sorts it into one of two categories. And in this case, we're sorting the strawberry into the strawberry side. At this point, you should be asking the question, how does the prediction work? Before we dig into an example with numbers, let's apply this to our fruit scenario. We have our support vector machine. We've taken it and we've taken a labeled sample of data, strawberries and apples, and we draw on a line down the middle between the two groups. This split now allows us to take new data, in this case an apple and a strawberry, and place them in the appropriate group based on which side of the line they fall in. And that way we can predict the unknown. As colorful and tasty as the fruit example is, let's take a look at another example with some numbers involved, and we can take a closer look at how the math works. In this example, we're going to be classifying men and women, and we're going to start with a set of people with a different height and a different weight. And to make this work, we'll have to have a sample data set of female, where you have their height and weight, 174, 65, 174, 88, and so on. And we'll need a sample data set of the male. They have a height 179, 90, 180 to 80, and so on. Let's go ahead and put this on a graph so we have a nice visual. So you can see here we have two groups based on the height versus the weight. And on the left side, we're going to have the women. On the right side, we're going to have the men. Now, if we're going to create a classifier, let's add a new data point and figure out if it's male or female. So before we can do that, we need to split our data first. We can split our data by choosing any of these lines. In this case, we draw in two lines through the data in the middle that separates the men from the women. But to predict the gender of a new data point, we should split the data in the best possible way. And we say the best possible way because this line has a maximum space that separates the two classes. Here you can see there's a clear split between the two different classes, and in this one there's not so much a clear split. This doesn't have the maximum space that separates the two. That is why this line best splits the data. We don't want to just do this by eyeballing it. And before we go further, we need to add some technical terms to this. We can also say that the distance between the points in the line should be as far as possible. In technical terms, we can say the distance between the support vector and the hyperplane should be as far as possible. And this is where the support vectors are the extreme points in the data set. And if you look at this data set, they have circled 2 points which seem to be right on the outskirts of the women and one on the outskirts of the men. And hyperplane has a maximum distance to the support vectors of any class. Now you'll see the line down the middle, and we call this the hyperplane because when you're dealing with multiple dimensions, it's really not just a line but a plane of intersections. And you can see here where the support vectors have been drawn in dashed lines. The math behind this is very simple. We take d plus, the shortest distance to the closest positive point, which would be on the men's side, and d minus is the shortest distance to the closest negative point, which is on the women's side. The sum of d plus and d minus is called the distance margin, or the distance between the two support vectors that are shown in the dashed lines. And then, by finding the largest distance margin, we can get the optimal hyperplane. Once we've created an optimal hyperplane, we can easily see which side the new data fits in. And based on the hyperplane, we can say the new data point belongs to the male gender. Hopefully that's clear how that works on a visual level. As a data scientist, you should also be asking what happens if the hyperplane is not optimal. If we select a hyperplane having low margin, then there is a high chance of misclassification. This particular SVM model, the one we discussed so far, is also called or referred to as the LSVM. So far so clear, but a question should be coming up. We have our sample data set, but instead of looking like this, what if it looked like this, where we have two sets of data, but one of them occurs in the middle of another set? You can see here where we have the blue and the yellow, and then blue again on the other side of our data line. In this data set, we can't use a hyperplane. So when you see data like this, it's necessary to move away from a 1D view of the data to a 2-dimensional view of the data. And for the transformation, we use what's called a kernel function. The kernel function will take the 1D input and transfer it to a 2-dimensional output. As you can see in this picture here, the 1D when transferred to a 2-dimensional makes it very easy to draw a line between the two data sets. What if we make it even more complicated? How do we perform an SVM for this type of data set? Here you can see we have a 2-dimensional data set where the data is in the middle surrounded by the green data on the outside. In this case, we're going to segregate the two classes. We have our sample data set, and if you draw a line through, it's obviously not an optimal hyperplane in there. So to do that, we need to transfer the 2D to a 3D array. And when you translate it into a 3-dimensional array using the kernel, you can see where you can place a hyperplane right through it and easily split the data. Before we start looking at a programming example and dive into the script, let's look at the advantage of the support vector machine. We'll start with high-dimensional input space, or sometimes referred to as the curse of dimensionality. We looked at earlier 1 dimension, 2 dimension, 3 dimension. When you get to 1,000 dimensions, a lot of problems start occurring with most algorithms that have to be adjusted for. The SVM automatically does that in high dimensional space. One high dimensional space that we work on is sparse document vectors. This is where we tokenize the words in documents so we can run our machine learning algorithms over them. I've seen ones get as high as 2.4 million different tokens. That's a lot of vectors to look at. And finally, we have regularization parameter. The regularization parameter, or lambda, is a parameter that helps figure out whether we're going to have a bias or overfitting of the data. Whether it's going to be overfitted to a very specific instance or it's going to be biased to a high or low value. With the SVM, it naturally avoids the overfitting and bias problems that we see in many other algorithms. These three advantages of the support vector machine make it a very powerful tool to add to your repertoire of machine learning tools. Now, we did promise you a use case study where we're actually going to dive into some Python programming. And so we're going to go into a problem statement and start off with the zoo. So in the zoo example, we have family members going to the zoo, and we have the young child going, "Dad, is that a group of crocodiles or alligators?" Well, that's hard to differentiate. And zoos are a great place to start looking at science and understanding how things work, especially as a young child. And so we can see the parents sitting here thinking, well, what is the difference between a crocodile and an alligator? Well, one, crocodiles are larger in size, alligators are smaller in size. Snout width, the crocodiles have a narrow snout and alligators have a wider snout. And of course, in the modern day and age, the father's sitting here thinking, how can I turn this into a lesson for my son? And he goes, let a support vector machine segregate the two groups. I don't know if my dad ever told me that, but that would be funny. Now, in this example, we're not going to use actual measurements and data. We're just using that for imagery. And that's very common in a lot of machine learning algorithms and setting them up. But let's roll up our sleeves, and we'll talk about that more in just a moment as we break into our Python script. So here we arrive in our actual coding. And I'm going to move this into a Python editor in just a moment. But let's talk a little bit about what we're going to cover. First, we're going to cover in the code the setup, how to actually create our SVM. And you're going to find that there's only 2 lines of code that actually create it, and the rest of it is done so quick and fast that it's all here in the first page. And we'll show you what that looks like as far as our data, because we're going to create some data. I talked about creating data just a minute ago. And so we'll get into the creating data here, and you'll see this nice correction of our 2 blobs, and we'll go through that in just a second. And then the second part is we're going to take this and we're going to bump it up a notch. We're going to show you what it looks like behind the scenes. But let's start with actually creating our setup. I like to use the Anaconda Jupyter Notebook because it's very easy to use, but you can use any of your favorite Python editors or setups and go in there. But let's go ahead and switch over there and see what that looks like. So here we are in the Anaconda Python Notebook, or Anaconda Jupyter Notebook with Python. We're using Python 3. I believe this is 3.5, but it should be work in any of your 3x versions. And you'd have to look at the sklearn and make sure if you're using a 2x version or an earlier version. Now let's go ahead and put our code in there. And one of the things I like about the Jupyter Notebook is I can go up to View, and I'm going to go ahead and toggle the line numbers on to make it a little bit easier to talk about. And we can even increase the size because this is edited in this case I'm using Google Chrome Explorer, and that's how it opens up for the editor. Although like I said, any editor will work. Now the first step is going to be our imports. And we're going to import 4 different parts. The first 2 I want you to look at are line 1 and line 2 are numpy as np and matplotlibary.pyplot as plt. Now, these are very standardized imports when you're doing work. The first one is the numbers Python. We need that because part of the platform we're using uses that for the NumPy array. And I'll talk about that in a minute so you can understand why we want to use a NumPy array versus the standard Python array. And normally it's pretty standard setup to use NP for NumPy. The matplot library is how we're going to view our data. So this has, you do need the NP for the sklearn module, but the matplot library is purely for our use for visualization. And so you really don't need that for the SVM, but we're going to put it there so you have a nice visual aid and we can show you what it looks like. That's really important at the end when you finish everything, so you have a nice display for everybody to look at. And then finally, I'm going to jump one ahead to line number 4. That's the sklearn.datasets.samples generator import make blobs. And I told you that we were going to make up data. And this is a tool that's in the sklearn to make up data. I personally don't want to go to the zoo, get in trouble for jumping over the fence, and probably get eaten by the crocodiles or alligators as I work on measuring their snouts and width and length. Instead, we're just going to make up some data. And that's what that make blobs is. It's a wonderful tool if you're ready to test your setup and you're not sure about what data you're going to put in there. You can create this blob and it makes it real easy to use. And finally, we have our actual SVM, the sklearn import SVM on line 3. So that covers all our imports. We're going to create, remember I used the make blobs to create data. And we're going to create a capital X and a lowercase y equals make blobs in samples equals 40. So we're going to make 40 lines of data. It's going to have 2 centers with a random state equals 20. So each group's going to have 20 different pieces of data in it. And the way that looks is that we'll have under X an XY plane. So I'll have 2 numbers under X, and Y will be 0 or 1. That's the 2 different centers. So we have yes or no, in this case alligator or crocodile. That's what that represents. And then I told you that the actual sklearn or the SVM is in 2 lines of code. And we see it right here with CLF equals SVM.SVC kernel equals linear, and I set C equal to 1. Although in this example, since we are not regularizing the data, because we want it to be very clear and easy to see, I went ahead, you can set it to 1,000 a lot of times when you're not doing that. But for this thing, linear, because it's a very simple linear example, we only have the 2 dimensions, and it'll be a nice linear hyperplane. It'll be a nice linear line instead of a full plane. So we're not dealing with a huge amount of data. And then all we have to do is do CLF.fit x, y. And that's it. CLF has been created, and then we're going to go ahead and display it. And I'm going to talk about this display here in just a second, but let me go ahead and run this code. And this is what we've done, is we've created 2 blobs. You'll see the blue on the side and then kind of an orangish on the other side. That's our 2 sets of data. They represent, one represents crocodiles and one represents alligators. And then we have our measurements. In this case, we have like the width and length of the snout. And I did say I was going to come up here and talk just a little bit about our plot. And you'll see PLT, that's what we imported. We're going to do a scatter plot. That means we're just putting dots on there. And then look at this notation. I have the capital X, and then in brackets I have a colon, comma, 0. That's from NumPy. If you did that in a regular array, you'll get an error in a Python array. You have to have that in a NumPy array. It turns out that our make blobs returns a NumPy array. And this notation is great because what it means is the first part is the colon. It means we're going to do all the rows. That's all the data in our blob we created under capital X. And then the second part has a comma 0. We're only going to take the first value. And then if you notice, we do the same thing, but we're going to take the second value. Remember, we always start with 0 and then 1. So we have column 0 and column 1. And you can look at this as our XY plots. The first one is the X plot, and the second one is the Y plot. So the first one is on the bottom, 0, 2, 4, 6, 8, and 10. And then the second one, X of the 1, is the 4, 5, 6, 7, 8, 9, 10 going up the left-hand side. S equals 30 is just the size of the dots, so we can see them instead of real tiny dots. And then CMap equals plt.cm.paired. And you'll also see the C equals Y. That's the color. We're using 2 colors, 0, 1, and that's why we get the nice blue and the 2 different colors for the alligator and the crocodile. Now you can see here that we did this, the actual fit was done in 2 lines of code. A lot of times there'll be a third line where we regularize the data. We set it between like -1 and 1, and we reshape it. But for this, it's not necessary, and it's also kind of nice because you can actually see what's going on. And then if we wanted to actually run a prediction. Let's take a look and see what that looks like. And to predict some new data, and we'll show this again as we get towards the end of digging in deep, you can simply assign your new data. In this case, I am giving it a width and length 3, 4 and a width and length 5, 6. And note that I put the data as a set of brackets and then I have the brackets inside. And the reason I do that is because when we're looking at data, it's designed to process a large amount of data coming in. We don't want to just process one line at a time. And so in this case, I'm processing 2 lines. And then I'm just going to print, and you'll see CLF.predict new data. So the CLF and the .predict part is going to give us an answer, and let's see what that looks like. And you'll see 0, 1. So predicted the first one, the 3, 4, is going to be on the one side, and the 5, 6 is going to be on the other side. So one came out as an alligator, and one came out as a crocodile. Now that's a pretty short explanation for the setup, but really we want to dig in and see what's going on behind the scenes. And let's see what that looks like. So the next step is to dig in deep and find out what's going on behind the scenes. And also put that in a nice pretty graph. We're going to spend more work on this than we did actually generating the original model. And you'll see here that we go through a few steps, and I'll move this over to our editor in just a second. We come in, we create our original data. It's exactly identical to the first part, and I'll explain why we redid that and show you how not to redo that. And then we're going to go in there and add in those lines. We're going to see what those lines look like and how to set those up. And finally, we're going to plot all that on here and show it. And you'll get a nice graph with what we saw earlier when we were going through the theory behind this, where it shows the support vectors and the hyperplane. And those are done where you can see the support vectors as the dashed lines and the solid line, which is the hyperplane. Let's get that into our Jupyter notebook. Before I scroll down to a new line, I want you to notice line 13. It has plot show. And we're going to talk about that here in just a second, but let's scroll down to a new line down here. And I'm going to paste that code in. And you'll see that the plot show has moved down below. Let's scroll up a little bit. And if you look at the top here of our new section, 1, 2, 3, and 4 is the same code we had before. And let's go back up here and take a look at that. We're going to fit the values on our SVM, and then we're going to plot scatter it, and then we're going to do a plot show. So you should be asking, why are we redoing the same code? Well, when you do the plot show, that blanks out what's in the plot. So once I've done this plot show, I have to reload that data. Now we could do this simply by removing it up here, rerunning it, and then coming down here, and then we wouldn't have to rerun these first 4 lines of code. Now in this, it doesn't matter too much, and you'll see the plot show is down here and then removed right there on line 5. I'll go ahead and just delete that out of there because we don't want to blank out our screen. We want to move on to the next setup. So we can go ahead and just skip the first 4 lines because we did that before. And let's take a look at the AX equals plt.gca. Now right now, we're actually spending a lot of time just graphing. That's all we're doing here. Okay, so this is how we display a nice graph with our results and our data. AX is a very standard used variable when you're talking about PLT, and it's just setting it to that axis, the last axis in the PLT. It can get very confusing if you're working with many different layers of data on the same graph, and this makes it very easy to reference the AX. So this reference is looking at the PLT that we created and we already mapped out our 2 blobs on. And then we want to know the limits. So we want to know how big the graph is. We can find out the x limit and the y limit simply with the get x limit and get y limit commands, which is part of our matplot library. And then we're going to create a grid. And you'll see down here we've set the variable xx equal to np.linespace, x limit 0, x limit 1, 30. And we've done the same thing for the y space. And then we're going to go in here and we create a mesh grid. And this is a numpy command. So we're back to our numbers Python. Let's go through what these numpy commands mean with the line space and the mesh grid. We've taken xx, small xx equals np line space, and we have our x limit 0 and our x limit 1, and we're going to create 30 points on it. And we're going to do the same thing for the y-axis. Now, this has nothing to do with our evaluation. It's all we're doing is we're creating a grid of data. And so we're creating a set of points between 0 and the x limit. We're creating 30 points, and the same thing with the y. And then the mesh grid loops those all together so it forms a nice grid. So if we were going to do this, say between the limit 0 and 10 and do 10 points, we would have a 0, 0, 1, 1, 0, 1, 0, 2, 0, 3, 0, 4 to 10, and so on. You can just imagine a point at each corner of one of those boxes. And the mesh grid combines them all, so we take the YY and the XX we created and creates the full grid. And we've set that grid into the YY coordinates and the XX coordinates. Now remember, when we're working with NumPy and Python, we like to separate those. We like to have, instead of it being x comma 1, x comma y, and then x2 comma y2, and in the next set of data, it would be a column of x's and a column of y's. And that's what we have here, is we have a column of y's, and we put it as a capital YY, and a column of x's, capital XX, with all those different points being listed. And finally, we get down to the NumPy VStack. Just as we created those in the mesh grid, we're now going to put them all into one array, XY array. Now that we've created the stack of data points, we're going to do something interesting here. We're going to create a value z, and the z equals the CLF. That's our support vector machine we created, and we've already trained. And we have a dot decision function, and we're going to put the xy in there. So here we have all this data. We're going to put that xy in there, that data, and we're going to reshape it. And you'll see that we have the xx.shape in here. This literally takes the xx, resets it up connected to the y, and the z value lets us know whether it is the left-hand side. It's going to generate 3 different values, the z value does. And it'll tell us whether that data is a support vector to the left, the hyperplane in the middle, or the support vector to the right. So it generates 3 different values for each of those points. And those points have been reshaped so that they're right on a line, on those 3 different lines. So we've set all of our data up. We've labeled it to 3 different areas, and we've reshaped it. And we've just taken 30 points in each direction. If you do the math, you have 30 times 30, so that's 900 points of data. And we separated it between the 3 lines and reshaped it to fit those 3 lines. We can then go back to our matplot library, where we've created the AX, and we're going to create a contour. And you'll see here where we have contour, capital XX, capital YY. These have been reshaped to fit those lines. Z is the labels. So now we have the 3 different points with the labels in there, and we can set the colors equals K. And I told you we had 3 different labels, but we have 3 levels of data. The alpha just makes it kind of see-through, so it's only 0.5 of the value in there. So when we graph it, the data will show up from behind it, wherever the lines go. And finally, the line styles. This is where we set the 2 support vectors to be dash dash lines, and then a single one is just a straight line. That's what all of that setup does. And then finally, we take our ax.scatter. We're going to go ahead and plot the support vectors, but we've programmed it in there so that they look nice, like the dash dash line and the dash line on that grid. And you can see here, when we do the CLF dot support vectors, we are looking at column 0 and column 1. And then again, we have the S equals 100, so we're going to make them larger. And the line width equals 1, face colors equals none. Let's take a look and see what that looks like when we show it. And you can see when we get down to our end result, it creates a really nice graph. We have our 2 support vectors in dashed lines, and they have the near data. So you can see those 2 points, or in this case the 4 points, where those lines nicely cleave the data. And then you have your hyperplane down the middle, which is as far from the 2 different points as possible, creating the maximum distance. So you can see that we have our nice output for the size of the body and the width of the snout, and we've easily separated the 2 groups of crocodile and alligator. Congratulations! You've done it. We've made it. Of course, these are pretend data for our crocodiles and alligators, but this hands-on example will help you to encounter any support vector machine projects in the future, and you can see how easy they are to set up and look at in depth.
So what is K-means clustering? K-means clustering is an unsupervised learning algorithm. In this case, you don't have labeled data, unlike in supervised learning. So you have a set of data and you want to group them. And as the name suggests, you want to put them into clusters, which means objects that are similar in nature, similar in characteristics, need to be put together. So that's what K-means clustering is all about. The term K is basically a number. So we need to tell the system how many clusters we need to perform. So if K is equal to 2, there will be 2 clusters. If K is equal to 3, it's 3 clusters, and so on and so forth. That's what the K stands for. And of course, there is a way of finding out what is the best or optimum value of K for a given data. We will look at that. So that is K-means clustering. So let's take an example. K-means clustering is used in many scenarios, but let's take an example of cricket, the game of cricket. Let's say you received data of a lot of players from maybe all over the country or all over the world, and this data has information about the runs scored by the people or by the player, and the wickets taken by the player. And based on this information, we need to cluster this data into two clusters, batsmen and bowlers. So this is an interesting example. Let's see how we can perform this. So we have the data which consists of primarily two characteristics, which is the runs and the wickets. So the bowlers basically take wickets and the batsmen score runs. There will be, of course, a few bowlers who can score some runs, and similarly there will be some batsmen who would have taken a few wickets. But with this information, we want to cluster those players into batsmen and bowlers. So how does this work? Let's say this is how the data is. So there is information on the y-axis about the runs scored, and on the x-axis about the wickets taken by the players. So if we do a quick plot, this is how it would look. And when we do the clustering, we need to have the clusters like shown in the third diagram out here. So we need to have a cluster which consists of people who have scored high runs, which is basically the batsmen, and then we need a cluster with people who have taken a lot of wickets, which is typically the bowlers. There may be a certain amount of overlap, but we will not talk about it right now. So with k-means clustering, we will have here, that means k is equal to 2, and we will have two clusters, which is batsmen and bowlers. So how does this work? The way it works is, the first step in k-means clustering is the allocation of two centroids randomly. So 2 points are assigned as so-called centroids. So in this case, we want two clusters, which means k is equal to 2. So 2 points have been randomly assigned as centroids. Keep in mind, these points can be anywhere. There are random points. They are not really the centroids. Centroid means it's a central point of a given data set, but in this case, when it starts off, it's not really the centroid. Okay, so these points, though in our presentation here we have shown them 1 point closer to these data points and another closer to these data points, they can be assigned randomly anywhere. Okay, so that's the first step. The next step is to determine the distance of each of the data points from each of the randomly assigned centroids. So for example, we take this point and find the distance from this centroid and the distance from this centroid. This point is taken and the distance is found from this centroid and this centroid, and so on and so forth. So for every point, the distance is measured from both the centroids, and then whichever distance is less, that point is assigned to that centroid. So for example, in this case, visually it is very obvious that all these data points are assigned to this centroid and all these data points are assigned to this centroid. And that's what is represented here in blue color and in this yellow color. The next step is to actually determine the central point or the actual centroid for these two clusters. So we have this one initial cluster, this one initial cluster, but as you can see, these points are not really the centroid. Centroid means it should be the central position of this data set, central position of this data set. So that is what needs to be determined as the next step. So the central point or the actual centroid is determined and the original randomly allocated centroid is repositioned to the actual centroid of this new clusters. And this process is actually repeated. Now what might happen is some of these points may get reallocated. In our example, that is not happening probably, but it may so happen that the distance is found between each of these data points once again with these centroids. And if it is required, some points may be reallocated. We will see that in a later example, but for now we will keep it simple. So this process is continued till the centroid repositioning stops, and that is our final cluster. So this is so after iteration, we come to this position, this situation where the centroid doesn't need any more repositioning, and that means our algorithm has converged. Convergence has occurred, and we have the cluster, two clusters, we have the clusters with a centroid. So this process is repeated. The process of calculating the distance and repositioning the centroid is repeated till the repositioning stops, which means that the algorithm has converged and we have the final cluster with the data points and the centroids. So this is what you're going to learn from this session. We will talk about the types of clustering, what is k-means clustering, application of k-means clustering. K-means clustering is done using distance measure, so we will talk about the common distance measures, and then we will talk about how k-means clustering works and go into the details of k-means clustering algorithm, and then we will end with a demo and a use case for k-means clustering. So let's begin. First of all, what are the types of clustering? There are primarily two categories of clustering: hierarchical clustering and then partitional clustering. And each of these categories are further subdivided into agglomerative and divisive clustering and k-means and fuzzy c-means clustering. Let's take a quick look at what each of these types of clustering are. In hierarchical clustering, the clusters have a tree-like structure, and hierarchical clustering is further divided into agglomerative and divisive. Agglomerative clustering is a bottom-up approach. We begin with each element as a separate cluster and merge them into successively larger clusters. So for example, we have A, B, C, D, E, F. We start by combining B and C, form one cluster, D, E and E, form one more. Then we combine D, E and F, one more bigger cluster, and then add B, C to that, and then finally A to it. Compared to that, divisive clustering or divisive clustering is a top-down approach. We begin with the whole set and proceed to divide it into successively smaller clusters. So we have A, B, C, D, E, F. We first take that as a single cluster and then break it down into A, B, C, D, E, and F. Then we have partitional clustering split into two subtypes: k-means clustering and fuzzy c-means. In k-means clustering, the objects are divided into the number of clusters mentioned by the number k. That's where the k comes from. So if we say k is equal to 2, the objects are divided into two clusters, C1 and C2. And the way it is done is the features or characteristics are compared, and all objects having similar characteristics are clubbed together. So that's how k-means clustering is done. We will see it in more detail as we move forward. And fuzzy c-means is very similar to k-means in the sense that it clubs objects that have similar characteristics together, but while in k-means clustering, two objects cannot belong to, or any object, a single object cannot belong to two different clusters, in c-means objects can belong to more than one cluster. So that is the primary difference between k-means and fuzzy c-means. So what are some of the applications of k-means clustering? K-means clustering is used in a variety of examples or variety of business cases in real life, starting from academic performance, diagnostic systems, search engines, and wireless sensor networks, and many more. So let us take a little deeper look at each of these examples. Academic performance. So based on the scores of the students are categorized into A, B, C, and so on. Clustering forms a backbone of search engines. When a search is performed, the search results need to be grouped together. The search engines very often use clustering to do this. And similarly, in case of wireless sensor networks, the clustering algorithm plays the role of finding the cluster heads, which collects all the data in its respective cluster. So clustering, especially k-means clustering, uses distance measure. So let's take a look at what is distance measure. So while these are the different types of clustering, in this video we will focus on k-means clustering. So distance measure tells how similar some objects are. So the similarity is measured using what is known as distance measure. And what are the various types of distance measures? There is Euclidean distance, there is Manhattan distance, then we have squared Euclidean distance measure and cosine distance measure. These are some of the distance measures supported by k-means clustering. Let's take a look at each of these. What is Euclidean distance measure? This is nothing but the distance between 2 points. So we have learnt in high school how to find the distance between 2 points. This is a little sophisticated formula for that, but we know a simpler one is square root of y2 minus y1 whole square plus x2 minus x1 whole square. So this is an extension of that formula. So that is the Euclidean distance between 2 points. What is the squared Euclidean distance measure? It's nothing but the square of the Euclidean distance, as the name suggests. So instead of taking the square root, we leave the square as it is. And then we have Manhattan distance measure. In case of Manhattan distance, it is the sum of the distances across the x-axis and the y-axis. And note that we are taking the absolute value so that the negative values don't come into play. So that is the Manhattan distance measure. Then we have cosine distance measure. In this case, we take the angle between the two vectors formed by joining the points from the origin. So that is the cosine distance measure. Okay, so that was a quick overview about the various distance measures that are supported by k-means. Now let's go and check how exactly k-means clustering works. Okay, so this is how k-means clustering works. This is like a flowchart of the whole process. There is a starting point, and then we specify the number of clusters that we want. Now there are a couple of ways of doing this. We can do by trial and error. So we specify a certain number, maybe k is equal to 3 or 4 or 5 to start with, and then as we progress we keep changing until we get the best clusters. Or there is a technique called elbow technique, whereby we can determine the value of k. What should be the best value of k? How many clusters should be formed? So once we have the value of k, we specify that, and then the system will assign that many centroids. So it picks randomly, that to start with, randomly that many points that are considered to be the centroids of these clusters. And then it measures the distance of each of the data points from these centroids and assigns those points to the corresponding centroid from which the distance is minimum. So each data point will be assigned to the centroid which is closest to it. And thereby we have k number of initial clusters. However, this is not the final clusters. The next step it does is, for the new groups, for the clusters that have been formed, it calculates the mean position, thereby calculates the new centroid position. The position of the centroid moves compared to the randomly allocated one. So it's an iterative process. Once again, the distance of each point is measured from this new centroid point, and if required, the data points are reallocated to the new centroids, and the mean position or the new centroid is calculated once again. If the centroid moves, then the iteration continues, which means the convergence has not happened. The clustering has not converged. So as long as there is a movement of the centroid, this iteration keeps happening. But once the centroid stops moving, which means that the cluster has converged or the clustering process has converged, that will be the end result. So now we have the final position of the centroid, and the data points are allocated accordingly to the closest centroid. I know it's a little difficult to understand from this simple flowchart, so let's do a little bit of visualization and see if we can explain it better. Let's take an example. If we have a data set for a grocery shop. So let's say we have a data set for a grocery shop, and now we want to find out how many clusters this has to be spread across. So how do we find the optimum number of clusters? There is a technique called the elbow method. So when these clusters are formed, there is a parameter called within sum of squares, and the lower this value is, the better the cluster is. That means all these points are very close to each other. So we use this within sum of squares as a measure to find the optimum number of clusters that can be formed for a given data set. So we create clusters, or we let the system create clusters of a variety of numbers, maybe of 10 clusters, and for each value of k, the within SS is measured, and the value of k which has the least amount of within SS or WSS, that is taken as the optimum value of k. So this is the diagrammatic representation. So we have on the y-axis the within sum of squares or WSS, and on the x-axis we have the number of clusters. So as you can imagine, if you have k is equal to 1, which means all the data points are in a single cluster, the within SS value will be very high because they are probably scattered all over. The moment you split it into 2, there will be a drastic fall in the within SS value. That's what is represented here. But then as the value of k increases, the rate of decrease will not be so high. It will continue to decrease, but probably the rate of decrease will not be high. So that gives us an idea. So from here, we get an idea, for example, the optimum value of k should be either 2 or 3 or at the most 4. But beyond that, increasing the number of clusters is not dramatically changing the value in WSS because that pretty much gets stabilized. Okay, now that we have got the value of k, and let's assume that these are our delivery points, the next step is basically to assign two centroids randomly. So let's say C1 and C2 are the centroids assigned randomly. Now the distance of each location from the centroid is measured, and each point is assigned to the centroid which is closest to it. So for example, these points are very obvious that these are closest to C1, whereas this point is far away from C2. So these points will be assigned, which are close to C1 will be assigned to C1, and these points or locations which are close to C2 will be assigned to C2. And then, so this is how the initial grouping is done. This is part of C1 and this is part of C2. Then the next step is to calculate the actual centroid of this data, because remember, C1 and C2 are not the centroids. They have been randomly assigned points, and only thing that has been done was the data points which are closest to them have been assigned to them. But now in this step, the actual centroid will be calculated, which may be for each of these data sets somewhere in the middle. So that's like the mean point that will be calculated, and the centroid will actually be positioned or repositioned there. Same with C2. So the new centroid for this group is C2 in this new position, and C1 is in this new position. Once again, the distance of each of the data points is calculated from these centroids. Now remember, it's not necessary that the distance still remains or each of these data points still remain in the same group. By recalculating the distance, it may be possible that some points get reallocated. Like so. You see this? So this point earlier was closer to C2 because C2 was here, but after recalculating, repositioning, it is observed that this is closer to C1 than C2. So this is the new grouping. So some points will be reassigned. And again, the centroid will be calculated, and if the centroid doesn't change, so that is a repetitive process, iterative process. And if the centroid doesn't change, once the centroid stops changing, that means the algorithm has converged. And this is our final cluster with this as the centroid, C1 and C2 as the centroids, these data points as a part of each cluster. So I hope this helps in understanding the whole process, iterative process of k-means clustering. So let's take a look at the k-means clustering algorithm. Let's say we have x1, x2, x3, n number of points as our inputs, and we want to split this into k clusters, or we want to create k clusters. So the first step is to randomly pick k points and call them centroids. They are not real centroids because centroid is supposed to be a center point, but they are just called centroids. And we calculate the distance of each and every input point from each of the centroids. So the distance of x1 from C1, from C2, C3, each of the distances we calculate. And then find out which distance is the lowest and assign x1 to that particular random centroid. Repeat that process for x2. Calculate its distance from each of the centroids C1, C2, C3 up to Ck, and find which is the lowest distance and assign x2 to that particular centroid. Same with x3 and so on. So that is the first round of assignment that is done. Now we have k groups, because we have assigned the value of k. So there are k centroids, and so there are k groups. All these inputs have been split into k groups. However, remember, we picked the centroids randomly, so they are not real centroids. So now what we have to do, we have to calculate the actual centroids for each of these groups, which is like the mean position, which means that the position of the randomly selected centroids will now change, and they will be the mean positions of these newly formed k groups. And once that is done, we once again repeat this process of calculating the distance, right? So this is what we are doing as a part of step 4. We repeat step 2 and 3. So we again calculate the distance of x1 from the centroid C1, C2, C3, and then see which is the lowest value and assign x1 to that. Calculate the distance of x2 from C1, C2, C3 or whatever up to ck, and find whichever is the lowest distance and assign x2 to that centroid, and so on. In this process, there may be some reassignment. x1 was probably assigned to cluster C2, and after doing this calculation, maybe now x1 is assigned to C1. So that kind of reallocation may happen. So we repeat the steps 2 and 3 till the position of the centroids don't change or stop changing, and that's when we have convergence. So let's take a detailed look at each of these steps. So we randomly pick k cluster centers. We call them centroids because they are not really the centroids. So let us name them C1, C2 up to ck. And then step 2, we assign each data point to the closest center. So what we do, we calculate the distance of each x value from each c value. So the distance between x1, c1, distance between x1, c2, x1, c3, and then we find which is the lowest value, right? That's the minimum value we find, and assign x1 to that particular centroid. Then we go next to x2, find the distance of x2 from c1, x2 from c2, x2 from c3, and so on up to ck, and then assign it to the point or to the centroid which has the lowest value, and so on. So that is step number 2. In step number 3, we now find the actual centroid for each group. So what has happened? As a part of step number 2, we now have all the points, all the data points grouped into k groups, because we wanted to create k clusters, right? So we have k groups. Each one may be having a certain number of input values, and they need not be equally distributed, by the way. Based on the distance, we will have k groups. But remember, the initial values of the C1, C2 were not really the centroids of these groups, right? We assigned them randomly. So now in step 3, we actually calculate the centroid of each group, which means the original point which we thought was the centroid will shift to the new position, which is the actual centroid for each of these groups. Okay? And we again calculate the distance. So we go back to step 2, which is what? We calculate again the distance of each of these points from the newly positioned centroids. And if required, we reassign these points to the new centroids. So as I said earlier, there may be a reallocation. So we now have a new set or a new group. We still have k groups, but the number of items and the actual assignment may be different from what was in step 2 here. Okay, so that might change. Then we perform step 3 once again to find the new centroid of this new group. So we have again a new set of clusters, new centroids, and new assignments. We repeat this step 2 again. Once again we find, and then it is possible that after iterating through 3 or 4 or 5 times, the centroid will stop moving, in the sense that when you calculate the new value of the centroid, that will be same as the original value, or there will be very marginal change. So that is when we say convergence has occurred, and that is our final cluster. That's the formation of the final cluster. Alright, so let's see a couple of demos of k-means clustering. We will actually see some live demos in Python Notebook using Python Notebook. But before that, let's find out what's the problem that we are trying to solve. The problem statement is, let's say Walmart wants to open a chain of stores across the state of Florida, and it wants to find the optimal store locations. Now the issue here is, if they open too many stores close to each other, obviously they will not make profit. But if the stores are too far apart, then they will not have enough sales. So how do they optimize this? Now, for an organization like Walmart, which is an e-commerce giant, they already have the addresses of their customers in their database. So they can actually use this information or this data and use k-means clustering to find the optimal location. Now, before we go into the Python Notebook and show you the live code, I wanted to take you through very quickly a summary of the code in the slides, and then we will go into the Python Notebook. So in this block, we are basically importing all the required libraries like NumPy, Matplotlib, and so on. And we are loading the data that is available in the form of, let's say, the addresses. For simplicity's sake, we will just take them as some data points. Then the next thing we do is quickly do a scatter plot to see how they are related to each other with respect to each other. So in the scatter plot, we see that there are a few distinct groups already being formed. So you can actually get an idea about how the cluster would look and how many clusters, what is the optimal number of clusters. And then starts the actual k-means clustering process. So we will assign each of these points to the centroids and then check whether they are the optimal distance, which is the shortest distance, and assign each of the points, data points, to the centroids, and then go through this iterative process till the whole process converges. And finally, we get an output like this. So we have 4 distinct clusters, and which is, we can say that this is how the population is probably distributed across Florida state, and the centroids are like the location where the store should be, the optimum location where the store should be. So that's the way we determine the best locations for the store, and that's how we can help Walmart find the best locations for their stores in Florida. So now let's take this into Python Notebook. Let's see how this looks when we are running the code live. Alright, so this is the code for k-means clustering in Jupyter Notebook. We have a few examples here which we will demonstrate how k-means clustering is used, and even there is a small implementation of k-means clustering as well. Okay, so let's get started. Okay, so this block is basically importing the various libraries that are required, like Matplotlib and NumPy and so on and so forth, which would be used as a part of the code. Then we are going and creating blobs which are similar to clusters. Now this is a very neat feature which is available in Scikit-learn. Make blobs is a nice feature which creates clusters of data sets. So that's a wonderful functionality that is readily available for us to create some test data kind of thing. Okay, so that's exactly what we are doing here. We are using make blobs, and we can specify how many clusters we want. So centers we are mentioning here. So it will go ahead, and so we just mentioned 4. So it will go ahead and create some test data for us. And this is how it looks. As you can see, visually also we can figure out that there are 4 distinct classes or clusters in this data set. And that is what make blobs actually provides. Now, from here onwards, we will basically run the standard k-means functionality that is readily available. So we really don't have to implement k-means itself. The k-means functionality or the function is readily available. You just need to feed the data and we'll create the clusters. So this is the code for that. We import k-means, and then we create an instance of k-means, and we specify the value of k. This n underscore clusters is the value of k. Remember, in k means k is basically the number of clusters that you want to create, and it is a integer value. So this is where we are specifying that. So we have k is equal to 4, and so that instance is created. We take that instance, and as with any other machine learning functionality, fit is what we use. The function, or the method rather, fit is what we use to train the model. Here there is no real training kind of thing, but that's the call. Okay, so we are calling fit, and what we are doing here, we are just passing the data. So x has these values, the data that has been created, right? So that is what we are passing here. And this will go ahead and create the clusters, and then we are using, after doing fit, we run the predict, which basically assigns for each of these observations which cluster it belongs to. All right, so it will name the clusters. Maybe this is cluster 1, this is 2, 3, and so on, or I will actually start from 0, cluster 0, 1, 2, and 3 maybe, and then for each of the observations, it will assign based on which cluster it belongs to, it will assign a value. So that is stored in y underscore k means. When we call predict, that is what it does. And we can take a quick look at these y underscore k means, or the cluster numbers that have been assigned for each observation. So this is the cluster number assigned for observation 1, maybe this is for observation 2, observation 3, and so on. So we have how many? About, I think, 300 samples, right? So all the 300 samples, there are 300 values here. Each of them, the cluster number is given, and the cluster number goes from 0 to 3. So there are 4 clusters, so the numbers go from 0, 1, 2, 3. So that's what is seen here. Okay, now, so this was a quick example of generating some dummy data and then clustering that. Okay, and this can be applied if you have proper data. You can just load it up into X, for example, here, and then run the k-means. So this is the central part of the k-means clustering program example. So you basically create an instance, and you mention how many clusters you want by specifying this parameter n underscore clusters, and that is also the value of k, and then pass the data to get the values. Now, the next section of this code is the implementation of a k-means. Now, this is kind of a rough implementation of the k-means algorithm. So we will just walk you through. I will walk you through the code at each step, what it is doing, and then we will see a couple of more examples of how k-means clustering can be used in maybe some real life examples, real life use cases. All right. So in this case here, what we are doing is basically implementing the k-means clustering, and there is a function or a library calculates for a given 2 pairs of points. It will calculate the distance between them and see which one is the closest and so on. So this is pretty much like what k-means does, right? So it calculates the distance of each point or each data set from predefined centroid, and then based on whichever is the lowest, this particular data point is assigned to that centroid. So that is basically available as a standard function, and we will be using that here. So as explained in the slides, the first step that is done in case of k-means clustering is to randomly assign some centroids. So as a first step, we randomly allocate a couple of centroids, which we call here, we are calling as centers. And then we put this in a loop and we take it through an iterative process. For each of the data points, we first find out using this function pairwise distance argument. For each of the points, we find out which center or which randomly selected centroid is the closest. And accordingly, we assign that data or the data point to that particular centroid or cluster. And once that is done for all the data points, we calculate the new centroid by finding out the mean position with the center position, right? So we calculate the new centroid, and then we check if the new centroid is the coordinates or the position is the same as the previous centroid. The positions we will compare, and if it is the same, that means the process has converged. So remember, we do this process till the centroids or the centroid doesn't move anymore, right? So the centroid gets relocated each time this reallocation is done. So the moment it doesn't change anymore, the position of the centroid doesn't change anymore, we know that convergence has occurred. So till then, so you see here, this is like an infinite loop. While true is an infinite loop. It only breaks when the centers are the same. The new center and the old center positions are the same. And once that is done, we return the centers and the labels. Now, of course, as explained, this is not a very sophisticated and advanced implementation, very basic implementation, because one of the flaws in this is that sometimes what happens is the centroid, the position will keep moving, but the change will be very minor. So in that case, also that is actually convergence, right? So for example, the change is 0.0001. We can consider that as convergence. Otherwise, what will happen is this will either take forever or it will be never ending. So that's a small flaw here. So that is something, additional checks may have to be added here. But again, as mentioned, this is not the most sophisticated implementation. This is like a kind of a rough implementation of the k-means clustering. Okay, so if we execute this code, this is what we get as the output. So this is the definition of this particular function, and then we call that find underscore clusters, and we pass our data x and the number of clusters, which is 4. And if we run that and plot it, this is the output that we get. So this is, of course, each cluster is represented by a different color. So we have a cluster in green color, yellow color, and so on and so forth. And these big points here, these are the centroids. This is the final position of the centroids. And as you can see visually also, this appears like a kind of a center of all these points here, right? Similarly, this is like the center of all these points here, and so on. So this is the example, or this is an example of an implementation of k-means clustering. And next we will move on to see a couple of examples of how k-means clustering is used in maybe some real life scenarios or use cases. In the next example or demo, we are going to see how we can use k-means clustering to perform color compression. We will take a couple of images, so there will be 2 examples, and we will try to use k-means clustering to compress the colors. This is a common situation in image processing when you have an image with millions of colors, but then you cannot render it on some devices which may not have enough memory. So that is the scenario where something like this can be used. So before again we go into the Python notebook, let's take a look at quickly the code. As usual, we import the libraries and then we import the image, and then we will flatten it. So the reshaping is basically, we have the image information is stored in the form of pixels, and if the image is like, for example, 427 by 640 and it has 3 colors, so that's the overall dimension of the initial image. We just reshape it and then feed this to our algorithm, and this will then create clusters of only 16 clusters. So this colors, there are millions of colors, and now we need to bring it down to 16 colors. So we use k is equal to 16, and this is how, when we visualize, this is how it looks. These are all about 16 million possible colors. The input color space has 16 million possible colors, and we just compress it to 16 colors. So this is how it would look when we compress it to 16 colors, and this is how the original image looks, and after compression to 16 colors, this is how the new image looks. As you can see, there is not a lot of information that has been lost, though the image quality is definitely reduced a little bit. So this is an example which we are going to now see in Python notebook. Let's go into the Python notebook. And once again, as always, we will import some libraries and load this image called flower.jpg. Okay, so we'll load that, and this is how it looks. This is the original image, which has, I think, 16 million colors. And this is the shape of this image, which is basically what is the shape is nothing but the overall size, right? So this is 427 pixel by 640 pixel, and then there are 3 layers, which is this 3 basically is for RGB, which is red, green, blue. So color image will have that, right? So that is the shape of this. Now what we need to do is data. Let's take a look at how data is looking. So let me just create a new cell and show you what is in data. Basically we have captured this information. So data is what, let me just show you here. All right, so let's take a look at China. What are the values in China? And if we see here, this is how the data is stored. This is nothing but the pixel values. Okay, so this is like a matrix, and each one has about for this 427 by 640 pixels. All right, so this is how it looks. Now the issue here is these values are large, the numbers are large, so we need to normalize them to between 0 and 1. Right, so that's why we will basically create one more variable, which is data, which will contain the values between 0 and 1, and the way to do that is divide by 255. So we divide China by 255 and we get the new values in data. So let's just run this piece of code, and this is the shape. So we now have also, what we have done is we changed using reshape, we converted into the 3-dimensional into a 2-dimensional data set. And let us also take a look at how, let me just insert probably a cell here and take a look at how data is looking. All right, so this is how data is looking, and now you see this is the values are between 0 and 1. Right, so if you earlier noticed, in case of China the values were large numbers. Now everything is between 0 and 1. This is one of the things we need to do. All right, so after that, the next thing that we need to do is to visualize this, and we can take random set of maybe 10,000 points and plot it and check and see how this looks. So let us just plot this. And so this is how the original, the color, the pixel distribution is. These are 2 plots. One is red against green and another is red against blue, and this is the original distribution of the color. So then what we will do is we will use k-means clustering to create just 16 clusters for the various colors and then apply that to the image. Now what will happen is, since the data is large because there are millions of colors, using regular k-means may be a little time consuming. So there is another version of k-means which is called mini batch k-means. So we will use that, which processes in the overall concept remains the same, but this basically processes it in smaller batches. That's the only thing. Okay, so the results will pretty much be the same. So let's go ahead and execute this piece of code and also visualize this so that we can see that there are these. This is how the 16 colors would look. So this is red against green and this is red against blue. There is quite a bit of similarity between this original color schema and the new one, right? So it doesn't look very completely different or anything like that. Now we apply the newly created colors to the image, and we can take a look how this is looking now. We can compare both the images. So this is our original image and this is our new image. So as you can see, there is not a lot of information that has been lost. It pretty much looks like the original image. Yes, we can see that, for example, here there is a little bit, it appears a little dullish compared to this one, right? Because we kind of took off some of the finer details of the color, but overall the high level information has been maintained. At the same time, the main advantage is that now this is an image which can be rendered on a device which may not be that very sophisticated. Now let's take one more example with a different image. In the second example, we will take an image of the Summer Palace in China, and we repeat the same process. This is a high definition color image with millions of colors and also 3-dimensional. Now we will reduce that to 16 colors using k-means clustering, and we do the same process like before. We reshape it and then we cluster the colors to 16, and then we render the image once again, and we will see that the color, the quality of the image slightly deteriorates. As you can see here, this has much finer details in this which are probably missing here, but then that's the compromise, because there are some devices which may not be able to handle this kind of high density images. So let's run this code in Python notebook. Alright, so let's apply the same technique for another picture, which is even more intricate and has probably much complicated color schema. So this is the image. Now once again, we can take a look at the shape, which is 427 by 640 by 3. And this is the new data would look somewhat like this compared to the flower image. So we have some new values here, and we will also bring this. As you can see, the numbers are much big, so we will much bigger, so we will now have to scale them down to values between 0 and 1, and that is done by dividing by 255. So let's go ahead and do that and reshape it. Okay, so we get a two-dimensional matrix, and we will then, as a next step, we will go ahead and visualize this, how it looks, the 16 colors. And this is basically how it would look, 16 million colors. And now we can create the clusters out of this. The 16 k-means clusters we will create. So this is how the distribution of the pixels would look with 16 colors. And then we go ahead and apply this and visualize how it is looking for with the new, just the 16 colors. So once again, as you can see, this looks much richer in color, but at the same time, and this probably doesn't have, as we can see, it doesn't look as rich as this one, but nevertheless the information is not lost, the shape and all that stuff. And this can be also rendered on a slightly a device which is probably not that sophisticated. Okay, so that's pretty much it. So we have seen two examples of how color compression can be done using k-means clustering, and we have also seen in the previous examples of how to implement k-means, the code to roughly how to implement k-means clustering, and we use some sample data using blob to just execute the k-means clustering. All right, so with that, let's move on.
When we talk about the principal component analysis, we're going to cover dimensionality reduction, principal component analysis, what is it, important PCA terminologies, and you'll see it abbreviated normally as PCA, principal component analysis, PCA properties, PCA example, and then we'll pull up some Python code in our Jupyter Notebook and have some hands-on demo on the PCA and how it's used. Dimensionality reduction. Dimensionality reduction refers to the technique that reduces the number of input variables in a data set. And so you can see on the table on the right shows the orders made at an automobile parts retailer. The retailer sells different automobile parts from different companies. And you can see we have company BPEX, Isomax, and they have the item, the tire, the axle, an order ID, a price number, and a quantity. In order to predict the future sales, we find out that using correlation analysis that we just need 3 attributes. Therefore, we have reduced the number of attributes from 5 to 3. And clearly we don't really care about the part number. I don't think the part number would have an effect on how many tires are bought. And even the store, who's buying them, probably does not have an effect on that. In this case, that's what they've actually done, is remove those. And we just have the item, the tire, the price, and the quantity. One of the things you should be taking away from this is, in the scheme of things, we are in the descriptive phase. We're describing the data, and we're pre-processing the data. What can we do to clean it up? Why dimensionality reduction? Well, number one, less dimensions for a given data set means less computation or training time. That can be really important if you're trying a number of different models and you're rerunning them over and over again. And even if you have 7 gigabytes of data, that can start taking days to go through all those different models. So this is huge. This is probably the hugest part as far as reducing our data set. Redundancy is removed after removing similar entries from the data set. Again, pre-processing, some of our models, like a neural network, if you put in two of the same data, it might give them a higher weight than they would if it was just one. So we want to get rid of that redundancy. It also increases the processing time if you have multiple data coming in. Space required to store the data is reduced. So if we're committing this into a big data pool, we might not send the company that bought it. Why would we want to store two whole extra columns when we add it into that pool of data? Makes the data easy for plotting in 2D and 3D plots. This is my favorite part. Very important. You're in your shareholder meeting. You want to be able to give them a really good, clear, and simplified version. You want to reduce it down to something people can take in. It helps to find out the most significant features and skip the rest, which also comes in post-scribing. Leads to better human interpretation. That kind of goes with number 4, where it makes data easy for plotting. You have a better interpretation when we're looking at it. Principal component analysis. So what is it? Principal component analysis is a technique for reducing the dimensionality of data sets, increasing interpretability, but at the same time minimizing information loss. So we take some very complex data set with lots of variables, we run it through the PCA, we reduce the variables. We end up with a reduced variable setup. This is very confusing to look at because if you look at the end result, we have the different colors all lined up. So what we're going to take a look at is, let's say we have a picture here. Let's say you are asked to take a picture of some toddlers and you are deciding which angle would be the best to take the picture from. So if we come up here, we look at this, we say, okay, this is one angle. We get the back of a lot of heads, not many faces. So we'll do it from here. We might get the one person up front smiling. A lot of the people in the class are missing, so we have a huge amount off to the right of blank space. Maybe from up here, again, we have the back of someone's head. And it turns out that the best angle to click the picture from might be this bottom left angle. You look at it and you say, hey, that makes sense. It's a good configuration of all the people in the picture. Now, when we're talking about data, it's not, you really can't do it by what you think is going to be the best. We need to have some kind of mathematical formula so it's consistent and so it makes sense in the back end. One of the projects I worked on many years ago had something similar to the iris. And if you've ever done the iris data set, it's probably one of the most common ones out there where they have the flower and they're measuring the stamen in the petals, and they have width and they have length of the petal. Instead of putting through the width and the length of the petal, we could just as easily do the width to length ratio. We can divide the width by the length and you get a single number where you had 2. That's the kind of idea that's going on into this in pre-processing and looking at what we can do to bring the data down. The very simplified example on my iris petal example. When we look at the similarity in PCA, we find the best picture or projection of the data points. And so when we look down at from one angle, we've drawn a line down there, we can see these data points based on, in this case, just 2 variables. Now keep in mind, we're usually talking about 36, 40 variables. Almost all of your business models usually have about 26 to 27 different variables they're looking at. Same thing with like a bank loan model. We're talking 26 to 36 different variables they're looking at that are going in. So what we want to do is we want to find the best view. In this case, we're just looking at the XY. We look down at it and we have our second idea, PC2. And again, we're looking at the XY, this time from a different direction. Here, for our ease, we can consider that we get 2 principal components, namely PC1 and PC2. Comparing both the principal components, we find the data points are sufficiently spaced in PC1. So if you look at what we got here, we have PC1. You can see along the line how the data points are spaced versus the spacing in PC2. And that's what they're coming up with. What is going to give us the best look for these data points when we combine them? And we're looking at them from just a single angle. Whereas in PC2, they are less spaced, which makes the observation and further calculations much more difficult. Therefore, we accept the PC1 and not the PC2 as the data points are more spaced. Now, obviously, the back-end calculations are a little bit more complicated when we get into the math of how they decide what is more valuable. This gives you an idea, though, that when we're talking about this, we're talking about the perspective, which would help in understanding how PCA analysis works. What we want to go ahead and do is dive into the important terminologies under PCA. And important terminologies are views, the perspective through which data points are observed. And so you'll hear that if someone's talking about a PCA presentation and they're not taking the time to reduce it to something that the average person, shareholders, can understand, you might hear them refer to it as the different views. What view are we taking? Dimension, number of columns in a data set are called the dimensions of that data set. And we talked about, you'll hear features, dimensions. Now I was talking about features. There's usually, when you're running a business, you're talking 25, 26, 27 different features minimal. And then you have the principal component, new variables that are constructed as linear combinations or mixtures of the initial variables. Principal component is very important. It's a combination. If you remember my flower example, it would be the width over the length of the petal as opposed to putting both width and length in. You just put in the ratio instead, which is a single number versus two separate numbers. Projections, the perpendicular distance between the principal component and the data points. And that goes to that line we had earlier. It's that right angle line of where how all those points fall onto the line. Important properties. Important properties. Number of principal components is always less than or equal to the number of attributes. That just makes common sense. You're not going to do 10 principal properties with only 3 features. You're trying to reduce them, so it's just kind of goofy, but it is important to remember that. People will throw weird code out there and just randomly do stuff instead of really thinking it through. Principal components are orthogonal. And this is what we're talking about, that right angle from the line. When we do PC1, we're looking at how those points fall on to that line. Same thing with PC2. And we want to make sure that PC1 does not equal PC2. We don't want to have the same 2 principal points when we do 2 points. The priority of principal components decreases as their numbers increase. This is important to understand. If you're going to create one principal component, everything is summarized into that one component. As we go to 2 components, the priority, how much it holds value, decreases as we go down. So if you have 5 different points, each one of those points is going to have less value than just the one point, which has everything summarized in it. How PCA works. I said there was more in the back end. When we talk about the math, this is what we're talking about, is how does it actually work. So now we have understanding that you're looking at a perspective. Now we want to see how that math side works. PCA performs the following operations in order to evaluate the principal components for a given data set. First, we start with the standardization. Then we have a covariance matrix computation. And we use that to generate our eigene vectors and eigene values, which is the feature vector. And if you remember, the eigene vector is like a translation. If we're moving the data from x equals 1 to x equals 2, or whatever, altering it, and the eigene value is the final value that we generate. When we talk about standardization, the main aim of this step is to standardize the range of the attributes so that each one of them lie within similar boundaries. This process involves removal of the mean from the variable values and scaling the data with respect to the standard deviation. And you can see here we have z equals the variable values minus the mean over the standard deviation. The covariance matrix computation. Covariance matrix is used to express the correlation between any 2 or more attributes in multi-dimensional data set. The covariance matrix has the entries as the variance and the covariance of the attribute values. The variance is denoted by var and the covariance is denoted by cov. On the right, we can see the covariance matrix for 2 attributes and their values. When we do a hands-on look at the code, we'll do a display of this so you can see what we're talking about and what that looks like. For now, you can just notice that this is a matrix that we're generating with the variance and then the covariance of x to y. On the right side, we can see the covariance table for more than 2 attributes in a multi-dimensional data set. And this is what I was talking about. We usually are looking at not just 1 feature or 2 features. We're usually looking at 25, 30 features going on. And so if we do a setup like this, we should see all those different features as the different variables. Covariance matrix tells us how the 2 or more variables are related. Positive covariance indicate that the value of one variable is directly proportional to the other variable. Negative covariance indicate that the value of one variable is inversely proportional to the other variable. That is always important to note whenever we're doing any of these matrices, that we're going to be looking at that positive and negative, whether it's inverted or not. And then we have the eigene values and the eigene vectors. Eigene values and eigene vectors are the mathematical value that are extracted from the covariance table. They are responsible for the generation of a new set of variables from the old set of variables, which further lead to the construction of the principal components. Eigene vectors do not change directions after linear transformation. Eigene values are the scalars or the magnitude of the eigene vectors. And again, this is just transforming that data. So we're going to change the vector b to the b prime as denoted on the chart. And so when we have like multiple variables, how do we calculate that new variable? And then we have feature vectors. Feature vectors is simply a matrix that has eigene vectors of the components that we decide to keep as the columns. Here we decide whether we must keep or discard the less significant principal components that we have generated in the above steps. This becomes really important as we start looking at the back end of this, and we'll do this in the demo, but one of the more important steps to understand. And so we have the PCA example. Consider matrix X with n rows or observations and k columns or variables. Now for this matrix, we would construct a variable space with as many dimensions as the variable. But for our simplicity, let's consider this 3 dimensions for now. Now each observation, row of the matrix X, is placed in the k-dimensional variable space, such that the rows in the data table form a swarm of points in this space. Now we find the mean of all the observations and then place it along the data points on the plot. The first principal component is a line that best accounts for the shape of the point swarm. It represents the maximal variance direction in the data. Each observation may be projected onto this line in order to get a coordinate value along the PC1. This value is known as a score. Usually only one principal component is insufficient to model the systematic variation for a data set. Thus, a second principal axis is created. The second principal component is oriented such that it reflects the second largest source of variation in the data. While being orthogonal to PC1, PC2 also passes through the average point. Let's go ahead and pull this up and just see what that means inside our Python scripting. I'm going to use the Anaconda Navigator, and I will be in Python 3.6 for this example. I believe there's even like a 3.9 out. I tend to stay in 3.6 because a lot of the models I use, especially with the neural networks, are stable in 3.6. And then we open up our Jupyter. I'm in Chrome, and we go ahead and create a new Python 3. And for ease of use, our team in the back was nice enough to put this together for me. And we'll go ahead and start with the libraries. The first thing I like to do whenever I'm looking at any new setup, well, you know what, let's do the libraries first. We're going to do our basic libraries, which is matplotlib library, the PLT from the matplotlib library, pandas, our data frame, PD, numpy, our numbers array, np, seaborn for graphing, SNS, that goes with the plot that actually sits on matplotlib library, so the seaborn sits on there. And then we have our ampersand, because we're in Jupyter Notebook, matplotlib library inline. The newer version actually doesn't require that, but I put it in there anyway, just because I'm so used to it. And then we want to go ahead and take a look at the data. And in this case, we're going to pull in, certainly you can have lots of fun with different data, but we're going to use the cancer data set. And one of the reasons a cancer data set is it has like 36, 35 different features. So it's kind of fun to use that as our base for this. And we'll go ahead and run this and look at our keys. And the first thing we notice in our keys for the cancer data set is we have our data, we have our target, our frame, target names, description, feature names, and file name. So what we're looking for in all this is, well, let's take a look at the description. Let's go in here and pull up the description on here. I'm not going to spend a huge amount of time on the description because we don't want to get into a medical domain. We want to focus on our PCA setup. What's important is you start looking at what the different attributes are, what they mean. If you were in the medical field, you'd want to note all these different things, what they're measuring, where it's coming from. You can actually see the actual different measurements they're taking. No missing attributes. We page all the way to the bottom. And you're going to have your data, in this case our target. And if you dig deep enough to the target, let's actually do this. Let's go ahead and print target names. Real quick here, I always like to just take a look and see what's on the other end of this. Target names. Run that. And so the target name is it malignant or is it benign? So in other words, is this dangerous growth or is it something we don't have to worry about? That's the bottom line with the cancer in this case. And then we can go ahead and load our data. And you know what, let me go up just a notch here for easy of reading. It's hard to get that just right. I guess I'll have to do. So let's go ahead and look at our data. We're going to use our pandas. And we're going to go ahead and do our data frame. It's going to equal cancer data. Columns equals cancer. Feature equals feature names. So remember up here, we already loaded the names up of the features in there. What is going to come out of this? Let me just see if I can get to that. It's at the top of target names. That's just this list of names here in the setup. And we can go ahead and run this code, and it'll print the head. And you can see here we have the mean radius, the mean texture, mean perimeter. I don't know about you, this is a wonderful data set if you're playing with it, because like most of the data that comes in, half the time we don't even know what we're looking at. We're just handed a bunch of stuff as a data scientist going, what the heck is this? And so this is a good place to start because this has a number of different features in there and we have no idea what these features mean or where they come from. We want to just look at the data and figure that out. And now we actually are getting into the PCA side of it. As we've noticed before, it is difficult to visualize high-dimensional data. We can use PCA to find the first two principal components and visualize the data, this new two-dimensional space, with a single scatter plot. Before we do this, we need to go ahead and scale our data. Now, I haven't run this to see if you really have to scale the data on this, but as just a general runtime, I almost do that as the first step of any modeling, even if it's pre-modeling as we're doing here. In neural networks, that is so important. With PCA visualization, it's already going to scale it when we do the means and deviation inside the PCA. But just in case, it's always good to scale it. And then we're going to take our PCA with the scikit-learn uses very similar process to other pre-processing functions that come with scikit-learn. We instantiate a PCA object, find the principal components using the fit method, then apply the rotation and dimensionality reduction by calling transform. We can also specify how many components we want to keep when creating the PCA object. And so the code for this, oops, getting a little bit ahead. Let me go ahead and run this code. So the code for this is from sklearn decomposition import PCA. PCA equals PCA, in components equals 2. And that's really important to note that, because we're only going to want to look at 2 components. I would never go over 4 components, especially if you're going to demo this with somebody else. If you're showing this to the shareholders, the whole idea is to reduce it to something people can see. And then the PCA fit, we're going to is going to take the scaled data that we generated up here, and then you can see we've created our PCA model with in components equals 2. Now, whenever I use a new tool, I like to go in there and actually see what I'm using. So let's go to the Scikit webpage for the PCA. And you can see in here, here's our call statement. It describes what all the different setups you have on there. Probably the biggest one to look at would be, well, the biggest one is your components. How many components do you want, which you have to put in there pretty much. And then you also might look at the SVD solver. It's on auto right now, but you can override that and do different things with it. It does a pretty good job as it is. And if we go down, all the way down to, here we go, to our methods, if you notice we have fit, and we have fit transform. Nowhere in here is predict, because this is not used for prediction. It's used to look at the data. Again, we're in the describe setup. We're fitting the data. We're taking a look at it. We've already looked at our minimum maximum. We've already looked at what's in each quarter. We've done a full description of the data. This is part of describing the data. That's the biggest thing I take away when I come zooming in here. And of course, they have examples of it down here if you forget. And the biggest one, of course, is the number of components. And then, I mean, the rest you can play with. The actual solver, whether you're doing a full or randomized, there's different things. It does pretty good on the auto. And now we can transform this data to its first 2 principal components. And so we have our XPCA. We're going to set that equal to PCA transform scaled data. So there we go. There's our first transformation. And let's just go ahead and print the scaled data shape and the XPCA data shape. And the reason we want to do this is just to show us what's going on here. We've taken 30 features. I think I said 36 or something like that, but it's 30. And we've compressed it down to 2 features. And we decided we wanted 2 features, and that's where this comes from. We still have 569 data sets. I mean data rows, not data sets. We still have 569 rows of data, but instead of computing 30 features, we're now only doing our model on 2 features. So let's go ahead and plot these and take a look and see what's going on. And we're just going to use our PLT figure. We're going to set the figure size on here. Here's our scatter plot, XPCA, X underscore PCA of 1. These are our 2 different perceptions we're using. And then you'll see right here, C for color, cancer equals target. And so remember we have 0, we have 1. And if I remember correctly, 0 was malignant, 1 was benign. So everything in the 0 column is going to be one color, and the other color is going to be 1. And then we're going to use the plasma map, just kind of telling you what color it is. Add some labels, first principal component, second principal component. And we'll go ahead and run this. And you can see here, instead of having a chart, one of those heat maps with 30 different columns in it, we can look at this and say, hey, this one actually did a pretty good job of separating the data. And a couple things when I'm looking at this that I notice is, first, we have a very clear area where it's clumped together, where it's going to be benign. And we have a huge area, it's still clumped together, more spread out, where it's going to be malignant. Or I think I had that backwards. And then in the middle, because we're dealing with something, in this particular case, cancer, we would try to separate, I would be exploring how to separate this middle group out. In other words, there's an area where everything overlaps, and we're not going to have a clear result on it. Just because those are the people you want to go in there and have extra tests or treat it differently versus going in and saying just cutting into the cancer so that the body absorbs it and it dissipates versus actively going in there, removing it, testing it, going through chemo and all the different things. That's a big difference, you know, as far as what's going to happen here. And that middle line where they overlap is going to be huge. That's domain specific. Going back to the data, we can see here clearly by using these two components we can easily separate these two classes. So the next step is, what does that mean? Interpreting the components. Unfortunately, with this great power of dimensionality reduction comes a cost of not being able to easily understand what these components represent. I don't know what principal component 1 represents or second principal. The components correspond to combinations of original features. The components themselves are stored as an attribute of the filtered PCA object. And so when we look at that, we can go ahead and look at the PCA components. This is in our model we built. We've trained it. We can run that, and you can see here's the actual components. It's the two components each have their own array. And within the array, you can see what the scores they're using. And these actually give weight to what features are doing what. So in this NumPy matrix array, each row represents a principal component and each column relates back to the original features. What's really neat about this is we can now go in reverse and drop this onto a heat map and start seeing what this means. And so let me go ahead and just put this down. Oops, I already got it down here. We'll go ahead and put this in here. We're going to use our dfcomp data frame, and we do our PCA components. And I want you to notice how easy this is. We're going to set our columns equal to cancer feature names. That just makes it really easy. And we're dumping it into a data frame. What's neat about a data frame is when we get to Seaborn, it will pull that data frame apart and set it up for us the way we want. And so we're just going to do the Seaborn heat map of our data frame composition, and we'll use the plasma coloring. And it creates a nice little color graph here. You can see we have the mean radius and all the different features along the bottom. On the right, we have a scale, so we can see we have the dark colors all the way to the really light colors, which are what's really shining there. This is like the primary stuff we want to look at. So this heat map and the color bar basically represent the correlation between the various features and the principal component itself. So, you know, very powerful map to look at, and then you can go in here, and we might notice that the mean radius, look how on the bottom of the map it is on some of this. So you have some interesting correlations here that change the variations on that and what means what. This is more when you get to PostScribe, you can also use this to try to guess as what these things mean and what you want to change to get a better result.
Feature selection in machine learning. Today we're going to look at what's in it for you, the need for feature selection, what is feature selection methods, feature selection statistics. So the need for feature selection. To train a model, we collect huge quantities of data to help the machine learn better. Consider a table which contains information on old cars. The model decides which cars must be crushed for spare parts. And when we talk about huge quantities of data, they save everything from people's favorite cat pictures to, and you can imagine there's so much data out there. Even in a company, they'll save all these little pieces of information about people and companies and corporations. You need some way to sort through, because if you try to run your models on all of it, you'll end up with these very clunky models, and they might have issues, which we'll talk about later. But in this case, we're talking about cars and crushing. But not all this data will be useful to us. Some classes or part of the data may not contribute much to our model and can be dropped. And you can see right here we have who was the owner of the car. In our data, a car will not be crushed based on its previous owner. So that's kind of a clear cut. You can see that. Why would I care who owned the car before? Once it's in the junkyard and we're crushing the cars, we're not going to really care about that. So here we have dropped the owner column as it does not contribute to the model. Having too much unnecessary data can cause the model to be slow. The model may also learn from this irrelevant data and be inaccurate. So feature selection is a process of reducing the input variable to your model by using only relevant data and getting rid of the noise in the data. Consider the database given below. A library wants to donate some old books to make place in their shelves for new books. We want to train a model to automate this task. In this case, the color of the book does not matter, and keeping it can cause the model to learn to donate books based on color. We can remove this as a feature. Using feature selection, we can optimize our model in several ways. And so the number one is to prevent learning from noise and overfitting. That's actually the huge one because we don't want it to give us a wrong prediction. And that means also improved accuracy. So instead of giving us a wrong prediction, we also want it to be as close to the right answer as we can get. And we want to reduce the training time. It's an exponential growth in some of these models, so that each feature you add in increases that much more training time. We talk about feature selection methods. We put together a nice little flow chart that shows the various methods used for feature selection. And you have your basic feature selection, and then there is supervised and unsupervised. Under supervised, there's intrinsic, wrapper method, filter method. So when we talk about unsupervised feature selection, refers to the method which does not need the output label class for feature selection. And that was, you can see here under unsupervised, we don't have, that's really a growing market right now, unsupervised learning. And so feature selection is the same thing. Supervised feature selection refers to the method which uses the output label class for the feature selection. And if you remember, we looked at we have intrinsic, wrapper, and filter method. So we're going to start with the filter method on this. Now remember, we know what the output is. So we're going to be looking at that output to see how well it's doing versus the features. In this method, features are dropped based on their relation to the output, or how they are correlating to the output. And you can see here we have a set of features, selecting best feature, learning algorithm, and then performance. And so we want to find out which feature correlates to the performance on the output. Consider the example of book classifier. Here we drop the color column based on simple deduction. And that kind of sums it up in a nutshell, is we want to filter out things that clearly do not go with what we're looking for. We look at the wrapper method. In the wrapper method, we split our data into subsets and train a model using this. Based on the output of the model, we add and subtract features and train the model again. And you can see here in the wrapper method where we have a set of features, we generate a subset, we run it through the algorithm, and we see how each one of those subset of features performs. Consider the book data set. By using the wrapper method, we would use a subset of different features to train the machine and adjust the subset according to the output. And so you can see here, let's say we take name and number of times read, and we run just those, and we look at the output. And if we looked at them with all 4 inputs and look at the output, we'd see quite a different variation in there, and we might say, you know what, condition of the book and color really doesn't affect what we're looking for. And you can see here we've run it on condition of the book and color. Depending on the output of the model, we will choose our final set of features. These features will give us the best result for our model. And it might come up that the name, number of times read is probably pretty important. The intrinsic method, this method combines the qualities of both filter and wrapper method to create the best subset. The model will train and check the accuracy of different subsets and select the best among them. We kind of looked at a little overview of some of the stuff. Some of the common feature selection algorithms based on which method they belong to are given below. And you'll see it's primarily under supervised. There's not, like I said, a lot of unsupervised methods, and the ones that are usually use these methods and finds a way to create a supervised connection between the data. And we talk about supervised methods. We have our filter method, which we talked about, and it uses like the Pearson's coefficient, chi-squared, ANOVA coefficient. Those are all under the filter method. And in the wrapper method, recursive feature elimination. So remember, we're choosing a subset, and we want to go through there and look at each one. So you're just doing a lot of loops or recursive calculations to see which one works best and which ones don't have an impact on the output. And there's a lot of genetic algorithms to go with this too on the wrapper method and how they evaluate it. And with the intrinsic method, there's the two main ones we're looking at is the lasso regularization. The lasso algorithms are basically your standard regression model. So it's finding out how these different methods fit together and which ones have the best add together to have the least amount of error. The other one used in the intrinsic method is the decision tree. It says, hey, if this one is this one produces this result, this one produces this result, yes, no, which way do we go? Based on the input and the output variables, we can choose our feature selection model. So you have your numeric input coming in, you have your numeric output. If you use the Pearson's correlation coefficient or Spearman's rank coefficient, you can then select what features you're going to feed into that specific model. And you maybe have a numerical input and a categorical input, so we're going to be looking more at ANOVA correlation coefficient or Kendall's rank coefficient. And if you have a categorical input and a numerical output, we might be looking at ANOVA correlation coefficient and Kendall's rank coefficient. So based on the input and the output variables, we can choose our feature selection model. And you can see we have categorical to categorical. We might be looking at the chi-squared test, contingency tables, and mutual information. Let's go ahead and take a look and see in the Python code what we're talking about here. And I'm going to go ahead and use for my IDE the Jupyter notebook, and I always launch it out of Anaconda on here. And we'll go ahead and go up here and create a new Python 3 module. And we'll call it feature select. Since we're in Python, we're going to be working mainly with your NumPy, your pandas, your matplotlib library. So we have our number array, our data frame setup, which goes with the number array, the NumPy, the pandas data frame. And then we want to go ahead and graph everything. So we're going to import these three modules. And then we put together some data. We're going to read this in. It's Kobe Bryant. I guess he's a basketball player. Our guys in the back, we have a number of them. Guys, it's both, we have a lot of men and women, so it's probably a misnomer. Our team in the back, they have some of them have a liking for basketball, and they know who Kobe Bryant is, and they want to learn a little bit more about Kobe Bryant and what's going in for whatever's going on with his game in basketball. So we're going to take a look at him. And once we import the data, we can see what columns are available, original features count, so we can see how many features there are, the length of it, and we'll actually have a list of them, and then print just the data head, the top 5 rows. And so when we do this, we can see from the CSV file, we have 25 original features. Our original features are your action type, combined shot type, game event ID, and so forth. There's a lot of features in here that they recorded on all of his shots. This is what we talk about, like a massive amount of data. I mean, people are sitting there and they record all this stuff and they import this stuff for different reasons. But depending on what we want to look at, do we really want all those features? Maybe the question we're going to ask is, what's the chance of him making any one specific shot? Right from the beginning, we can look at some of these things and say team name. Team name probably, I don't know, maybe it does matter because the other team might be really good at defense. Game date, maybe we don't really want to look at the game date. Team ID, definitely not of importance in any of this. So when we look at this, we have 25 features, and some of these features just really don't matter to us. We also have location X, location Y, latitude and longitude. I'm guessing that's the same data. We've actually imported the very similar data. Maybe they're slightly zoned differently. But as far as our program, we don't want to repeat data. Some of the models, when you repeat data into them, and this is true for most models, create a huge bias. They weigh that data over other data. So just at a glance, these are the things we're looking at. We want to find out, well, how do we get these features down and get rid of this bias and all these extraneous features that we don't really want to spend time running our models on and programming on. And as I pointed out, there's a location X, a location Y, latitude and longitude. Let's just take a look at that and see what we're looking at here. We'll go ahead and create a plot of these. And we'll just plot, we'll do a scatter plot of location X and location Y, and then we'll do a scatter plot of data lon, data lat, which is probably longitude and latitude. And the scatter plot, let's go ahead and actually put a little title here, location and scatter on there. And we'll just go ahead and plot these. And when you look at this coming in, these two graphs are pretty identical except they're flipped. And so when we look at the location from which they're shooting from, they're probably the same. And at this point we can say, okay, we can get rid of one of these sets of data. So we don't need both X and Y and latitude and longitude because it's the same data coming in. And as we look at this particular data, the latitude, longitude, we might also ask, does it really make a difference which side of the court you're on, whether you're on the left side or the right side? And so we might go ahead and explore, instead of looking at this as XY, we might look at it as a distance and an angle. And we can easily compute that. And you can see we can create our data distance equals the location X plus the location Y squared, standard Euclidean geometry or triangular geometry. Hypotenuse squared equals each side squared. And then once we've done that, we can also compute the angle. So the data angle is based on the arc tangent and so forth on here. So this is all this is we're just going to compute the angle here and then set that up, pi over 2 to get our angle. And we'll go ahead and run that. And you'll see some errors come up, and that's because when we took slices over here, we took a slice of a slice. There's ways to fix that, but it's really not important for this example. So if you do see that, you want to start looking up here for, instead of data location X of not location X0, this would be like, I believe the term is .iLocation. If this was, yeah, this is in pandas. So there's different things in there, but for this, it doesn't really matter. These are just warnings. That's all they are. And then let's combine our remaining minutes and seconds column into one. There's another one. So if you remember up here, we're trying to get rid of these columns. Do we really need, let me see if I can find it on here. There we go. There's our minutes remaining. And then they had, what was it? It was minutes remaining and seconds column. So there's also a seconds column on here. Let me see if I can find that one. This is where it really gets kind of crazy because here's our seconds remaining. So you can see that, and here's our minutes remaining. This gets crazy when you're looking at hundreds of these features. And you can see that if I'm going to, say, write a model that's going to predict a lot of this, and I want it to run, in this case, it's a basketball and how good his shots are as the data comes in. Let's say I want to have it run on your phone. If I'm running it across hundreds of features, it's going to just hang up on your phone, where if I can get it down to just a handful, we'll actually be able to come in here and run it on a smaller device and not use up as much memory or processing power. So we'll go ahead and take data remaining time here, and data minutes remaining times 60 plus data seconds remaining. So we're just going to combine those, and we'll go ahead and reprint our data so we can see what we got. Coming across, we have our action type combined, and this is, we do this a lot. We want to take a look at, oops, I got it so zoomed in. Let me see if I can zoom out just a little bit. There we go. Boom. Alright, so we come up here, you can see that we now have our distance, our angle, remaining time, which is now just a number that computes both the minutes and seconds together. And we still have, we've been adding columns. I thought you said we're supposed to subtract columns, right? We're going to delete the obsolete columns when we get to them. So we're just filtering out, and this is the filter method. We're just filtering through the things that we really don't need. And next, let's go ahead and explore team ID and team name. Now, let me just go ahead and run that. And if you look at this, we have Los Angeles Lakers, and then they have the team ID here, and they're unique. That's not really anything that's going to come up because that's this particular athlete's works for that team. So it's the same on every line. So there's another thing we can filter out on there. Team ID and team name is just useless. The whole column contains only one value each, and it's pretty much useless. Let's go ahead and take a look at matchup and opponent. That's an interesting one. And we see here that we have the LAL versus POR, and the opponent is POR and IND. Again, here's a lot of duplicate information. So this basically contains the same information on here. Again, we're filtering all this stuff out, and this is because we're only looking at one athlete. And this might change if you're looking at multiple athletes, that kind of thing. Now, these are easy to see, but we might have something that looks more like this. We might have something where we're looking at the distance, which we computed, and the shot distance. Are they the same thing? And what we can do is we can plot that and plot them against each other on here, and we see it just draws a nice straight line. And so, again, we're looking at the same information. So again, we're repeating stuff, and we really don't want to be running our model on repeat information on here. So again, it contains the same information. So now let's look at the shot zone area, shot zone basic, shot zone range. So now we're looking at the zones, and what does that mean? And we'll go ahead and do this also in a scatter plot. In this case, we're going to just create 3 of these side by side. So we're going to create our plot figure side 20 by 10. And then we're going to define our scatter plot by category feature. And we're going to do each one, set up on here, give it a slightly different color. And so our shot zone area is going to be plot, subplot 131, scatter 131 is how that's read, by the way. Meaning that it's number 1, we have 3 across, and this is the first one down, so 1, 1, 1. Our scatter plot by category is going to be the shot zone area. We're going to plot that. And then we're going to do the shot zone basic and then the shot zone range, and each just push them through our definition. So each of those areas go through, and you'll see 131, 132, 133. Again, it's a 1 by 3 setup, and then it's just a place on each one. And so when we look at this, we can see that these shots, they map out the same. So it's very, again, redundant information. That should be intuitive. When we're looking at this in these color graphs, it kind of helps, and you start looking at something it's very intuitive like this is, and you start to realize that some of this stuff you'll be looking for in data you might not understand. And you'll see these circular patterns where they match, or they mostly match, and you start to realize when you're looking at these that they're repetitive data, and then you want to explore them more closely depending on what domain you're working in. So we look at these, and we look at them, and they look just like the regions of the court, but we already have stored this information in angle and distance columns. So we've seen this image before. We go back up here, and here's the similar image. And repeating that image is down here, and so let's go ahead and drop some of this stuff. So now let's drop all the useless columns. And we can drop the shot ID, team name, shot zone area, shot zone range, shot zone basic, the matchup, the longitude and latitude, because we're putting that into distance, seconds remaining, minutes remaining, because we combine that into one column, shot distance, because we have just distance on there, location X, location Y, the game event ID, game ID, all of this stuff is just being dropped on here. And we'll just go ahead and loop through our drops. And this is a nice way of doing this, because as you're playing with this, this kind of data, putting your list into one setup helps, because then you're just running it through an iteration, and you can come back and change it. You might be playing with different models and do this with models. You might be looking at all kinds of different things that you can drop and add in as you test these out. And again, we're working in the filter method. So this is a lot of human interaction with the data. And it takes a lot of critical thinking to look at this stuff and say what matches and what doesn't. And so when we look at the remaining features, let me go ahead and just run this. The original to the new count, we had 25 features. Now we have 11 features. You can see that right there. We just circle that. There's our 25, and there's old, new. Now we're down to 11. So we've cut it down to less than half. And you can just see the actual different information on here and the remaining time. At this point, we filtered it through, and then we'd move into the next process, which would be to run our model on this, and maybe we would drop some of the features and see if it runs better or worse and what happens. That's kind of would be the next step on there versus this is the filter setup, and that would be one of the other setups depending on which algorithm you use. So that wraps up our demo on filter, the feature selection, and going through and seeing how these different features are being repeated in this particular in a basketball setup. We're going to cover reinforcement learning today. And what's in it for you? We'll start with why reinforcement learning. We'll look at what is reinforcement learning. We'll see what the different kinds of learning strategies are that are being used today in computer models under supervised versus unsupervised versus reinforcement. We'll cover important terms specific to reinforcement learning. We'll talk about Markov's decision process, and we'll take a look at a reinforcement learning example. Well, we'll teach a tic-tac-toe how to play. Why reinforcement learning? Training a machine learning model requires a lot of data, which might not always be available to us. Further, the data provided might not be reliable. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. You can see here we have the robot learning to walk. Very complicated setup when you're learning how to walk, and you'll start asking questions like, if I'm taking one step forward and left, well, what happens if I pick up a 50-pound object? How does that change how a robot would walk? These things are very difficult to program because there's no actual information on it until it's actually tried out. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. And we'll see here it learned how to walk. This is going to slow the growth that technology is capable of. Machines need to learn to perform actions by themselves and not just learn off humans. And you see the objective climb a mountain. A real interesting point here is that as human beings we can go into a very unknown environment and we can adjust for it and kind of explore and play with it. Most of the models, the non-reinforcement models in computer machine learning, aren't able to do that very well. There's a couple of them that can be used or integrated. To see how it goes is what we're talking about with reinforcement learning. So what is reinforcement learning? Reinforcement learning is a sub-branch of machine learning that trains a model to return an optimum solution for a problem by taking a sequence of decisions by itself. Consider a robot learning to go from one place to another. The robot is given a scenario and must arrive at a solution by itself. The robot can take different paths to reach the destination. It will know the best path by the time taken on each path. It might even come up with a unique solution all by itself. And that's really important as we're looking for unique solutions. We want the best solution, but you can't find it unless you try it. So when we're looking at our different systems, our different model, we have supervised versus unsupervised versus reinforcement learning. And with the supervised learning, that is probably the most controlled environment. We have a lot of different supervised learning models, whether it's linear regression, neural networks, there's all kinds of things in between, decision trees. The data provided is labeled data with output values specified. And this is important because when we talk about supervised learning, you already know the answer for all this information. You already know the picture has a motorcycle in it, so you're supervised learning. You already know that the outcome for tomorrow, for going back a week, you're looking at stock, you can already have like the graph of what the next day looks like, so you have an answer for it. And you have labeled data which is used, you have an external supervision, and solves problems by mapping labeled input to known output. So very controlled. Unsupervised learning, and unsupervised learning is really interesting because it's now taking part in many other models. They start with, you can actually insert an unsupervised learning model in almost either supervised or reinforcement learning as part of the system, which is really cool. Data provided is unlabeled data. The outputs are not specified. Machine makes its own predictions. Used to solve association with clustering problems. Unlabeled data is used. No supervision. Solves problems by understanding patterns and discovering output. So you can look at this and you can think some of these things go with each other. They belong together. So it's looking for what connects in different ways. And there's a lot of different algorithms that look at this. When you start getting into those, there's some really cool images that come up of what unsupervised learning is. How it can pick out, say, the area of a donut One model will see the area of the donut, and the other one will divide it into 3 sections based on its location versus what's next to it. So there's a lot of stuff that goes in with unsupervised learning. And then we're looking at reinforcement learning, probably the biggest industry in today's market in machine learning, or growing market. It's very infant stage as far as how it works and what it's going to be capable of. The machine learns from its environment using rewards and errors, used to solve reward-based problems. No predefined data is used, no supervision, follows trial and error problem solving approach. So again, we have a random, at first you start with a random, I try this, it works and this is my reward, doesn't work very well maybe, or maybe it doesn't even get you where you're trying to get it to do, and you get your reward back, and then it looks at that and says, well, let's try something else, and it starts to play with these different things, finding the best route. So let's take a look at important terms in today's reinforcement model. And this has become pretty standardized over the last few years, so these are really good to know. We have the agent. Agent is the model that is being trained via reinforcement learning. So this is your actual entity that has, however you're doing it, whether you're using a neural network or a Q table or whatever, combination thereof. This is the actual agent that you're using. This is the model. And you have your environment. The training situation that the model must optimize to is called its environment. And you can see here, I guess we have a robot who's trying to get a chest full of gems or whatever, and that's the output. And then you have your action. This is all possible steps that can be taken by the model, and it picks one action. And you can see here that it's picked 3 different routes to get to the chest of diamonds and gems. We have a state, the current position condition returned by the model. And you could look at this if you're playing like a video game. This is the screen you're looking at. So when you go back here, the environment is a whole game board. So if you're playing one of those Mobius games, you might have the whole game board going on, but then you have your current position. Where are you on that game board? What's around that? What's around you? If you were talking about a robot, the environment might be moving around the yard, where it is in the yard and what it can see, what input it has in that location. That would be the current position condition returned by the model. And then the reward. To help the model move in the right direction, it is rewarded. Points are given to it to appraise some kind of action. So, yeah, you did good, or if didn't do as good, trying to maximize the reward and have the best reward possible. And then policy. Policy determines how an agent will behave at any time. It acts as a mapping between action and present state. This is part of the model. What is your action that you're going to take? What's the policy you're using to have an output from your agent? One of the reasons they separate policy as its own entity is that you usually have a prediction of different options, and then the policy, well, how am I going to pick the best? Based on those predictions, I'm going to guess at different options. And we'll actually weigh those options in and find the best option we think will work. So it's a little tricky, but the policy thing is actually pretty cool how it works. Let's go ahead and take a look at a reinforcement learning example. And just in looking at this, we're going to take a look, consider what a dog that we want to train. So the dog would be like the agent. So you have your puppy or whatever. And then your environment is going to be the whole house or whatever it is where you're training them. And then you have an action. We want to teach the dog to fetch. So action equals fetching, and then we have a little biscuit, so we can get the dog to perform various actions by offering incentives such as a dog biscuit as a reward. The dog will follow a policy to maximize this reward, and hence will follow every command and might even learn new actions like begging by itself. So you have, so we start off with fetching. It goes, oh, I get a biscuit for that. It tries something else, and you get a handshake or begging or something like that. And it goes, oh, this is also reward based. And so it kind of explores things to find out what will bring it as biscuit. And that's very much like how a reinforced model goes. Is it looks for different rewards. How do I find? Can I try different things and find a reward that works? The dog also will want to run around and play and explore its environment. This quality of model is called exploration. So there's a little randomness going on in exploration. And it explores new parts of the house. Climbing on the sofa doesn't get a reward. fact, it usually gets kicked off the sofa. So let's talk a little bit about Markov's decision process. Markov's decision process is a reinforcement learning policy used to map a current state to an action where the agent continuously interacts with the environment to produce new solutions and receive rewards. And you'll see here's all of our different vocabulary we just went over. We have a reward, our state, our agent, our environment, and our action. And so even though the environment kind of contains everything, that you really, when you're actually writing the program, your environment's going to put out a reward and state that goes into the agent. The agent then looks at this state, or it looks at the reward usually first, and it says, okay, I got rewarded for whatever I just did, or I didn't get rewarded. And then it looks at the state, and then it comes back, and if you remember from policy, the policy comes in, and then we have a reward. The policy is that part that's connected at the bottom. And so it looks at that policy and it says, hey, what's a good action that will probably be similar to what I did, or sometimes they're completely random, but what's a good action that's going to bring me a different reward? So taking the time to just understand these different pieces as they go is pretty important in most of the models today. And so a lot of them actually have templates based on this that you can pull in and start using. Pretty straightforward as far as once you start seeing how it works, you can see your environment says, hey, this is the agent did this. If you're a character in a game, this happened, and it shoots out a reward and a state. The agent looks at the reward, looks at the new state, and then takes a little guess and says, I'm going to try this action. And then that action goes back into the environment. It affects the environment. The environment then changes depending on what the action was, and then it has a new state and a new reward that goes back to the agent. So in the diagram shown, we need to find the shortest path between node A and D. Each path has a reward associated with it, and the path with a maximum reward is what we want to choose. The nodes A, B, C, D denote the nodes to travel from node A to B is an action. Reward is the cost of each path, and policy is each path taken. And you can see here A can go to B, or A can go to C right off the bat, or it can go right to D. And if you explored all three of these, you would find that A going to D was a 0 reward, A going to C and D would generate a different reward, or you could go A, C, B, D. There's a lot of options here. And so when we start looking at this diagram, you start to realize that even though today's reinforced learning models do really good at finding an answer, they end up trying almost all the different directions you see. And so they take up a lot of work or a lot of processing time for reinforcement learning. They're right now in their infant stage, and they're really good at solving simple problems. And we'll take a look at one of those in just a minute in a tic-tac-toe game. But you can see here, once it's gone through these and it's explored, it's going to find the ACD is the best reward. It gets a full 30 points for it. So let's go ahead and take a look at a reinforcement learning demo. In this demo, we're going to use reinforcement learning to make a tic-tac-toe game. You will be playing this game against the machine learning model. And we'll go ahead, we're doing it in Python. So let's go ahead and go through, not always, I actually have a lot of Python tools. Let's go through Anaconda, which will open up a Jupyter notebook. Seems like a lot of steps, but it's worth it to keep all my stuff separate, and it also has a nice display when you're in the Jupyter notebook for doing Python. So here's our Anaconda navigator. I open up the notebook, which is going to take me to a web page, and I've gone in here and created a new Python folder. In this case, I've already done it and enabled it to change the name to tic-tac-toe. And then for this example, we're going to go ahead and import a couple things. We're going to import numpy as np. We'll go ahead and import pickle. Numpy, of course, is our number array, and then pickle is just a nice way sometimes for storing different information, different states that we're going to go through on here. And so we're going to create a class called state. We're going to start with that. And there's a lot of lines of code to this class that we're going to put in here. Don't let that scare you too much. There's not as much here It looks like there's going to be a lie here, but there really is just a lot of setup going on in our class state. And so we have up here, we're going to initialize it. We have our board. It's a tic-tac-toe board, so we're only dealing with 9 spots on the board. We have player 1, player 2 is end. We're going to create a board hash. We'll look at that in just a minute. We're just going to store some information in there. Symbol of player equals 1. So there's a few things going on as far as the initialization. Then something simple, we're just going to get the hash of the board. We're going to get the information from the board on there, which is columns and rows. We want to know when a winner occurs. So if you get 3 in a row, that's what this whole section here is for. Let me go ahead and scroll up a little bit. And you can get a copy of this code if you send a note over to Simplilearn. We'll send you over this particular file, and you can play with it yourself and see how it's put together. I don't want to spend a huge amount of time on this because this is just some real general Python coding. But you can see here we're just going through all the rows, and you add them together, and if it equals 3 in a row, the same thing with columns. Diagonal, so you got to check the diagonal. That's what all this stuff does here, is it just goes through the different areas. Actually, let me go ahead and put, there we go. And then it comes down here and we do our sum, and it says true, -3 just says did somebody win, or is it a tie? So you got to add up all the numbers on there anyway, just in case they're all filled up. And next we also need to know available positions. These are ones that no one's ever used before. This way when you try something, or the computer tries something, it's not going to give it an illegal move. That's what the available positions is doing. Then we want to update our state. And so you have your position going in. We're just sending in the position that you just chose. And you'll see there's a little user interface we put in there. We can pick the row and column in there. And again, I mean, this is a lot of code. So really it's kind of a thing you'd want to go through and play with a little bit and just read through it, get a copy of it. A great way to understand how this works. And here is a given reward. So we're going to give a reward, result equals self winner. This is one of the hearts of what's going on here, is we have a result self.winner. So if there's a winner, then we have a result. If the result equals 1, here's our feedback. If it doesn't equal 1, then it gets a 0. So it only gets a reward in this particular case if it wins. And that's important to know because different systems of reinforced learning do rewarding a lot differently depending on what you're trying to do. This is a very simple example with a 3x3 board. Imagine if you're playing a video game, certainly you only have so many actions, but your environment is huge. You have a lot going on in the environment. And suddenly a reward system like this is going to be just, is going to have to change a little bit. It's going to have different rewards and different setup. And there's all kinds of advanced ways to do that as far as weighing, you add weights to it. And so they can add the weights up depending on where the reward comes in. So it might be that you actually get a reward. In this case, you get the reward at the end of the game. And I'm spending just a little bit of time on this because this is an important thing to note. But there's different ways to add up those rewards. It might have, like if you take a certain path, the first reward is going to be weighed a little bit less than the last reward because the last reward is actually winning the game or scoring or whatever it is. So this reward system gets really complicated in some of the more advanced setups. In this case, though, you can see right here that they give a 0.1 and a 0.5 reward just for picking the right value and something that's actually valid instead of picking an invalid value. So rewards, again, that's like key. It's huge. How do you feed the rewards back in? Then we have a board reset. That's pretty straightforward. It just goes back and resets the board to the beginning because it's going to try out all these different things while it's learning. It's going to do it by trial and error, so you have to keep resetting it. And then, of course, there's the play. We want to go ahead and play rounds equals 100. Depends on what you want to do on here. You can set this different. You can obviously set that to higher level. But this is just going to go through, and you'll see in here that we have player 1 and player 2. This is the computer playing itself. One of the more powerful ways to learn to play a game, or even learn something that isn't a game, is to have two of these models that are basically trying to beat each other. And so they keep explore new things. This one works for this one, so this one tries new things. It beats this. We've seen this in chess. I think was a big one where they had the two players in chess with reinforcement learning. It was one of the ways they trained one of the top computer chess playing algorithms. So this is just what this is. It's going to choose an action, it's going to try something, and the more it tries stuff, the more we're going to record the hash. We actually have a board hash where you self get the hash set up on here where it stores all the information. And then once you get to a win, one of them wins, it gets the reward. Then we go back and reset and try again. And then kind of the fun part we actually get down here is we're going to play with a human. So we'll get a chance to come in here and see what that looks like when you put your own information in. And then it just comes in here and does the same thing it did above. It gives it a reward for its things, or sees if it wins or ties, looks at available positions, all that kind of fun stuff. And then finally we want to show the board. So it's going to print the board out each time. Really, as an integration, is not that exciting. What's exciting in here is, one, looking at this reward system. Whoops, play one more up. The reward system is really the heart of this. How do you reward the different setup? And the other one is when it's playing, it's got to take an action. And so what it chooses for an action is also the heart of reinforcement learning. How do we choose that action? And those are really key to right now where reinforcement learning is in today's technology, is figuring this out. How do we reward it, and how do we guess the next best action? So we have our environment, and you can see the environment is or the state, which is kind of like what's going on. We're going to return the state depending on what happens. And we want to go ahead and create our agent, in this case our player. So each one is, let me go and grab that. And so we look at a class player. This is where a lot of the magic is really going on, is how is this player figuring out how to maneuver around the board, and then the board of course returns a state that it can look at and a reward. So we want to take a look at this. We have name, self-state. This is class player. And when we say class player, we're not talking about a human player. We're talking about just the computer players. And this is kind of interesting. So remember I told you, depending on what you're doing, there's going to be a decay gamma, explore rate. These are what I'm talking about, is how do we train it? As you try different moves, it gets to the end. The first move is important, but it's not as important as the last one. And so you could say that the last one has the heaviest weight, and then as you get there, the first one, let's see, the first move gives you a 5 reward, the second gives you a 2 reward, and the third one gives you a 10 reward, because that's the final ending. You got it. The 10's going to count more than the first step. And here's our, we're going to get the board information coming in, and then choose an action. This was the second part that I was talking about that was so important. So once you have your training going on, we have to do a little randomness, and you can see right here is our NP random uniform. So it's picking out a random number. Take a random action. This is going to just pick which row and which column it is. And so choosing the action, this one you can see we're just doing random states, choice, length of positions, action position, and then it skips in there and takes a look at the board for P in positions. And it's actually storing the different boards each time you go through, so it has a record of what it did, so it can properly weigh the values. And this simply just appends a hash state. What's the last state? Append it to the to our states on here. Here's our feedback reward. So the reward comes in, and it's going to take a look at this and say, is it none? What is the reward? And here is that formula. Remember I was telling you about up here that was important because it has decay gamma times the reward. This is where, as it goes through each step, and this is really important. This is kind of the heart of this. of what I was talking about earlier. You have step 1, and this might have a reward of 2. You have step 2, I probably should have done ABC. This has a step 3, step 4, and so on until you get to step N. And this might have a reward of 10. So reward of 10, we're going to add that, but we're not adding, let's say this one right here, let's say this reward here right before 10 was, let's say it's also 10. That just makes the math easy. So we had 10 and 10. We had 10, this is 10 and 10n, whatever it is, but it's time it's 0.9. So instead of putting a full 10 here, we only do 9. That's 0.9 times 10. And so this formula, as far as the decay times the reward minus the cell state value, it basically adds in, it says here's 1, or here's 2, I'm sorry, I should have done this ABC, it would have been easier. So the first move goes in here and it puts 2 in here. Then we have ourselves set up on here. You can see how this gets pretty complicated in the math, but this is really the key, is how do we train our states? And we want the final state, the win, to get the most points. If you win, you get most points. And the first step gets the least amount of points. So you're really training this almost in reverse. You're training it from the last place where you have, like it says, okay, this is now where I need to sum up my rewards, and I want to sum them up going in reverse, and I want to find the answer in reverse. Kind of an interesting play on the mind when you're trying to figure this stuff out. And of course we want to go ahead and reset the board down here and save the policy, load policy. These are the different things that are going in between the agent and the state to figure out what's going on. Let's go ahead and load that up. And then finally we want to go ahead and create a human player. And the human player is going to be a little different in that you choose an action, row and column. Here's your action. If action in positions, meaning positions that are available, you return the action. If not, it just keeps asking you until you get an action that actually works. And then we're going to go ahead and append to the hash state, which we don't need to worry about because it returns the action up here, and feed forward. Again, this is because it's a human. At the end of the game, backpropagate and update state values. This part isn't being done because it's not programming the model. The model is getting its own rewards. So we've gone ahead and loaded this in here. So here's all our pieces, and the first thing we want to do is set up P1 player 1, P2 player 2, and then we're going to send our players to our state. So now it has P1, P2, and it's going to play, 50,000 rounds. Now we can probably do a lot less than this, and it's not going to get the full results. In fact, you know what? Let's go ahead and just do 5, just to play with it, because I want to show you something here. Oops, somewhere in there I forgot to load something. There we go. I must have forgot to run this. Run. Oops, forgot a reference there for the board, rows and columns, 3 by 3. There's actually in the state, it references that. We can just tack it on the end. It was supposed to be at the beginning. So now I've only set this up with, let's see, where are we going here? I've only set this up to train 5 times. And the reason I did that is we're going to come in and actually play it, and then I'm going to change that, and we can see how it differs on there. There we go. And it didn't even make it through a run, and we're going to go ahead and save the policy. So now we have our player 1 and our player 2 policy. The way we set it up, it has 2 separate policies loaded up in there. And then we're going to come in here and we're going to do player 1 is going to be the computer, experience rate 0, load policy 1, human player human, and we're going to go ahead and play this. Now remember, I only went through it just one round of training, in fact minimal training. And so it puts an X there, and I'm going to go ahead and do row 0, column 1. And you can see this is very basic on here. And so I put in my 0, and then I'm going to go 0, block it, 0, 0. And you can see right here, it let me win. Just like that, I was able to win. 0, 2, and woo, human wins. So I only trained it 5 times. We're going to run this again, and this time, instead of 5, let's do 5,000 or 50,000. I think that's what the guys in the back had. And this takes a while to train it. This is where reinforcement learning really falls apart. Look how simple this game is. We're talking about a 3x3 set of columns. And so for me to train it on this, I could do a Q table which would go much quicker. You could build a quick Q table with almost all the different options on there, and you would probably get the same result much quicker. We're just using this as an example. So when we look at reinforcement learning, you need to be very careful what you apply it to. It sounds like a good deal until you do like a large neural network, where you're doing, you set the neural network to a learning increment of 1, so every time it goes through it learns, and then you do your actions. So you pick from the learning setup, and you actually try actions on the learning setup until you get what you think is going to be the best action. So you actually feed what you think is right back through the neural network. There's a whole layer there, which is really fun to play with. And then it has an output. Well, think of all those processes. I mean, that is just a huge amount of work it's going to do. Let's go ahead and skip ahead here. Give it a moment. It's going to take a minute or two to go ahead and run. Now, to train it, we went ahead and let it run, and it took a while. This took, I got a pretty powerful processor, and it took about 5 minutes plus to run it. And we'll go ahead and run our player setup on here. Oops, it brought in the last whoops, it brought in the last round. So give me just a moment to redo the policy save. There we go. I forgot to save the policy back in there. And then go ahead and run our player again. So we've saved the policy, and then we want to go ahead and load the policy for P1 as a computer. And we can see the computer's gone in the bottom right corner. I'm going to go ahead and go 1, 1, which is the center. And it's gone right up the top, and if you have ever played tic-tac-toe, you know the computer has me. But we'll go ahead and play it out. Row 0, column 2. There it is, and then it's gone here, and so I'm going to go ahead and go row 0, 1, 2, no, 0, 1, there we go, and column 0. That's where I wanted. Oh, and it says, okay, your action, there we go, boom. So you can see here, we've got didn't catch the win on this, it said tie. Kind of funny that it didn't catch the win on there. But if we play this a bunch of times, you'll find that it's going to win more and more. The more we train it, the more the reinforcement happens. This lengthy training process is really the stopper on reinforcement learning. As this changes, reinforcement learning will be one of the more powerful packages evolving over the next decade or two. In fact, I would even go as far as to say it is the most important machine learning tool and artificial intelligence tool out there, as it learns not only a simple tic-tac-toe board, but we start learning environments. And the environment would be like in language. If you're translating a language or something from one language to the other, so much of it is lost if you don't know the context it's in, what's the environments it's in. And so being able to attach environment and context and all those things together is going to require reinforcement learning to do. So again, if you want to get a copy of the tic-tac-toe board, it's kind of fun to play with. Run it, you can test it out, you can do test it for different values. You can switch from P1 computer, where we loaded the policy 1, to load the policy 2 and just see how it varies. There's all kinds of things you can do on there.
Hello and welcome to this tutorial on deep learning. My name is Mohan, and in the next about 1.5 hours I will take you through what is deep learning and into TensorFlow environment to show you an example of deep learning. Now, there are several applications of deep learning, really very interesting and innovative applications, and one of them is identifying the geographic location based on a picture. And how does this work? The way it works is pretty much we train an artificial neural network with millions of images which are tagged, their geolocation is tagged, and then when we feed a new picture, it will be able to identify the geolocation of this new image. For example, you have all these images, especially with maybe some significant monuments or significant locations, and you train with millions of such images, and then when you feed another image, it need not be exactly one of those that you have trained. It can be completely different. That is the whole idea of training. It will be able to recognize, for example, that this is a picture from Paris because it is able to recognize the Eiffel Tower. So the way it works internally, if we have to look a little bit under the hood, is these images are nothing but this is digital information in the form of pixels. So each image could be a certain size. It can be 256 by 256 pixel kind of a resolution, and then each pixel is either having a certain grade of color, and all that is fed into the neural network, and it then gets trained in, and it's able to, based on these pixel information, it is able to get trained and able to recognize the features and extract the features, and thereby it is able to identify these images and the location of these images. And then when you feed a new image, it kind of, based on the training, it will be able to figure out where this image is from. So that's the way, a little bit under the hood, how it works. So what are we going to do in this tutorial? We will see what is deep learning and what do we need for deep learning. And one of the main components of deep learning is neural networks. So we will see what is neural network, what is a perceptron, and how to implement logic gates like AND, OR, NOR, and so on using perceptrons. The different types of neural networks, and then applications of deep learning, and we will also see how neural networks works. So how do we do the training of neural networks? And at the end, we will end up with a small demo code which will take you through in TensorFlow. Now, in order to implement deep learning code, there are multiple libraries or development environments that are available, and TensorFlow is one of them. So the focus at the end of this would be on how to use TensorFlow to write a piece of code using Python as a programming language. And we will take up an example which is a very common one, which is like the hello world of deep learning, the handwriting number recognition, which is a MNIST, commonly known as MNIST database. So we will take a look at MNIST database and how we can train a neural network to recognize handwritten numbers. So that's what you will see in this particular video. So let's get started. What is deep learning? Deep learning is like a subset of what is known as a high-level concept called artificial intelligence. You must be already familiar, must have heard about this term, artificial intelligence. So artificial intelligence is like the high-level concept, if you will. And in order to implement artificial intelligence applications, we use what is known as machine learning. And within machine learning, a subset of machine learning is deep learning. Machine learning is a little bit more generic concept, and deep learning is one type of machine learning, if you will. And we will see a little later in maybe the following slides a little bit more in detail how deep learning is different from traditional machine learning. But to start with, we can mention here that deep learning uses one of the differentiators between deep learning and traditional machine learning is that deep learning uses neural networks. And we will talk about what are neural networks and how we can implement neural networks and so on and so forth as a part of this tutorial. So a little deeper into deep learning. Deep learning primarily involves working with complicated unstructured data compared to traditional machine learning, where we normally use structured data. In deep learning, the data would be primarily images or voice or maybe text file. So and it is large amount of data as well. And deep learning can handle complex operations. It involves complex operations. And the other difference between traditional machine learning and deep learning is that the feature extraction happens pretty much automatically. In traditional machine learning, feature engineering is done manually. The data scientists, we data scientists have to do feature engineering, feature extraction. But in deep learning, that happens automatically. And of course, deep learning, for large amounts of data, complicated unstructured data, deep learning gives very good performance. Now, as I mentioned, one of the secret sources of deep learning is neural networks. Let's see what neural networks is. Neural networks is based on our biological neurons. The whole concept of deep learning and artificial intelligence is based on human brain, and human brain consists of billions of tiny stuff called neurons, and this is how a biological neuron looks, and this is how an artificial neuron looks. So neural networks is like a simulation of our human brain. Human brain has billions of biological neurons, and we are trying to simulate the human brain using artificial neurons. This is how a biological neuron looks. It has dendrites, and the corresponding component with an artificial neural network is, or an artificial neuron, are the inputs. They receive the inputs through dendrites. And then there is the cell nucleus, which is basically the processing unit in a way. So in artificial neuron also there is a piece which is an equivalent of this cell nucleus, and based on the weights and biases, we will see what exactly weights and biases are as we move. The input gets processed, and that results in an output. In a biological neuron, the output is sent through a synapse, and in an artificial neuron there is an equivalent of that in the form of an output. And biological neurons are also interconnected. So there are billions of neurons which are interconnected. In the same way, artificial neurons are also interconnected. So this output of this neuron will be fed as an input to another neuron, and so on. Now, in neural network, one of the very basic units is a perceptron. So what is a perceptron? A perceptron can be considered as one of the fundamental units of neural networks. It can consist at least of one neuron, but sometimes it can be more than one neuron. But you can create a perceptron with a single neuron, and it can be used to perform certain functions. It can be used as a basic binary classifier. It can be trained to do some basic binary classification, and this is how a basic perceptron looks like. And this is nothing but a neuron. You have inputs x1, x2, to xn, and there is a summation function, and then there is what is known as an activation function. And based on this input, what is known as the weighted sum, the activation function either gives an output like a 0 or a 1. So we say the neuron is either activated or not. So that's the way it works. So you get the inputs. These inputs are, each of the inputs are multiplied by a weight, and there is a bias that gets added, and that whole thing is fed to an activation function, and then that results in an output. And if the output is correct, it is accepted. If it is wrong, if there is an error, then that error is fed back, and the neuron then adjusts the weights and biases to give a new output, and so on and so forth. So that's what is known as the training process of a neuron or a neural network. There's a concept called perceptron learning. So perceptron learning is again one of the very basic learning processes. The way it works is somewhat like this. So you have all these inputs like x1 to xn, and each of these inputs is multiplied by a weight, and then that sum, this is the formula, the equation. So that sum, wi xi sigma of that, which is the sum of all these product of x and w, is added up, and then a bias is added to that. The bias is not dependent on the input or the input values, but the bias is common for one neuron. However, the bias value keeps changing during the training process. Once the training is completed, the values of these weights, W1, W2, and so on, and the value of the bias gets fixed. So that is basically the whole training process, and that is what is known as the perceptron training. So the weights and biases keep changing till you get the accurate output. And the summation is of course passed through the activation function. As you see here, this WIXI summation plus B is passed through activation function, and then the neuron gets either fired or not. And based on that, there will be an output. That output is compared with the actual or expected value, which is also known as labeled information. So this is the process of supervised learning. So the output is already known, and that is compared, and thereby we know if there is an error or not. And if there is an error, the error is fed back and the weights and biases are updated accordingly till the error is reduced to the minimum. So this iterative process is known as perceptron learning or perceptron learning rule, and this error needs to be minimized. So till the error is minimized, this iteratively the weights and biases keep changing, and that is what is the training process. So the whole idea is to update the weights and the bias of the perceptron till the error is minimized. The error need not be zero. The error may not ever reach zero, but the idea is to keep changing these weights and bias so that the error is minimum, the minimum possible that it can have. So this whole process is an iterative process, and this is the iteration continues till either the error is zero, which is unlikely situation, or it is the minimum possible within these given conditions. Now in 1943, two scientists, Warren McCulloch and Walter Pitts, came up with an experiment where they were able to implement the logical functions like AND, OR, and NOR using neurons. And that was a significant breakthrough in a sense. So they were able to come up with the most common logical gates. They were able to implement some of the most common logical gates, which could take two inputs like A and B and then give a corresponding result. So for example, in case of an AND gate, A and B, and then the output is AB. In case of an OR gate, it is A plus B, and so on and so forth. And they were able to do this using a single layer perceptron. Now, most of these gates, it was possible to use single layer perceptron except for XOR, and we will see why that is in a little bit. So this is how an AND gate works. The inputs A and B, the output should be fired, or the neuron should be fired only when both the inputs are 1. So if you have 0, 0, the output should be 0. For 0, 1, it is again 0, 1, 0 again 0, and 1, 1, the output should be 1. So how do we implement this with a neuron? So it was found that by changing the values of weights, it is possible to achieve this logic. So for example, if we have equal weights like 0.7, 0.7, and then if we take the sum of the weighted product, so for example 0.7 into 0, and then 0.7 into 0 will give you 0, and so on and so forth. And in the last case, when both the inputs are 1, you get a value which is greater than 1, which is the threshold. So only in this case the neuron gets activated and the output is, there is an output. In all the other cases, there is no output because the threshold value is 1. So this is implementation of an AND gate using a single perceptron or a single neuron. Similarly, an OR gate. In order to implement an OR gate, in case of an OR gate, the output will be 1 if either of these inputs is 1. So for example, 0, 1 will result in 1, or rather, in all the cases it is 1 except for 0, 0. So how do we implement this using a perceptron? Once again, if you have a perceptron with weights, for example 1.2, now if you see here, if in the first case when both are 0, the output is 0. In the second case, when it is 0 and 1, 1.2 into 0 is 0, and then 1.2 into 1 is 1. And in the second case, similarly, the output is 1.2. In the last case, when both the inputs are 1, the output is 2.4. So during the training process, these weights will keep changing, and then at one point where the weights are equal to W1 is equal to 1.2 and W2 is equal to 1.2, the system learns that it gives the correct output. So that is implementation of OR gate using a single neuron or a single layer perceptron. Now XOR gate. This was one of the challenging ones. They tried to implement an XOR gate with a single level perceptron, but it was not possible. And therefore, in order to implement an XOR, so this was like a roadblock in the progress of neural network. However, subsequently they realized that this can be implemented, an XOR gate can be implemented using a multi-level perceptron or MLP. So in this case, there are two layers instead of a single layer, and this is how you can implement an XOR gate. So you will see that X1 and X2 are the inputs, and there is a hidden layer, and that's why it is denoted as H3 and H4, and then you take the output of that and feed it to the output at O5 and provide a threshold here. So we will see here that this is the numerical calculation. So the weights are, in this case for X1 it is 20 and minus 20, and once again 20 and minus 20. So these inputs are fed into H3 and H4. So you will see here for H3 the input is 0 1 1 1, and for H4 it is 1 0 1 1. And if you now look at the output, final output, where the threshold is taken as 1, if we use a sigmoid with the threshold 1, you will see that in these two cases it is 0, and in the last two cases it is 1. So this is the implementation of XOR. In case of XOR, only when one of the inputs is 1, you will get an output. So that is what we are seeing here. If we have either both the inputs are 1 or both the inputs are 0, then the output should be 0. So that is what is an exclusive OR gate. So it is exclusive because only one of the inputs should be 1, and then only you will get an output of 1, which is satisfied by this condition. So this is a special implementation. XOR gate is a special implementation of perceptron. Now that we got a good idea about perceptron, let's take a look at what is a neural network. So we have seen what is a perceptron, we have seen what is a neuron, so we will see what exactly is a neural network. So neural network is nothing but a network of these neurons, and they are different types of neural networks. There are about 5 of them. These are artificial neural network, convolutional neural network, then recursive neural network or recurrent neural network, deep neural network, and deep belief network. So, and each of these types of neural networks have a special, they can solve a special kind of problems. For example, convolutional neural networks are very good at performing image processing and image recognition and so on, whereas RNN are very good for speech recognition and also text analysis and so on. So each type has some special characteristics, and they're good at performing certain special kind of tasks. What are some of the applications of deep learning? Deep learning is today used extensively in gaming. You must have heard about AlphaGo, which is a game created by a startup called DeepMind, which got acquired by Google. And AlphaGo is an AI which defeated the human world champion Lee Sedol in this game of Go. So gaming is an area where deep learning is being extensively used, and a lot of research happens in the area of gaming as well. In addition to that, nowadays there are neural networks or special type called generative adversarial networks, which can be used for synthesizing either images or music or text and so on, and they can be used to compose music. So the neural network can be trained to compose a certain kind of music. And autonomous cars, you must be familiar with Google's self-driving car, and today a lot of automotive companies are investing in this space, and deep learning is a core component of this autonomous cars. The cars are trained to recognize, for example, the road, the lane markings on the road, signals, any objects that are in front, any obstruction, and so on and so forth. So all this involves deep learning. So that's another major application. And robots, we have seen several robots, including Sophia. You may be familiar with Sophia, who was given a citizenship by Saudi Arabia. And there are several such robots which are very human-like, and the underlying technology in many of these robots is deep learning. Medical diagnostics and healthcare is another major area where deep learning is being used. And within healthcare diagnostics, again, there are multiple areas where deep learning and image recognition, image processing can be used. For example, for cancer detection, as you may be aware, if cancer is detected early on, it can be cured. And one of the challenges is in the availability of specialists who can diagnose cancer using these diagnostic images and various scans and so on and so forth. So the idea is to train neural network to perform some of these activities so that the load on the cancer specialist doctors or oncologists comes down. And there is a lot of research happening here, and there are already quite a few applications that are claimed to be performing better than human beings in this space. It can be lung cancer, it can be breast cancer, and so on and so forth. So healthcare is a major area where deep learning is being applied. Let's take a look at the inner working of a neural network. So how does an artificial neural network, let's say, can we train a neural network to identify the shapes like squares and circles and triangles when these images are fed? So this is how it works. Any image is nothing but it is a digital information of the pixels. So in this particular case, let's say this is an image of 28 by 28 pixel and this is an image of a square. There is a certain way in which the pixels are lit up, and so these pixels have a certain value, maybe from 0 to 256, and 0 indicates that it is black or it is dark, and 256 indicates it is white or lit up. So that is like an indication or a measure of how the pixels are lit up. And so this is an image is, let's say, consisting of information of 784 pixels. So all the information, what is inside this image, can be kind of compressed into these 784 pixels. The way each of these pixels is lit up provides information about what exactly is the image. So we can train neural networks to use that information and identify the images. So let's take a look how this works. So each neuron, the value, if it is close to 1, that means it is white, whereas if it is close to 0, that means it is black. Now, this is an animation of how this whole thing works. So these pixels, one of the ways of doing it is we can flatten this image and take this complete 784 pixels and feed that as input to our neural network. The neural network can consist of probably several layers. There can be a few hidden layers, and then there is an input layer and an output layer. Now the input layer takes these 784 pixels as input, the values of each of these pixels, and then you get an output which can be of 3 types or 3 classes. One can be a square, a circle, or a triangle. Now during the training process, there will be initially, obviously you feed this image and it will probably say it's a circle or it will say it's a triangle. So as a part of the training process, we then send that error back, and the weights and the biases of these neurons are adjusted till it correctly identifies that this is a square. That is the whole training mechanism that happens out here. Now let's take a look at a circle. Same way. So you feed these 784 pixels. There is a certain pattern in which the pixels are lit up, and the neural network is trained to identify that pattern. And during the training process, once again, it would probably initially identify it incorrectly, saying this is a square or a triangle, and then that error is fed back and the weights and biases are adjusted finally till it finally gets the image correct. So that is the training process. So now we will take a look at same way a triangle. So now if you feed another image which is consisting of triangles. So this is the training process. Now we have trained our neural network to classify these images into a triangle or a circle and a square. So now this neural network can identify these 3 types of objects. Now if you feed another image and it will be able to identify whether it's a square or a triangle or a circle. Now, what is important to be observed is that when you feed a new image, it is not necessary that the image or the triangle is exactly in this position. Now, the neural network actually identifies the patterns. So even if the triangle is, let's say, positioned here, not exactly in the middle, but maybe at the corner or in the side, it would still identify that it is a triangle. And that is the whole idea behind pattern recognition. So how does this training process work? This is a quick view of how the training process works. So we have seen that a neuron consists of inputs. It receives inputs, and then there is a weighted sum, which is nothing but this xi, wi, summation of that plus the bias. And this is then fed to the activation function, and that in turn gives us a output. Now, during the training process, initially, obviously, when you feed these images, when you send maybe a square, it will identify it as a triangle, and when you maybe feed a triangle, it will identify as a square, and so on. So that error information is fed back, and initially these weights can be random. Maybe all of them have 0 values, and then it will slowly keep changing. So as a part of the training process, the values of these weights, W1, W2 up to Wn, keep changing in such a way that towards the end of the training process, it should be able to identify these images correctly. So till then, the weights are adjusted, and that is known as the training process. And these weights are numeric values. It could be 0.5, 0.25, 0.35, and so on. It could be positive or it could be negative, and the value that is coming here is the pixel value. As we have seen, it can be anything between 0 to 1. You can scale it between 0 to 1 or 0 to 256, whichever way. 0 being black and 256 being white, and then all the other colors in between. So that is the input. So these are numerical values. This multiplication or the product, Wixi, is a numerical value, and the bias is also a numerical value. We need to keep in mind that the bias is fixed for a neuron. It doesn't change with the inputs, whereas the weights are 1 per input. So that is one important point to be noted. But the bias also keeps changing. Initially, it will again have a random value, but as a part of the training process, the values of the weights W1, W2, Wn, and the value of B will change. And ultimately, once the training process is complete, these values are fixed for this particular neuron. W1, W2 up to Wn, and plus the value of the B is also fixed for this particular neuron. And in this way, there will be multiple neurons, and there may be multiple levels of neurons here, and that's the way the training process works. So this is another example of multi-layer. So there are 2 hidden layers in between, and then you have the input layer, values coming from the input layer, then it goes through multiple layers, hidden layers, and then there is an output layer. And as you can see, there are weights and biases for each of these neurons in each layer, and all of them keeps changing during the training process. And at the end of the training process, all these weights have a certain value, and that is a trained model, and those values will be fixed once the training is completed. Alright, then there is something known as activation function. Neural networks consists of one of the components in neural networks is activation function, and every neuron has an activation function, and there are different types of activation functions that are used. It could be a ReLU, it could be sigmoid, and so on and so forth. And the activation function is what decides whether a neuron should be fired or not. So whether the output should be 0 or 1 is decided by the activation function. And the activation function in turn takes the input, which is the weighted sum. Remember, we talked about Wixi plus B. That weighted sum is fed as an input to the activation function, and then the output can be either a 0 or a 1. And there are different types of activation functions which are covered in an earlier video you might want to watch. Alright, so as a part of the training process, we feed the inputs, the labeled data or the training data, and then it gives an output, which is the predicted output by the network, which we indicate as y hat. And then there is a labeled data, because for supervised learning, we already know what should be the output. So that is the actual output. And in the initial process, before the training is complete, obviously there will be error. So that is measured by what is known as a cost function. So the difference between the predicted output and the actual output is the error, and the cost function can be defined in different ways. There are different types of cost functions. So in this case, it is like the average of the squares of the error. So, and then all the errors are added, which can sometimes be called as sum of squares, sum of square errors, or SSE, and that is then fed as a feedback in what is known as backward propagation or backpropagation. And that helps in the network adjusting the weights and biases. And so the weights and biases get updated till this value, the error value or the cost function, is minimum. Now there is a optimization technique which is used here called gradient descent optimization. And this algorithm works in a way that the error, which is the cost function, needs to be minimized. So there's a lot of mathematics that goes behind this. For example, they find the local minima, the global minima using the differentiation and so on and so forth. But the idea is this. So as a training process, as the part of training, the whole idea is to bring down the error, which is like, let's say this is the function, the cost function. At certain levels it is very high, the cost value of the cost function, the output of the cost function is very high. So the weights have to be adjusted in such a way, and also the bias of course, that the cost function is minimized. So there is this optimization technique called gradient descent that is used, and this is known as the learning rate. Now gradient descent, you need to specify what should be the learning rate, and the learning rate should be optimal, because if you have a very high learning rate, then the optimization will not converge, because at some point it will cross over to the side. On the other hand, if you have very low learning rate, then it might take forever to converge. So you need to come up with the optimum value of the learning rate, and once that is done using the gradient descent optimization, the error function is reduced, and that's like the end of the training process. Alright, so this is another view of gradient descent. So this is how it looks. This is your cost function, the output of the cost function, and that has to be minimized using gradient descent algorithm. And these are like the parameters, and weight could be one of them. So initially we start with certain random values, so cost will be high, and then the weights keep changing, and in such a way that the cost function needs to come down, and at some point it may reach the minimum value and then it may increase. So that is where the gradient descent algorithm decides that, okay, it has reached a minimum value and it will kind of try to stay here. This is known as the global minima. Now sometimes these curves may not be, just for explanation purpose, this has been drawn in a nice way, but sometimes these curves can be pretty erratic. There can be some local minima here, and then there is a peak, and so on. So the whole idea of gradient descent optimization is to identify the global minima and to find the weights and the bias at that particular point. So that's what is gradient descent. And then this is another example. So you can have these multiple local minima. So as you can see, at this point when it is coming down, it may appear like this is a minimum value, but then it is not. This is actually the global minimum value, and the gradient descent algorithm will make an effort to reach this level and not get stuck at this point. So the algorithm is already there, and it knows how to identify this global minimum, and that's what it does during the training process. Now, in order to implement deep learning, there are multiple platforms and languages that are available, but the most common platform nowadays is TensorFlow. And so that's the reason we have this tutorial. We have created this tutorial for TensorFlow. So we will take you through a quick demo of how to write a TensorFlow code using Python. And TensorFlow is an open source platform created by Google. So let's just take a look at the details of TensorFlow. And so this is a library, a Python library. So you can use Python or any other languages. It's also supported in other languages like Java and R and so on. But Python is the most common language that is used. So it is a library for developing deep learning applications, especially using neural networks. And it consists of primarily two parts, if you will. So one is the tensors, and then the other is the graphs or the flow. That's the way the name, that's the reason for this kind of a name called TensorFlow. So what are tensors? Tensors are like multi-dimensional arrays, if you will. That's one way of looking at it. So usually you have a one-dimensional array. So first of all, you can have what is known as a scalar, which means a number. And then you have a one-dimensional array, something like this, which means this is like a set of numbers. So that is a one-dimensional array. Then you can have a two-dimensional array, which is like a matrix. And beyond that, sometimes it gets difficult. So this is a three-dimensional array, but TensorFlow can handle many more dimensions. So it can have multi-dimensional arrays. That is the strength of TensorFlow, and which makes computation, deep learning computation, much faster. And that's the reason why TensorFlow is used for developing deep learning applications. So TensorFlow is a deep learning tool, and this is the way it works. So the data basically flows in the form of tensors, and the way the programming works as well is that you first create a graph of how to execute it, and then you actually execute that particular graph in the form of what is known as a session. We will see this in the TensorFlow code as we move forward. So all the data is managed or manipulated in tensors, and then the processing happens using these graphs. There are certain terms called, like for example, ranks of a tensor. The rank of a tensor is like a dimensionality in a way. So for example, if it is scalar, so there is just a number, just one number, the rank is supposed to be 0. And then it can be a one-dimensional vector, in which case the rank is supposed to be 1. And then you can have a two-dimensional vector, typically like a matrix. Then in that case, we say the rank is 2. And then if it is a three-dimensional array, then rank is 3, and so on. So it can have more than 3 as well. So it is possible that you can store multi-dimensional arrays in the form of tensors. So what are some of the properties of TensorFlow? I think today it is one of the most popular platform. TensorFlow is the most popular deep learning platform or library. It is open source. It's developed by Google, developed and maintained by Google, but it is open source. One of the most important things about TensorFlow is that it can run on CPUs as well as GPUs. GPU is a graphical processing unit, just like CPU is central processing unit. Now, in earlier days, GPU was used primarily for graphics, and that's how the name has come. And one of the reasons is that it cannot perform generic activities very efficiently like CPU, but it can perform iterative actions or computations extremely fast and much faster than a CPU. So they are really good for computational activities, and in deep learning there is a lot of iterative computation that happens, so in the form of matrix multiplication and so on. So GPUs are very well suited for this kind of computation, and TensorFlow supports both GPU as well as CPU. And there's a certain way of writing code in TensorFlow. We will see as we go into the code. And of course, TensorFlow can be used for traditional machine learning as well, but then that would be an overkill. But just for understanding, it may be a good idea to start writing code for a normal machine learning use case so that you get a hang of how TensorFlow code works, and then you can move into neural networks. So that is just a suggestion, but if you're already familiar with how TensorFlow works, then probably you can go straight into the neural networks part. So in this tutorial, we will take the use case of recognizing handwritten digits. This is like a hello world of deep learning, and this is a nice little MNIST database is a nice little database that has images of handwritten digits nicely formatted, because very often in deep learning and neural networks, we end up spending a lot of time in preparing the data for training. And with MNIST database, we can avoid that. You already have the data in the right format, which can be directly used for training. And MNIST also offers a bunch of built-in utility functions that we can straight away use and call those functions without worrying about writing our own functions. And that's one of the reasons why MNIST database is very popular for training purposes. Initially, when people want to learn about deep learning and TensorFlow, this is the database that is used. And it has a collection of 70,000 handwritten digits, and a large part of them are for training. Then you have test, just like in any machine learning process, and then you have validation. And all of them are labeled. So you have the images and their label. And these images, they look somewhat like this. So they are handwritten images collected from a lot of individuals. People have, these are samples written by human beings. They have handwritten these numbers going from 0 to 9. So people have written these numbers, and then the images of those have been taken and formatted in such a way that it is very easy to handle. So that is MNIST database. And the way we are going to implement this in our TensorFlow is we will feed this data, especially the training data, along with the label information. And the data is basically, these images are stored in the form of the pixel information, as we have seen in one of the previous slides. All the images are nothing but, these are pixels. So an image is nothing but an arrangement of pixels, and the value of the pixel, either it is lit up or it is not, or in somewhere in between. That's how the images are stored, and that is how they are fed into the neural network and for training. Once the network is trained, when you provide a new image, it will be able to identify within a certain error, of course. And for this, we will use one of the simpler neural network configurations called softmax. And for simplicity, what we will do is we will flatten these pixels. So instead of taking them in a two-dimensional arrangement, we just flatten them out. So for example, it starts from here. It is a 28 by 28. So there are 784 pixels. So pixel number 1 starts here. It goes all the way up to 28. Then 29 starts here and it goes up to 56 and so on. And the pixel number 784 is here. So we take all these pixels, flatten them out, and feed them like one single line into our neural network. And this is what is known as a softmax layer. What it does is, once it is trained, it will be able to identify what digit this is. So there are, in this output layer, there are 10 neurons, each signifying a digit. And at any given point of time, when you feed an image, only one of these 10 neurons gets activated. So for example, if this is trained properly, and if you feed a number 9 like this, then this particular neuron gets activated. So you get an output from this neuron. Let me just use a pen or a laser to show you here. Okay, so you're feeding a number 9. Let's say this has been trained, and now if you're feeding a number 9, this will get activated. Now let's say you feed 1 to the trained network, then this neuron will get activated. If you feed 2, this neuron will get activated, and so on. I hope you get the idea. So this is one type of a neural network or an activation function known as softmax layer. So that's what we will be using here. This is one of the simpler ones for quick and easy understanding. So this is how the code would look. We will go into our lab environment in the cloud, and we will show you there directly. But very quickly, this is how the code looks. And let me run you through briefly here, and then we will go into the Jupyter notebook where the actual code is, and we will run that as well. So as a first step, first of all, we are using Python here, and that's why the syntax of the language is Python. And the first step is to import the TensorFlow library. So, and we do this by using this line of code saying import TensorFlow as TF. TF is just for convenience, so you can give any name. And once you do this, TensorFlow is available as an object in the name of TF, and then you can run its methods and access its attributes and so on and so forth. And MNIST database is actually an integral part of TensorFlow, and that's again another reason why we, as a first step, we always use this example MNIST database example. So you just simply import MNIST database as well using this line of code, and you slightly modify this so that the labels are in this format, what is known as one hot true, which means that the label information is stored like an array. And let me just use a pen to show what exactly it is. So when you do this one hot true, what happens is each label is stored in the form of an array of 10 digits, and let's say the number is 8. Okay, so in this case, all the remaining values, there will be a bunch of zeros. So this is like array at position 0, this is at position 1, position 2, and so on and so forth. Let's say this is position 7, then this is position 8. That will be 1 because our input is 8. And again, position 9 will be 0. Okay, so one hot encoding, this one hot encoding true will kind of load the data in such a way that the labels are in such a way that only one of the digits has a value of 1, and that indicates, so based on which digit is 1, we know what is the label. So in this case, the 8th position is 1, therefore we know this sample data, the value is 8. Similarly, if you have a 2 here, let's say, then the labeled information will be somewhat like this. So you have your labels. So you have this as 0, the 0th position. The first position is also 0. The second position is 1 because this indicates number 2. And then you have third as 0 and so on. Okay, so that is the significance of this one hot true. All right, and then we can check how the data is looking by displaying the data. And as I mentioned earlier, this is pretty much in the form of digital form, like numbers. So all these are like pixel values, so you will not really see an image in this format, but there is a way to visualize that image. I will show you in a bit. And this tells you how many images are there in each set. So the training, there are 55,000 images in training, and in the test set there are 10,000, and then validation there are 5,000. So altogether there are 70,000 images. All right, so let's move on, and we can view the actual image by using the matplotlib library. And this is how you can view. This is the code for viewing the images, and you can view them in color or you can view them in grayscale. So the CMap is what tells in what way we want to view it, and what are the maximum values and the minimum values of the pixel values. So these are the max and minimum values, so of the pixel values. So maximum is 1 because this is a scaled value. So 1 means it is white, and 0 means it is black, and in between is, it can be anywhere in between black and white. And the way to train the model, there is a certain way in which you write your TensorFlow code. And the first step is to create some placeholders, and then you create a model. In this case, we will use the softmax model, one of the simplest ones. And placeholders are primarily to get the data from outside into the neural network. So this is a very common mechanism that is used. And then, of course, you will have variables, which are your, remember, these are your weights and biases. So for, in our case, there are 10 neurons, and each neuron actually has 784 because each neuron takes all the inputs. If we go back to our slide here, actually every neuron takes all the 784 inputs. Right? This is the first neuron. It receives all the 784. This is the second neuron. This also receives all the 780. So each of these inputs needs to be multiplied with a weight, and that's what we are talking about here. So this is a matrix of 784 values for each of the neurons, and so it is like a 10 by 784 matrix because there are 10 neurons. And similarly, there are biases. Now remember, I mentioned biases only 1 per neuron, so it is not 1 per input, unlike the weights. So therefore there are only 10 biases because there are only 10 neurons in this case. So that is what we are creating a variable for biases. So this is something little new in TensorFlow. You will see, unlike our regular programming languages where everything is a variable, here the variables can be of three different types. You have placeholders, which are primarily used for feeding data. You have variables, which can change during the course of computation. And then a third type, which is not shown here, are constants. So these are like fixed numbers. All right. So in a regular programming language, you may have everything as variables or at the most variables and constants. But in TensorFlow, you have three different types: placeholders, variables, and constants. And then you create what is known as a graph. So TensorFlow programming consists of graphs and tensors, as I mentioned earlier. So this can be considered ultimately as a tensor. And then the graph tells how to execute the whole implementation, so that the execution is stored in the form of a graph. And in this case, what we are doing is we are doing a multiplication. TF, you remember this TF was created as a TensorFlow object here. One more level, one more. So TF is available here. Now TensorFlow has what is known as a matrix multiplication or matmul function. So that is what is being used here in this case. So we are using the matrix multiplication of TensorFlow so that you multiply your input values x with w, right? This is what we were doing, xw plus b. You're just adding b, and this is in very similar to one of the earlier slides where we saw sigma xi wi. So that's what we are doing here. Matrix multiplication is multiplying all the input values with the corresponding weights and then adding the bias. So that is the graph we created. And then we need to define what is our loss function and what is our optimizer. So in this case, we again use the TensorFlow's APIs. So tf.nn softmax cross entropy with logits is the API that we will use. And reduce mean is what is like the mechanism whereby which says that you reduce the error. And optimizer for doing reduction of the error, what optimizer are we using? So we are using gradient descent optimizer. We discussed about this in a couple of slides earlier. And for that, you need to specify the learning rate. You remember we saw that there was a slide somewhat like this, and then you define what should be the learning rate, how fast you need to come down. That is the learning rate. And this again needs to be tested and tried, and to find out the optimum level of this learning rate. It shouldn't be very high, in which case it will not converge, or shouldn't be very low, because it will, in that case, it will take very long. So you define the optimizer and then you call the method minimize for that optimizer, and that will kickstart the training process. And so far we've been creating the graph, and in order to actually execute that graph, we create what is known as a session, and then we run that session. And once the training is completed, we specify how many times, how many iterations we want it to run. So for example, in this case, we are saying 1000 steps. So that is a exit strategy in a way. So you specify the exit condition. So a training will run for 1000 iterations. And once that is done, we can then evaluate the model using some of the techniques shown here. So let us get into the code quickly and see how it works. So this is our cloud environment. Now you can install TensorFlow on your local machine as well. I'm showing this demo on our existing cloud, but you can also install TensorFlow on your local machine, and there is a separate video on how to set up your TensorFlow environment. You can watch that if you want to install your local environment. Or you can go for any cloud service, like for example Google Cloud, Amazon, or Cloud Labs. Any of these you can use and run and try the code. Okay, so it has got started. We will log in. Alright, so this is our deep learning tutorial code, and this is our TensorFlow environment. And so let's get started. We have seen a little bit of a code walkthrough in the slides as well. Now you will see the actual code in action. So the first thing we need to do is import TensorFlow, and then we will import the data. and we need to adjust the data in such a way that the one hot encoding is set to true, one hot encoding, right? As I explained earlier. So in this case, the label values will be shown appropriately. And if we just check what is the type of the data, so you can see that this is a data sets, Python data sets. And if we check the number of images, the way it looks, so this is how it looks. It is an array of type float 32. Similarly, the number, if you want to see what is the number of training images, there are 55,000, then there are test images 10,000, and then validation images 5,000. Now let's take a quick look at the data itself, visualization. So we will use matplotlib for this. And if we take a look at the shape, now shape gives us like the dimension of the tensors or the arrays, if you will. So in this case, the training data set, if we see the size of the training data set using the method shape, it says there are 55,000 and 55,000 by 784. So remember, the 784 is nothing but the 28 by 28, 28 into 28. So that is equal to 784. So that's what it is showing. Now we can take just one image and just see what is the first image and see what is the shape. So again, size, obviously it is only 784. Similarly, you can look at the image itself, the data of the first image itself. So this is how it shows. So large part of it will probably be zeros, because as you can imagine, in the image only certain areas are written, rest is blank. So that's why you will mostly see zeros, either it is black or white. But then there are these values are, so the values are actually, they are scaled, so their values are between 0 and 1. Okay, so this is what you're seeing. So certain locations there are some values, and then other locations there are zeros. So that is how the data is stored and loaded. If we want to actually see what is the value of the handwritten image, if you want to view it, this is how you view it. So you create, like, do this reshape, and matplotlib has this feature to show you these images. So we will actually use the function called imshow, and then if you pass this parameters appropriately, you will be able to see the different images. Now I can change the values in this position, so which image we are looking at, right? So we can say, if I want to see what is there in maybe 5,000, right? So 5,000 has 3. Similarly, you can just say 5. What is in 5? 5 has 8. What is in 50? Again 8. So basically, by the way, if you're wondering how I'm executing this code, Shift Enter, in case you're not familiar with Jupyter Notebooks, Shift Enter is how you execute each cell, individual cell. And if you want to execute the entire program, you can go here and say run all. So that is how this code gets executed. And here again, we can check what is the maximum value and what is the minimum value of this pixel values. As I mentioned, it is scaled, so therefore it is between, the values lie between 1 and 0. Now this is where we create our model. The first thing is to create the required placeholders and variables, and that's what we are doing here, as we have seen in the slides. So we create one placeholder and we create 2 variables, which is for the weights and biases. These 2 variables are actually matrices. So each variable has 784 by 10 actual values. Okay, so one for this 10 is for each neuron. There are 10 neurons, and 784 is for the pixel values inputs that are given, which is 28 into 28. And the biases, as I mentioned, one for each neuron, so there will be 10 biases. They are stored in a variable by the name B. And this is the graph, which is basically the multiplication of these matrix multiplication of X into W, and then the bias is added for each of the neurons. And the whole idea is to minimize the error. So let me just execute. I think this code is executed. Then we define what is our The y value is basically the label value. So this is another placeholder. We had x as one placeholder and y underscore true as a second placeholder, and this will have values in the form of 10 digit arrays. And since we said one hot encoded, the position which has a 1 value indicates what is the label for that particular number. All right. Then we have cross entropy, which is nothing but the loss function. And we have the optimizer. We have chosen gradient descent as our optimizer. Then the training process itself. So the training process is nothing but to minimize the cross entropy, which is again nothing but the loss function. So we define all of this in the form of a graph. So up to here, remember what we have done is we have not exactly executed any TensorFlow code till now. We are just preparing the graph, the execution plan. That's how the TensorFlow code works. So the whole structure and format of this code will be completely different from how we normally do programming. So even with people with programming experience may find this a little difficult to understand it, and it needs quite a bit of practice. So you may want to view this video also maybe a couple of times to understand this flow, because the way TensorFlow programming is done is slightly different from the normal programming. Some of you who, let's say, have done maybe Spark programming to some extent will be able to easily understand this. But even in Spark, the programming, the code itself is pretty straightforward. Behind the scenes, the execution happens slightly differently. But in TensorFlow, even the code has to be written in a completely different way. So the code doesn't get executed in the same way as you have written. So that's something you need to understand, and a little bit of practice is needed for this. So far what we have done up to here is creating the variables and feeding the variables, and or rather not feeding, but setting up the variables and the graph. That's all. Defining maybe the what kind of a network you want to use. For example, we want to use softmax and so on. So you have created the variables, how to load the data, loaded the data, viewed the data, and prepared everything, but you have not yet executed anything in TensorFlow. Now the next step is the execution in TensorFlow. So the first step for doing any execution in TensorFlow is to initialize the variables. So anytime you have any variables defined in your code, you have to run this piece of code always. So you need to basically create what is known as a node for initializing. So this is a node. You still are not yet executing anything here. You just created a node for the initialization. So let us go ahead and create that. And here onwards is where you will actually execute your code in TensorFlow. And in order to execute the code, what you will need is a session, TensorFlow session. So tf.session will give you a session, and there are a couple of different ways in which you can do this, but one of the most common methods of doing this is with what is known as a with loop. So you have a with tf.session as ses and with a colon here, and this is like a block, starting of the block, and these indentations tell how far this block goes, and this session is valid till this block gets executed. So that is the purpose of creating this with block. This is known as a with block. So with tf.session as ses, you say ses.run init. Now ses.run will execute a node that is specified here. So for example, here we are saying ses.run. Ses is basically an instance of the session. Right? So here we are saying tf.session. So an instance of the session gets created and we are calling that ses. And then we run a node within that, one of the nodes in the graph. So one of the nodes here is init. So we say run that particular node, and that is when the initialization of the variables happens. Now what this does is, if you have any variables in your code, in our case we have w is a variable and B is a variable. So any variables that we created, you have to run this code. You have to run the initialization of these variables, otherwise you will get an error. Okay, so that's what this is doing. Then we, within this with block, we specify a for loop, and we are saying we want the system to iterate for 1000 steps and perform the training. That's what this for loop does. Run training for 1000 iterations. And what it is doing basically is it is fetching the data or these images. Remember, there are about 50,000 images, but it cannot get all the images in one shot because it will take up a lot of memory and performance issues will be there. So this is a very common way of performing deep learning training. You always do in batches. So we have maybe 50,000 images, but you always do it in batches of 100 or maybe 500 depending on the size of your system and so on and so forth. So in this case, we are saying, okay, get me 100 images at a time and get me only the training images. Remember, we use only the training data for training purpose, and then we use test data for test purpose. You must be familiar with machine learning, so you must be aware of this. But in case you are not, in machine learning also, this is not specific to deep learning, but in machine learning in general, you have what is known as training data set and test data set. Your available data, typically you will be splitting into two parts and using the training data set for training purpose. And then to see how well the model has been trained, you use the test data set to check or test the validity or the accuracy of the model. So that's what we are doing here. And you observe here that we are actually calling an mnest function here. So we are saying mnest train.next batch. Right? So this is the advantage of using MNIST database, because they have provided some very nice helper functions which are readily available. Otherwise, this activity itself, we would have had to write a piece of code to fetch this data in batches. That itself is a lengthy exercise. So we can avoid all that if we are using MNIST database, and that's why we use this for the initial learning phase. Okay, so when we say fetch, what it will do is it will fetch the images into X and the labels into Y, and then you use this batch of 100 images and you run the training. So ses.run, basically what we are doing here is we are running the training mechanism, which is nothing but it passes this through the neural network, passes the images through the neural network, finds out what is the output, and if the output, obviously initially it will be wrong, so all that feedback is given back to the neural network, and thereby all the W's and B's get updated till it reaches 1000 iterations. In this case, the exit criteria is 1000, but you can also specify probably accuracy rate or something like that for as an exit criteria. So here it just says that, okay, this particular image was wrongly predicted, so you need to update your weights and biases. That's the feedback given to each neuron, and that is run for 1000 iterations. And typically by the end of this 1000 iterations, the model would have learned to recognize these handwritten images. Obviously, it will not be 100% accurate. Okay, so once that is done, so this happens for 1000 iterations. Once that is done, you then test the accuracy of these models by using the test data set. Right? So this is what we are trying to do here. The code may appear a little complicated because if you're seeing this for the first time, you need to understand the various methods of TensorFlow and so on. But it is basically comparing the output with what is actually there. That's all it is doing. So you have your test data, and you're trying to find out what is the actual value and what is the predicted value, and seeing whether they are equal or not, tf.equal, right? And how many of them are correct, and so on and so forth. And based on that, the accuracy is calculated as well. So this is the accuracy, and that is what we are trying to see, how accurate the model is in predicting these numbers or these digits. Okay, so let us run this. This entire thing is in one cell, so we will have to just run it in one shot. It may take a little while. Let us see. And Not bad. So it has finished the 1000 iterations. And what we see here as an output is the accuracy. So we see that the accuracy of this model is around 91%. Okay. Now, which is pretty good for such a short exercise. Within such a short time, we got 90% accuracy. However, in real life, this is probably not sufficient. So there are other ways to increase the accuracy. We will see probably in some of the later tutorials how to improve this accuracy, how to change maybe the hyperparameters like number of neurons or number of layers and so on and so forth, and so that this accuracy can be increased beyond 90%.
All right, so what is the TensorFlow Object Detection API? It is an open source framework which is actually provided by the TensorFlow team, and there are trained models available, and the sample code is also available which we can use in order to easily detect objects in images and videos. This is pretty robust and can detect objects fairly quickly, and this is very easy for people to use as well. People with very less or no knowledge of machine learning or deep learning can also, with a little bit of Python programming knowledge, can actually use this API, this library, to build object detection applications. This is a list of libraries that are required, and they have been shown in the code as well. The exact purpose of each of this library, why it is required, is out of the scope of this tutorial, but we will see in the code as we walk through some of these libraries how and why they are used. The COCO data set. COCO stands for Common Objects in Context. So this data set consists of 300,000 images of 90 most commonly found objects like chairs and tables and so on and so forth. So this model has been trained, or in fact a set of models have been trained on this data set, and this is pretty good to detect the most common objects in the images and videos. So with that, let's get into the code. Alright, so the first part is to import all these libraries, and this we have shown you in the slides as well. Again, a large part of this will be for doing some helper functions and maybe for visualizing the images and so on and so forth. So that's the reason they are required. As I said, the exact details of each and every library probably is out of scope, but these are needed. So as a first step, maybe you just go ahead and include these libraries and run the code, and maybe at a later point we can discuss what each of these libraries does. Now, this will work with TensorFlow version higher than 1.4. So if you are having TensorFlow version below 1.4, you may have to upgrade to a higher version. So let me go ahead and execute the cell, and we also need this line of code to make sure that once we run this object detection, the labeled images are displayed within this notebook, and many of you by now must be familiar with this. And we will import a few utility libraries, and you will see that we will be using some of these for visualization purpose. So once the objects are detected, we need to display the information, what that object is, and then what percentage of confidence the model has. So all these details, that's the utility functions that are stored here. And then the next part is to prepare the model. As I mentioned, we will be using an existing trained model. The TensorFlow team has actually provided these models. The one that we will be using is SSD with the mobile net, but you can actually use any one of the ones that are listed in this URL. Let me just quickly take you through this URL. These are a bunch of models, trained models that are readily available for anybody to use. It is open source. And let me scroll down. The only thing is that if there are some of them where the accuracy is much higher but they take longer, and there are some where the accuracy is not so high and they are much faster. So they are faster but the accuracy accuracy may not be that very high. So you can play around with some of these, and we in this particular exercise or in this particular tutorial, we are using this SSD model, which is SSD MobileNet version 1. So that's the model that we'll be using. So in this cell, we are primarily creating a bunch of variables with the various, for example, the name of the model, the path, and so on and so forth, so that we will be using these names in the next step, which is to download this model and install it locally. These are also referred to as frozen models. So once they are trained, and then you kind of extract or you freeze the model. So that's the reason they are called frozen models, so that others can just use this without any further training. So this is where we download and extract our model locally. So this will take a little while. Let me see if I can wait or maybe pause the video and come back once it is done. Might take a little while. Let's see if it completes. I have a pretty high speed network, but even then it takes some time, so that's good. But this part is over. Now let us see this part, and yes, both are done. So once that is done, we need to load some label mapping. Basically what this will do is your model, as you may be aware by now, if you do some classification, the model will actually not give any output as a text. It will give some numbers. So if there are 5 classes, it will say, okay, this belongs to model class 1 or 2 or 3 or 5 and so on, the numbers. Now, each of these will obviously, the numbers will not make any sense to the outside world. So we need to do some small mapping. So in this case, let's say 1 may be a chair, 2 may be a table, 3 may be a balloon, and so on. So that kind of number to text mapping we need to do, and that is what is being done in this particular cell. And then we have a helper code which will load the image and convert it into a NumPy array, so that the NumPy array is what gets processed and used by the model to do the detection part of it. So that is what this method is all about. So we will be later on we will be calling that function. And next is preparation for detection. So here we are basically telling where the images are stored and how many images, or what is the naming convention or format of the images. Now if you want, you can modify this code. For example, currently I have test_images as my folder. So let me go and show this to you. So this is under my object detection folder. I have another subfolder where I am storing my images, which is text_images. Now you can rename this folder and give some other name, and then in your code you can probably give that particular name for the subfolder. Similarly, the format of these files, what is the name and format of these files? Here it is in a very simple format, which is the names of the files are like beach 1, beach 2, beach 3, and so on. So I have taken beach as the theme. So I have images which are related to beaches. So this is beach 1, beach 2, and then beach 3. I have a few others, but we will use these 3 for our demo. And so that's what I'm saying here. The name of the images will be beach something.jpg, which is JPEG format, and in this curly braces basically it will be filled with either 1, 2, or 3 based on in this particular for loop. Okay, so that is what this is doing. Alright, so the next step is to run inference on these images in a loop. And what we are basically doing here is getting these images one by one and then running through the model to find out what are the objects that can be detected. And then against each of the object, a box will be drawn and it will be labeled with the name and the percentage of accuracy or confidence that the model detects these objects. Okay, so that is the function here, and so let me just run that piece of code. And here is basically where we are calling this function. So we are loading this images and then we are calling this function for each image, and then we are displaying this using the matplotlib library. So let's run this. It will take one image at a time and then detect the images. Now the beauty is that the same format of the code can be used for doing object detection in a video. So we have another video for doing object detection in a video. So most of the code out there will be reused from here. And the only thing is that instead of reading the images from the local storage, we read the frames from the video, and there is a neat little video reader that is available, and it will be shown in the other video. And frame by frame, we read the video and then pass on to this function, and it will act as if each of these frames is an image, and then it will do the same object detection on the entire video. So that's in a separate video. Just look out for that. And actually, the information about that is provided in the cards, the eye symbol. So that's the video object detection in video. That's the separate tutorial. All right. So now that we have all the pieces together, the last cell is where the whole action takes place. So let's run this and see how it looks. So it will take probably a little while, and there are about 3 images. Let's see what it detects. There we go. So good. So the first one, it has detected a person, and that too with 97% accuracy, which is I think pretty good. Okay, and then the next image, it detects umbrella and chair. There are a few other objects, but it's not able to detect. It has detected umbrella with 63% accuracy, or confidence rather, and the chair with 58%. Again, not bad. Then let's see the next image. So here, these are actually balloons, hot air balloons, but the model thinks it is a kite, which is probably not that bad. It sees there's something in the sky, and therefore probably it thinks it is a kite, and it detects that with 65% confidence. Okay, so that was pretty much all I wanted to show you in this particular tutorial about object detection in images.
Hey everyone! In this video called Keras Tutorial, we will teach you everything that you need to know about Keras in machine learning and data analysis. To begin, we will explain the concept of Keras to you. We will answer the question, what is Keras and how it is used in deep learning. Then, we will list out some common differences between Keras, TensorFlow, and PyTorch so that you can understand why Keras is the superior framework. After this, we will dive deep into Keras and see how you can use Keras to implement deep learning models with hands-on tutorials. And finally, we will take a look at Keras sequential models, a type of model in Keras which makes implementing neural networks extremely easy. So, let's get started.
The first question that arises in our mind is, what is deep learning? Deep learning is generally considered to be a subset of machine learning, which is nothing but a subset of artificial intelligence. What is artificial intelligence? Artificial intelligence is the intelligence which is demonstrated by machines, unlike the natural intelligence which is displayed by humans and animals, which also involves consciousness and emotionality. Meanwhile, machine learning is an application of artificial intelligence that provides systems the ability to automatically learn and improve from experience without being programmed to specifically. Now, deep learning, as I said, is a class of machine learning algorithms that uses multiple layers to progressively extract higher level features from raw input. For example, if we have a system which we are using for image processing, lower layers in the system may be used to detect the outlines of images, while higher layers may identify the concepts which are relevant to the image. In case of the picture of a human, it might recognize features such as digits or letters or face. Now, in deep learning, we use neural networks to use multiple mathematical operations to break down a complex problem into smaller parts which are solved individually. Each mathematical expression is called a neuron. Deep learning models are trained using large sets of labeled data and neural network architectures that learn features directly from the data without the need for manual feature extraction. One of the most popular types of deep neural networks is known as a convolution neural network. A convolution neural network convolves learned features with input data and uses 2D convolutional layers, making this architecture well suited to processing 2D data such as images. Now, in deep learning, neural networks will play a very important part. What exactly are neural networks? Neural networks are modeled from the way the human brain works. In our brain, we have neurons which carry electrical impulses from our brain to different parts of our body and help in transmitting instructions from the brain all over our body. In neural networks, a neuron acts as nothing more but a mathematical operation. Multiple neurons are required to break down a complex problem into various parts to make it easier to solve. Now, a neural network contains layers of interconnected nodes. Each node in a neural network is a perceptron and is similar to a multiple linear regression. The perceptron feeds the signals which are produced by multiple linear regressions into an activation function that may be nonlinear. Hidden layers will fine-tune the input weightings until neural network's margin of error is minimal and we get the optimal output. Now, what is Keras? Before we move on to Keras, let's take a look at TensorFlow. TensorFlow is a software library which was created by Google to implement large-scale machine learning models and to help solve complex numerical problems. TensorFlow is an end-to-end open-source machine learning platform which you can think of as an infrastructure layer for differentiable programming. It combines 4 key abilities. First, efficiently executing low-level tensor operations on CPU and GPU or TPU, computing gradient of arbitrary differential expressions, scaling computation to many devices, and exporting programs to external runtimes such as servers, browsers, or mobiles. But what does Keras have to do with all of this? Keras is nothing more than a high-level deep learning API which is written in Python for neural networks. It has multiple backend neural network computations and it makes implementing neural networks easy. As we know, Keras is a powerful and easy-to-use free open-source Python library for developing and evaluating deep learning models. Keras is a high-level API of TensorFlow 2, an approachable, highly productive interface for solving machine learning problems with a focus on modern deep learning. It provides essential abstractions and building blocks for developing and shipping machine learning solutions with high iteration velocity. Keras empowers engineers and researchers to take full advantage of the scalability and cross-platform capabilities of TensorFlow 2. You can run Keras on TPU or on large classes of GPU, and you can export your Keras model to run in the browser or on a mobile device. Keras provides a Python interface for artificial neural networks. Keras acts as an interface for TensorFlow library, and it helps in implementation of commonly used neural network building block layers such as objectives, activation functions, and optimizers, and a host of tools to make working with images and text data easier to simplify the coding necessary for writing deep neural network code. Basically, it wraps efficient numerical computation libraries such as Theano and TensorFlow and allows you to define and train neural network models in just a few lines of code. In fact, TensorFlow and Keras are so tied together that even in TensorFlow, the official Get Started with TensorFlow tutorial, we use high-level Keras APIs embedded in TensorFlow instead of just using TensorFlow by itself. Some of the important features of Keras include Keras being a high-level interface which uses Theano or TensorFlow for its backend. Keras can run smoothly on both CPU and GPU. It supports almost all the models required for you to create a complete neural network. And it is extremely modular in nature, which means it is incredibly expressive, flexible, and apt for innovative research. So why do we need Keras? First of all, Keras is an API which is designed for human beings, not for machines, which means that it follows best practices for reducing cognitive load. It offers consistent and simple APIs. It minimizes the number of users' action required for common use cases, and it provides clear and actionable feedback upon user error. It is extremely powerful and easy to use, and it also wraps numerical computation libraries such as Theano and TensorFlow and allows you to train and define neural networks in a few lines of code. This makes Keras easy to learn and use. As a Keras user, you can be more productive, allowing you to try more ideas than your competition faster, which in turn will help you win machine learning competition. This ease of use does not come at the cost of reduced flexibility because Keras integrates deeply with low-level TensorFlow functionality. It enables you to develop highly hackable workflows where any piece of functionality can be customized or reused easily. Building a model in Keras. Let's take a look at the basic pipeline which you will have to follow when you are using Keras to define a neural network. First of all, you will have to define a neural network. You will have to select the activation functions and the various mathematical operations that are going to be taking place in your neural network along with the different weightages. Next, you will use Keras to compile your network, which is basically you will use Keras to build it. After this, you will fit to your network. You will fit all the training data that you have to your network and use your testing data to evaluate how the network works. Finally, you will use this network to make predictions. This entire 5-step pipeline can be executed in Keras within 2 to 3 lines of code. Neural networks, which would have taken people days or even weeks to make, can be executed in Keras in a couple of hours. Now, uses of Keras. The first use of Keras is to productize deep models on smartphones. Deep models require a lot of computation power to run, but with the help of Keras, we can literally make deep models a product which can be sold and executed on smartphones. The next use of Keras is in distributed training of deep learning models. Distributed training means that we can split our deep learning model into different parts and train it on systems all across the globe. This makes training of our deep learning model extremely fast. Along with saving time, we are also saving on the computational power of our system, as it is not only our system which has to run such a heavy program. By distributing it across various systems, all the resources required to train a deep learning model go down significantly. Before we can see the differences between these platforms, we first need to know what exactly each of these platforms are. Let's start with TensorFlow. What is TensorFlow? TensorFlow is a low-level software library which is created by Google to help implement machine learning models and to solve complex numerical problems. TensorFlow is nothing but a free and open source software library for machine learning. It can be used across a range of tasks but has a particular focus on training and inference of deep neural networks. TensorFlow is a symbolic math library based on data flow and differential programming. It is used for both research and production at Google. What do you mean by data flow? It basically means that we perform calculations by converting every element into graphical form. The variables of the graph are called tensors and mathematical operations are called operators. Here, in the computational graph shown, you can see that x, y, and 2 are the variables. They will also be called tensors, and division, multiplication, and addition are the operators. This graph basically shows us the calculation that is going to occur in a machine learning model where x and y are going to be divided and y and 2 are going to be multiplied. The results of these two calculations are then going to be added to give us the final output. I told you that x, y, and 2 are also called tensors. What exactly are tensors? Tensors are multidimensional arrays with a uniform type. All tensors are immutable like Python numbers and strings, which means that you cannot update the contents of a tensor. You can only create a new tensor. Next, let's look at the API Keras. What exactly is Keras? Keras is a high-level deep learning API written in Python for easy implementation and computation of neural networks. Keras is an open-source software library that provides a TensorFlow interface for artificial neural networks. Keras acts as an interface for the TensorFlow library, which means that it runs on top of TensorFlow. Up until version 2.3, Keras supported multiple backends, including TensorFlow, Microsoft Cognitive Toolkit or CNTK, R, Theano, and PlaidML. As of version 2.4, only TensorFlow is supported. Designed to help enable fast experimentation with deep neural networks, it focuses on being user-friendly, modular, and extensible. Keras is a high-level API of TensorFlow, an approachable, highly productive interface for solving machine learning problems with a focus on modern deep learning. It provides essential abstractions and building blocks for developing and shipping machine learning solutions with high iteration velocity. Keras does not perform its own low-level operations such as tensor products and convolution. It relies on back-end engines for that. Even though Keras supports multiple back-end engines, its primary back-end engine is TensorFlow, and its primary supporter is Google, which means that Keras acts as nothing more but a wrapper class around TensorFlow, Theano, CNTK, PlateML, or MXNet, which are low-level APIs. Next, we will look at PyTorch. What exactly is PyTorch? PyTorch is a low-level API which is developed by Facebook for natural language processing and computer vision. It is a more powerful version of NumPy. It is an open-source machine learning library based on the Torch library used for applications such as computer vision and natural language processing. Primarily developed by Facebook's AI Research Lab, it is free and open-source software released under the modified BSD license. Although the Python interface is a more polished and the primary focus of development, PyTorch also has a C++ interface. Python is a widely liked language because it is easy to understand and write. PyTorch emphasizes flexibility and allows deep learning models to be expressed in basic Python. PyTorch is mainly used for natural language processing and for computer vision. Now let's move on to the differences between TensorFlow, Keras, and PyTorch. The first difference that we'll be looking at is called level of API. There are two main types of APIs, a low-level API and a high-level API. API stands for Application Programming Interface. A low-level application programming interface is generally more detailed and allows you to have more detailed control to manipulate functions within them on how to use and implement them, while a high-level API is more generic and simple and provides more functionality with one command statements than a lower-level API. High-level interfaces are comparatively easier to learn and to implement the models using them. They allow you to write code in a shorter amount of time and to be less involved with the details. In this case, TensorFlow is a high and low-level API. Pure TensorFlow is a low-level API, while TensorFlow wrapped in Keras is a high-level API. Keras in itself is a high-level API which uses multiple low-level APIs as a backend and simplifies the operation of these low-level APIs. PyTorch is a low-level API. The next criteria that we'll be looking at is speed. TensorFlow is very fast and is used for high performances. Keras is slower as it works on top of TensorFlow. Not only does it have to wait for TensorFlow to finish implementation, it then starts its own implementation. Meanwhile, PyTorch works at the same speed as TensorFlow, as both of them are both low-level APIs. Now, Keras is a wrapper class for TensorFlow and has added abstraction functionalities on top of TensorFlow, which make it slower than TensorFlow and PyTorch. In computation speed, both TensorFlow and PyTorch are almost equal, and in development speed, Keras is faster as it has built-in functionalities which can significantly reduce your development time. The next difference is on the architecture. TensorFlow is not very easy to use, and even though it provides Keras as a framework that makes it work easier, TensorFlow still has a very complex architecture which is hard to use. Meanwhile, Keras has a simpler architecture and is easier to use. It provides a high level of abstraction which makes implementation of programs in Keras significantly easier. PyTorch, on the other hand, also has a complex architecture and the readability is less when compared to Keras. TensorFlow uses computational graphs which makes it very complex and hard to interpret, but it has amazing computational ability across platforms. PyTorch is a little hard for beginners, but is really good for computer vision and deep learning purposes. Datasets and debugging. TensorFlow works with large datasets due to its high execution speed, and debugging is really hard in TensorFlow due to its complex nature. Meanwhile, Keras only works with very small datasets as its speed of execution is low. Programs do not require frequent debugging in Keras as they are relatively simpler, and PyTorch can manage high-level tasks in higher dimension datasets and is easier to debug than both Keras and TensorFlow. Next, we'll be looking at ease of development. As we said before, TensorFlow works with many hard concepts such as computational graphs and tensors, which means that writing code in TensorFlow is very hard. It is generally used by people when they are doing research work and really need very specific functionalities. Keras, on the other hand, provides a high level of abstraction which makes it very easy to use. It is best for people who are just starting out with Python and machine learning. PyTorch is easier than TensorFlow but is still comparatively hard than Keras. It is not very easy to learn for beginners but is significantly more powerful than just plain Keras. Ease of deployment. TensorFlow is very easy to deploy as it uses TensorFlow serving. TensorFlow serving is a flexible, high-performance serving system for machine learning models designed for production environments. TensorFlow serving makes it easy to deploy new algorithms and experiments while keeping the same server architecture and APIs. TensorFlow serving provides out-of-the-box integration with TensorFlow models but can be easily extended to serve other types of models and data. In Keras, model deployment can be done with either TensorFlow serving or Flask, which makes it relatively easy but not as easy as it would be with TensorFlow and PyTorch. PyTorch uses PyTorch Mobile, which makes deployment easy, but again, for TensorFlow deployment is way easier as TensorFlow serving can update your machine learning backend on the fly without the user even realizing. There's a growing need to execute ML models on edge devices to reduce latency, preserve privacy, and enable new interactive use cases. In the past, engineers used to train models separately. They would then go through a multi-step, error-prone, and often complex process to train the models for execution on a mobile device. The mobile runtime was often significantly different from the operations available during training, leading to inconsistent developer and eventually user experience. All of these frictions have been removed by PyTorch Mobile by allowing a seamless process to go from training to deployment by staying entirely within the PyTorch ecosystem. It provides an end-to-end workflow that simplifies the research to production environment for mobile devices. In addition, it paves the way for privacy-preserving features via federated learning techniques. At the end of the day, the question that really matters is which framework should you use, Keras, TensorFlow, or PyTorch? Now, TensorFlow has implemented various levels of abstraction to make implementation of deep learning and neural networks easy. This has also made debugging easier. Keras is simple and easy but not as fast as TensorFlow. It is more user-friendly than any other deep learning API, however, and is easier to learn for beginners. PyTorch, on the other hand, is the preferred deep learning API for teachers, but it is not as widely used in production as TensorFlow is. It is faster, but it has lower GPU utilization. At the end of the day, the framework that we would suggest that you use is TensorFlow. Why? While PyTorch may have been the preferred deep learning library for researchers, TensorFlow is much more widely used in day-to-day production. PyTorch's ease of use combined with the default eager execution mode for easier debugging predestines it to be used for fast, hacky solutions and smaller scale models. But TensorFlow's extensions for deployment on both servers and mobile devices combined with the lack of Python overhead makes it the preferred option for companies that work with deep learning models. In addition, the TensorFlow board visualization features offers a nice way of showing the inner workings of your model to, say, your customers. Meanwhile, between TensorFlow and Keras, the main difference isn't in performance. TensorFlow is a bit faster due to less overhead, but also the level of control you would like. Keras is much easier to start with than plain TensorFlow, but if you want to do something with Keras that doesn't come out of the box, it will be harder to implement that. TensorFlow, on the other hand, allows you to create any arbitrary computational graph, providing much more flexibility. So if you're doing more research type of work, TensorFlow is the sure route to go due to the flexibility that it provides.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
So we're going to dive right into what is Keras. We'll also go all the way through this into a couple of tutorials, because that's where you really learn a lot, is when you roll up your sleeves. So when we talk about what is Keras, Keras is a high-level deep learning API written in Python for easy implementation of neural networks. It uses deep learning frameworks such as TensorFlow, PyTorch, etc. as backend to make computation faster. And this is really nice because as a programmer, there is so much stuff out there and it's evolving so fast, it can get confusing, and having some kind of high-level order in there where you can actually view it and easily program these different neural networks is really powerful. It's really powerful to have something out really quick and also be able to start testing your models and seeing where you're going. So Keras works by using complex deep learning frameworks such as TensorFlow, PyTorch, MLPlade, etc. as a backend for fast computation, while providing a user-friendly and easy-to-learn front-end. And you can see here we have the Keras API specifications, and under that you'd have like TF Keras for TensorFlow, Thano Keras, and so on. And then you have your TensorFlow workflow that this is all sitting on top of. And this is, like I said, it organizes everything. The heavy lifting is still done by TensorFlow or whatever underlying package you put in there. And this is really nice because you don't have to dig as deeply into the heavy end stuff while still having a very robust package you can get up and running rather quickly. And it doesn't distract from the processing time because all the heavy lifting is done by packages like TensorFlow. This is the organization on top of it. So the working principle of Keras. The working principle of Keras is Keras uses computational graphs to express and evaluate mathematical expressions. And you can see here we put them in blue. They have the expression expressing complex problems as a combination of simple mathematical operators, where we have like the percentage, or in this case in Python that's usually your remainder, or multiplication. You might have the operator of x to the power of 0.3. And it uses useful for calculating derivatives by using backpropagation. So if we're doing with neural networks, when we send the error back up to figure out how to change it, this makes it really easy to do that without really not banging your head and having to hand write everything. It's easier to implement distributed computation, and for solving complex problems, specify input and outputs and make sure all nodes are connected. And so this is really nice as you come in through, is that as your layers are going in there, you can get some very complicated different setups nowadays, which we'll look at in just a second. And this just makes it really easy to start spinning this stuff up and trying out the different models. So when we look at Keras models, Keras model, we have a sequential model. Sequential model is a linear stack of layers where the previous layer leads into the next layer. And this, if you've done anything else, even like the sklearn with their neural networks and propagation and any of these setups, this should look familiar. You should have your input layer, it goes into your layer 1, layer 2, and then to the output layer. And it's useful for simple classifier or decoder models. And you can see down here we have the model equals a Keras sequential, and this is the actual code. You can see how easy it is. We have a layer that's dense, your layer 1. As an activation, they're using the ReLU in this particular example. And then you have your name layer 1, layer dense ReLU, name layer 2, and so forth. And they just feed right into each other. So it's really easy just to stack them, as you can see here, and it automatically takes care of everything else for you. And then there's a functional model. And this is really where things are at. This is new. Make sure you update your Keras, or you'll find yourself running this, doing the functional model. You'll run into an error code because this is a fairly new release. And it uses multi-input and multi-output model. The complex model, which forks into 2 or more branches. And you can see here we have our image inputs equals your Keras input shape equals 32 by 32 by 3. You have your dense layers, dense 64 activation ReLU. This should look similar to what you already saw before, but if you look at the graph on the right, it's going to be a lot easier to see what's going on. You have 2 different inputs. And one way you could think of this is maybe one of those is a small image and one of those is a full-sized image. And that feedback goes into, you might feed both of them into one node because it's looking for one thing, and then only into one node for the other one. And so you can start to get kind of an idea that there's a lot of use for this kind of split and this kind of setup. We have multiple information coming in, but the information's very different even though it overlaps. And you don't want it to send it through the same neural network. And they're finding that this trains faster and also has a better result depending on how you split the data up and how you fork the models coming down. And so in here we do have the two complex models coming in. We have our image inputs, which is a 32 by 32 by 3 or 3 channels, or 4 if you're having an alpha channel. You have your layers dense is 64 activation using the ReLU, very common. X equals dense inputs, X layers dense X64 activation equals ReLU, X outputs equals layers dense 10X, model equals cross model inputs equals inputs, outputs equals outputs, name equals minced model. So we add a little name on there. And again, this is this kind of split here. This is setting us up to have the input go into different areas. So if you're already looking at Keras, you probably already have this answer. What are neural networks? But it's always good to get on the same page, and for those people who don't fully understand neural networks, to dive into them a little bit or do a quick overview. Neural networks are deep learning algorithms modeled after the human brain. They use multiple neurons, which are mathematical operations, to break down and solve complex mathematical problems. And so just like the neuron, one neuron fires in and it fires out to all these other neurons, or nodes as we call them, and eventually they all come down to your output layer. And you can see here we have the really standard graph input layer, a hidden layer, and an output layer. One of the biggest parts of any data processing is your data pre-processing. So we always have to touch base on that. With a neural network, like many of these models, they're kind of, when you first start using them, they're like a black box. You put your data in, you train it, and you test it and see how good it was. And you have to pre-process that data because bad data in is bad outputs. So in data pre-processing, we will create our own data examples set with Keras. The data consists of a clinical trial conducted on 2,100 patients, ranging from ages 13 to 100, with the patients under 65 and the other half over 65 years of age. We want to find the possibility of a patient experiencing side effects due to their age. And you can think of this in today's world with COVID, what's going to happen on there. And we're going to go ahead and do an example of that in our live hands-on. Like I said, most of this you really need to have hands-on to understand. So let's go ahead and bring up our Anaconda and open that up and open up a Jupyter notebook for doing the Python code in. Now if you're not familiar with those, you can use pretty much any of your setups. I just like those for doing demos and showing people, especially shareholders. It really helps because it's a nice visual. So let me go ahead and flip over to our Anaconda. And the Anaconda has a lot of cool tools. They just added Data Lore and IBM Watson Studio Cloud into the Anaconda framework. But we'll be in the Jupyter Lab or Jupyter Notebook. I'm going to do Jupyter Notebook for this because I use the lab for like large projects with multiple pieces because it has multiple tabs, where the notebook will work fine for what we're doing. And this opens up in our browser window because that's how Jupyter Notebook is set to run. And we'll go under New, create a new Python 3, and it creates an untitled Python. We'll go ahead and give this a title, and we'll just call this Keras tutorial. And let's change that to a capital. There we go. We'll go ahead and just rename that. And the first thing we want to go ahead and do is get some pre-processing tools involved. And so we need to go ahead and import some stuff for that, like our NumPy, do some random number generation. I mentioned sklearn or your scikit. If you're installing sklearn, the sklearn stuff, it's scikit you want to look up. That should be a tool of anybody who is doing data science. If you're not familiar with the sklearn toolkit, it's huge, but there's so many things in there that we always go back to. And we want to go ahead and create some train labels and train samples for training our data. And then just a note of what we're actually doing in here. Let me go ahead and change this. This is kind of a fun thing you can do. We can change the code to Markdown. And then Markdown code is nice for doing examples once you've already built this. Our example data, we're going to do experimental. There we go. Experimental drug was tested on 2,100 individuals between 13 to 100 years of age. Half the participants are under 65, and 95% of participants are under 65. Experienced no side effects, while 95% of participants over 65 experienced side effects. So that's kind of where we're starting at. And this is just a real quick example, because we're going to do another one with a little bit more complicated information. And so we want to go ahead and generate our setup. So we want to do for I in range, and we want to go ahead and create, if you look here, we have random integers, train the labels, append. So we're just creating some random data. And let me go ahead and just run that. And so once we've created our random data, and I mean, you can certainly ask for a copy of the code from Simplilearn. They'll send you a copy of this, or you can zoom in on the video and see how we went ahead and did our train samples, append. And we're just using this. I do this kind of stuff all the time. I was running a thing on that had to do with errors following a bell-shaped curve on a standard distribution error. And so what do? I generate the data on a standard distribution error to see what it looks like and how my code processes it, since that was the baseline I was looking for. In this, we're just doing generating random data for our setup on here. And we could actually go in, print some of the data up. Let's just do this, print. We'll do train samples, and we'll just do the first 5 pieces of data in there to see what that looks like. And you can see the first 5 pieces of data in our train samples is 49, 85, 41, 68, 19. Just random numbers generated in there. That's all that is. And we generated significantly more than that. Let's see, 50 up here, 1,000. Yeah, so there's 1,000 here. 1,000 numbers we generated. And we could also, if we wanted to find that out, we can do a quick print the length of it. And so, or you could do a shape kind of thing, and if you're using NumPy, although the link for this is just fine. And there we go, it's actually 2,100, like we said in the demo setup in there. And then we want to go ahead and take our labels. Oh, that was our train labels. We also did samples, didn't we? So we could also print, do the same thing. Oh, labels. And let's change this to labels. And labels. And run that just to double check, and sure enough we have 2,100, and they're labeled 10, 10, 10. I guess that's if they have symptoms or not. 1 symptoms, 0 none. And so we want to go ahead and take our train labels and we'll convert it into a NumPy array, and the same thing with our samples. And let's go ahead and run that. And we also shuffle. This is just a neat feature you can do in NumPy right here. Put my drawing thing on, which I didn't have on earlier. I can take the data and I can shuffle it. So we have it just randomizes it. That's all that's doing. We've already randomized it, so it's kind of an overkill. It's not really necessary. But if you're doing a larger package where the data is coming in, and a lot of times it's organized somehow, and you want to randomize it just to make sure that you know, the input doesn't follow a certain pattern that might create a bias in your model. And we go ahead and create a scalar. The scalar range, minimum max scalar, feature range 0 to 1. And then we go ahead and scale the scaled train samples. So we're going to go ahead and fit and transform the data so it's nice and scaled. And that is the age. So you can see up here we have 49, 85, 41. We're just moving that so it's going to be between 0 and 1. And so this is true with any of your neural networks. You really want to convert the data to 0 and 1, otherwise you create a bias. So if you have like 100 creates a bias versus the math behind it gets really complicated. If you actually start multiplying stuff, there's a lot of multiplication and addition going on in there, that higher end value will eventually multiply down, and it will have a huge bias as to how the model fits it, and then it will not fit as well. And then one of the fun things we can do in Jupyter Notebook is that if you have a variable and you're not doing anything with it, and it's the last one on the line, it will automatically print. And we're just going to look at the first 5 samples on here. And so it's going to print the first 5 samples. And you can see, here we go, 0.9195, 0.791. So everything's between 0 and 1. And that just shows us that we scaled it properly and it looks good. It really helps a lot to do these kind of print-ups halfway through. You never know what's going to go on there. I don't know how many times I've gotten down and found out that the data sent to me that I thought was scaled was not. And then I have to go back and track it down and figure it out on there. So let's go ahead and create our artificial neural network. And for doing that, this is where we start diving into TensorFlow and Keras. TensorFlow, if you don't know the history of TensorFlow, it helps to jump into, we'll just use Wikipedia. Be careful, don't quote Wikipedia on these things because you get in trouble. But it's a good place to start. Back in 2011, Google Brain built Disbelief as a proprietary machine learning setup. TensorFlow became the open source for it. So TensorFlow was a Google product, and then it became open sourced, and now it's just become probably one of the de factos when it comes for neural networks as far as where we're at. So when you see the TensorFlow setup, it's got like a huge following. There are some other setups like the Scikit under the sklearn has their own little neural network, but the TensorFlow is the most robust one out there right now. And Keras sitting on top of it makes it a very powerful tool, so we can leverage both the Keras easiness in which we can build a sequential setup on top of TensorFlow. And so in here we're going to go ahead and do our input of TensorFlow, and then we have the rest of this is all Keras here from number 2 down. We're going to import from TensorFlow the Keras connection. And then you have your TensorFlow Keras models, import sequential. It's a specific kind of model. We'll look at that in just a second. If you remember from the files, that means it goes from one layer to the next layer to the next layer. There's no funky splits or anything like that. And then we have from TensorFlow Keras layers, we're going to import our activation and our dense layer. And we have our optimizer Atom. This is a big thing to be aware of, how you optimize your data. When you first do it, Atom's as good as any. Atom is usually, there's a number of optimizer out there. There's a couple of main ones, but Atom is usually assigned to bigger data. It works fine. Usually the lower data does it just fine, but Atom is probably the mostly used. But there are some more out there, and depending on what you're doing with your layers, your different layers might have different activations on them. And then finally down here you'll see our setup where we want to go ahead and use the metrics. And we're going to use the TensorFlow Keras metrics for categorical cross entropy. So we can see how everything performs when we're done. That's all that is. A lot of times you'll see us go back and forth between TensorFlow, and then Scikit has a lot of really good metrics also for measuring these things. Again, it's the end of the at the end of the story. How good does your model do? And we'll go ahead and load all that, and then comes the fun part. I actually like to spend hours messing with these things. And 4 lines of code. You're like, you're gonna spend hours on 4 lines of code? No, we don't spend hours on 4 lines of code. That's not what we're talking about when I say spend hours on 4 lines of code. What we have here, and I'm going to explain that in just a second, we have a model. And it's a sequential model. If you remember correctly, we mentioned the sequential up here where it goes from one layer to the next. And our first layer is going to be our input. It's going to be what they call dense, which is usually it's just dense, and then you have your input and your activation. How many units are coming in? We have 16. What's the shape? What's the activation? And this is where it gets interesting, because we have in here ReLU on 2 of these and softmax activation on 1 of these. There are so many different options for what these mean and how they function. How does the ReLU, how does the softmax function? And they do a lot of different things. We're not going to go into the activations in here. That is what really you spend hours doing, is looking at these different activations. And just some of it is just almost like you're playing with it like an artist. You start getting a feel for like a inverse tangent activation, or the tan-H activation. Takes up a huge processing amount, so you don't see it a lot. Yet it comes up with a better solution, especially when you're doing when you're analyzing Word documents and you're tokenizing the words. And so you'll see this shift from one to the other because you're both trying to build a better model. And if you're working on a huge data set, it'll crash the system. It'll just take too long to process. And then you see things like softmax. Softmax generates an interesting setup where a lot of these, when you talk about ReLU, oops, let me do this. ReLU, there we go. ReLU has a setup where if it's less than 0, it's 0, and then it goes up. And then you might have what they call lazy setup, where it has a slight negative to it so that the errors can translate better. Same thing with softmax. It has a slight laziness to it so that errors translate better. All these little details make a huge difference on your model. So one of the really cool things about data science that I like is you build your what they call you build to fail. And it's an interesting design setup. Oops, I forgot the end of my code here. The concept of build to fail is you want the model as a whole to work, so you can test your model out, so that you can do you can get to the end and you can do your, let's see, where was it? Overshot down here. You can test out the quality of your setup on there. And see, where did I do my TensorFlow? Oh, here we go. It was right above me. There we go. We start doing your cross entropy and stuff like that. Is you need a full functional set of code so that when you run it, you can then test your model out and say, hey, it's either this model works better than this model, and this is why. And then you can start swapping in these models. And so when I say I spend a huge amount of time on pre-processing data, it's probably 80% of your programming time. Well, between those two, it's like 80-20. You'll spend a lot of time on the models. Once you get the model down, once you get the whole code and the flow down set, depending on your data, your models get more and more robust as you start experimenting with different inputs, different data streams, and all kinds of things. And we can do a simple model summary here. Here's our sequential, here's our layer, our output, our parameter. This is one of the nice things about Keras is you can see right here, here's our sequential 1 model. Boom, 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 boom. Everything's set and clear and easy to read. So once we have our model built, the next thing we're going to want to do is we're going to go ahead and train that model. And so the next step is, of course, model training. And when we come in here, this a lot of times is just paired with the model because it's so straightforward. It's nice to print out the model setup so you can have a tracking. But here's our model. The keyword in Keras is compile, optimizer atom, learning rate, another term right there that we're just skipping right over that really becomes the meat of the setup is your learning rate. So whoops, I forgot that I had an arrow, but I'll just underline it. A lot of times the learning rate set to 0.01. Depending on what you're doing, this learning rate can overfit and underfit. So you'd want to look up I know we have a number of tutorials out on overfitting and underfitting that are really worth reading once you get to that point and understanding. And we have our loss, sparse categorical cross entropy. So this is going to tell Keras how far to go until it stops. And then we're looking for metrics of accuracy. So we'll go ahead and run that. And now that we've compiled our model, we want to go ahead and run it, fit it. So here's our model fit. We have our scaled train samples, our train labels, our validation split. In this case, we're going to use 10% of the data for validation. Batch size, another number you kind of play with. Not a huge difference as far as how it works, but it does affect how long it takes to run, and it can also affect the bias a little bit. Most of the time, though, a batch size is between 10 to 100, depending on just how much data you're processing in there. We want to go ahead and shuffle it. We're going to go through 30 epochs and put a verbose of 2. Let me just go ahead and run this. And you can see right here, here's our epoch, here's our training, here's our loss. Now, if you remember correctly up here, we set the loss. Let's see, where was it? Compiled our data. There we go, loss. So it's looking at the sparse categorical cross entropy. This tells us that as it goes, how much does the error go down? Is the best way to look at that. And you can see here, the lower the number, the better. It just keeps going down. And vice versa, accuracy we want. Let's see, where's my accuracy? Value accuracy at the end. And you can see 0.619, 0.69, 0.74, it's going up. We want the accuracy, would be ideal if it made it all the way to 1. But we also, the loss is more important because it's a balance. You can have 100% accuracy and your model doesn't work because it's overfitted. Again, you want to look up overfitting and underfitting models. And we went ahead and went through 30 epochs. It's always fun to kind of watch your code going. To be honest, I usually, the first time I run it, I'm like, oh, that's cool, I get to see what it does. And after the second time of running it, I'm like, I like to just not see that. And you can repress those, of course, in your code. Repress the warnings in the printing. And so the next step is going to be building a test set and predicting it now. So here we go. We want to go ahead and build our test set. And we have, just like we did our training set, a lot of times you just split your initial set up. But we'll go ahead and do a separate set on here. And this is just what we did above. There's no difference as far as the randomness that we're using to build this set on here. The only difference is that we already did our scalar up here. Well, that doesn't matter because the data is going to be across the same thing. But this should just be transform down here instead of fit transform. Because you don't want to refit your data on your testing data. There we go. And now we're just transforming it because you never want to transform the test data. Easy mistake to make, especially on an example like this where we're not doing, we're randomizing the data anyway, so it doesn't matter too much because we're not expecting something weird. And then we want to go ahead and do our predictions. The whole reason we built the model is we take our model, we predict, and we're going to do, here's our X-scale data, batch size 10, verbose, and now we have our predictions in here, and we could go ahead and do a, we'll print predictions, and then I guess I could just put down predictions in 5 so we can look at the first 5 of the predictions. And what we have here is we have our age and the prediction on this age versus what we think it's going to be, what we think is going to, they're going to have symptoms or not. And the first thing we notice is that's hard to read because we really want a yes/no answer. So we'll go ahead and just round off the predictions using the argmax, the numpy argmax for predictions. So it just goes to a 0, 1, and if you remember, this is a Jupyter Notebook, so I don't have to put the print. I can just put in rounded predictions, and we'll just do the first 5. And you can see here 0, 1, 0, 0, 0. So that's what the predictions are that we have coming out of this. Is no symptoms, symptoms, no symptoms, symptoms, no symptoms. And just as we were talking about at the beginning, we want to go ahead and take a look at this. There we go. Confusion matrices for accuracy check. Most important part, when you get down to the end of the story, how accurate is your model? Before you go and play with the model and see if you can get a better accuracy out of it. And for this, we'll go ahead and use the scikit, the sklearn metrics, scikit being where that comes from. Import confusion matrix, some iteration tools, and of course a nice matplot library. That makes a big difference, so it's always nice to have a nice graph to look at. Picture's worth 1,000 words. And then we'll go ahead and call it CM for confusion matrix, y true equals test labels, y predict rounded predictions. And we'll go ahead and load in our CM. And I'm not going to spend too much time on the plotting, going over the different plotting code. You can spend, we have whole tutorials on how to do your different plotting on there. But we do have here is we're going to do a plot confusion matrix. There's our CM, our classes, normalized false title confusion matrix. CMAP is going to be in blues. And you can see here we have to the nearest CMAP titles, all the different pieces, whether you put tick marks or not, the marks, the classes, the color bar. So a lot of different information on here as far as how we're doing the printing of the confusion matrix. You can also just dump the confusion matrix into a Seaborn and real quick get an output. It's worth knowing how to do all this when you're doing a presentation to the shareholders. You don't want to do this on the fly. You want to take the time to make it look really nice, like our guys in the back did. And let's go ahead and do this. Forgot to put together our CM plot labels. We'll go ahead and run that. And then we'll go ahead and call the definition for our mapping. And you can see here plot confusion matrix. That's the little script we just wrote. And we're going to dump our data into it. So our confusion matrix, our classes, title confusion matrix. And let's just go ahead and run that. And you can see here we have our basic setup. No side effects 195, had side effects 200, no side effects that had side effects. So we predicted the 10 of them who actually had side effects. And that's pretty good. I mean, I don't know about you, but you know, that's 5% error on this. And this is because there's 200 here. That's where I get 5% is. Divide these both by 2 and you get 5 out of 100. You can do the same kind of math up here. Not as quick on the fly because it's 15 and 195. Not an easily rounded number. But you can see here where they have 15 people who predicted to have with the no side effects but had side effects kind of set up on there. And these confusion matrix are so important at the end of the day. This is really where you show whatever you're working on comes up, and you can actually show them, hey, this is how good we are or not, how messed up it is. So this was I spent a lot of time on some of the parts, but you can see here is really simple. We did the random generation of data, but when we actually built the model coming up here, here's our model summary. And we just have the layers on here that we built with our model on this. And then we went ahead and trained it and ran the prediction. Now we can get a lot more complicated. Let me flip back on over here because we're going to do another demo. So that was our basic introduction to it. We talked about the... oops, here we go. Okay, so implementing a neural network with Keras. After creating our samples and labels, we need to create our Keras neural network model. We will be working with a sequential model which has 3 layers. And this is what we did. We had our input layer, our hidden layers, and our output layers. And you can see the input layer coming in was the age factor. We had our hidden layer, and then we had the output. Are you going to have symptoms or not? So we're going to go ahead and go with something a little bit more complicated. Training our model is a 2-step process. We first compile our model and then we train it in our training data set. So we have compiling. Compiling converts the code into a form of understandable by machine. We used the atom in the last example, a gradient descent algorithm, to optimize the model, and then we trained our model, which means it let it learn on training data. And I actually had a little backwards there, but this is what we just did. Is if you remember from our code we just had, oops, let me go back here. Here's our model that we created, summarized. We come down here and we compile it. So it tells it, hey, we're ready to build this model and use it. And then we train it. And this is the part where we go ahead and fit our model and put that information in here, and it goes through the training on there. And of course we scaled the data, which was really important to do. And then you saw we did the creating a confusion matrix with Keras. As we are performing classifications on our data, we need a confusion matrix to check the results. A confusion matrix breaks down the various misclassifications as well as correct classifications to get the accuracy. And so you can see here, this is what we did with the true positive, false positive, true negative, false negative. And that is what we went over. Let me just scroll down here. On the end, we printed it out, and you can see we have a nice printout of our confusion matrix with the true positive, false negative, true negative. And so the blue ones, we want those to be the biggest numbers because those are the better side. And then we have our false predictions on here as far as this one. So it had no side effects, but we predicted, let's see, no side effects predicting side effects and vice versa.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Now, saving and loading models with Keras. We're going to dive into a more complicated demo. And you're going to say, oh, that was a lot of complication before. Well, if you broke it down, we randomized some data, we created the Keras setup, we compiled it, we trained it, we predicted, and we ran our matrix. So we're going to dive into something a little bit more fun. Is we're going to do a face mask detection with Keras. So we're going to build a Keras model to check if a person is wearing a mask or not in real time. And this might be important if you're at the front of a store. This is something today which is might be very useful as far as some of our, making sure people are safe. And so we're going to look at mask and no mask. And let's start with a little bit on the data. And so in my data I have with a mask, and you can see they just have a number of images showing the people in masks. And again, if you want some of this information, contact Simplilearn, and they can send you some of the information as far as people with and without masks, so you can try it on your own. And this is just such a wonderful example of this setup on here. So before I dive into the mask detection, talking about being in the current with COVID and seeing if people are wearing masks, this particular example I had to go ahead and update to a Python 3.8 version. It might run in a 3.7, I'm not sure. I kind of skipped 3.7 and installed 3.8. So I'll be running in a Python 3.8, and then you also want to make sure your TensorFlow is up to date, because they call functional layers, that's where they split, if you remember correctly from back. Let's take a look at this. Remember from here, the functional model and a functional layer allows us to feed in the different layers into different nodes into different layers and split them. Very powerful tool, very popular right now in the edge of where things are with neural networks and creating a better model. So I've upgraded to Python 3.8, and let's go ahead and open that up and go through our next example, which includes multiple layers, programming it to recognize whether someone wears a mask or not, and then saving that model so we can use it in real time. So we're actually almost a full end-to-end development of a product here. Of course, this is a very simplified version, and there'd be a lot more to it. You'd also have to do recognizing whether it's someone's face or not. All kinds of other things go into this. So let's go ahead and jump into that code, and we'll open up a new Python 3. Oops, Python 3. It's working on it. There we go. And then we want to go ahead and train our mask. We'll just call this train mask. And we want to go ahead and train mask and save it. So it's train mask detection, not to be confused with masking data. A little bit different. We're actually talking about a physical mask on your face. And then from the cross standpoint, we got a lot of imports to do here. And I'm not going to dig too deep on the imports. We're just going to go ahead and notice a few of them. So we have in here, oops, let me go Alt-D, there we go. Have something to draw with a little bit here. We have our image processing, and the image processing right here, let me underline that, deals with how do we bring images in, because most images are like a square grid, and then each value in there has 3 values for the 3 different colors. Keras and TensorFlow do a really good job of working with that, so you don't have to do all the heavy listening and figuring out what's going to go on. We have the mobile net average pooling, 2D. This again is how do we deal with the images and pooling them. Dropout's a cool thing worth looking up. If you haven't, as you get more and more into Keras and TensorFlow, it'll auto drop out certain nodes. That way you'll get a better, the nodes just kind of die. They find that they actually create more of a bias than a help, and they also add processing time, so they remove them. And then we have our flatten. That's where you take that huge array with the 3 different colors and you find a way to flatten it so it's just a one-dimensional array instead of a 2 by 2 by 3. Dense input, we did that in the other one, so that should look a little familiar. Oops, there we go. Our input, our model, again, these are things we had on the last one. Here's our optimizer with our atom. We have some pre-processing on the input that goes along with bringing in the data in. More pre-processing with image to array, loading the image. This stuff is so nice. It looks like a lot of work, so you have to import all these different modules in here. But the truth is it does everything for you. You're not doing a lot of pre-processing. You're letting the software do the pre-processing. And we're going to be working with the setting something to categorical. Again, that's just a conversion from a number to a category. 0, 1 doesn't really mean anything. It's like true, false. Label binarizer, the same thing. We're changing our labels around. And then there's our train test split classification report. Our IM utilities, let me just go ahead and scroll down here a notch for these. This is something a little different going on down here. This is not part of the TensorFlow or the sklearn. This is the scikit setup and TensorFlow above. The path, this is part of OpenCV, and we'll actually have another tutorial going out with the OpenCV. So if you want to know more about OpenCV, you'll get a glance on it in this software, especially the second piece when we reload up the data and hook it up to a video camera. We're going to do that on this round. But this is part of the OpenCV thing, and you'll see CV2 is usually how that's referenced. But the IM utilities has to do with how do you rotate pictures around and stuff like that, and resize them. And then the matplot library for plotting, because it's nice to have a graph, tells us how good we're doing, and then of course our numpy numbers array and just a straight OS access. Wow, so that was a lot of imports. Like I said, I'm not going to spend, I spent a little time going through them, but we didn't want to go too much into them. And then I'm going to create some variables that we need to go ahead and initialize. We have the learning rate, number of epochs to train for, and the batch size. And if you remember correctly, we talked about the learning rate to the -4.00001. A lot of times it's 0.001 or 0.001. Usually it's in that variation depending on what you're doing and how many epochs, and they kind of play with the epochs. The epochs is how many times we're going to go through all the data. Now I have it as 2. The actual setup is for 20, and 20 works great. The reason I have it for 2 is it takes a long time to process. One of the downsides of Jupyter is that Jupyter isolates it to a single kernel. So even though I'm on an 8-core processor with 16 dedicated threads, only one thread is running on this, no matter what. So it doesn't matter. So it takes a lot longer to run, even though TensorFlow really scales up nicely. And the batch size is how many pictures do we load at once and process. Again, those are numbers you have to learn to play with depending on your data and what's coming in. And the last thing we want to go ahead and do is there's a directory with a data set we're going to run. And this just has images of masks and not masks. And if we go in here, you'll see data set. And then you have pictures with masks. They're just images of people with masks on their face. And then we have the opposite. Let me go back up here. Without masks. So it's pretty straightforward. They look kind of askew because they tried to format them into very similar setup on there. So they're mostly squares. You'll see some that are slightly different on here. And that's kind of an important thing to do on a lot of these data sets. Get them as close as you can to each other. And we actually will run in this processing of images up here, and the cross layers and importing and dealing with images. It does such a wonderful job of converting these that a lot of it we don't have to do a whole lot with. So you have a couple things going on there. And so we're now going to be, this is now loading the images, and let me see. And we'll go ahead and create data and labels. Here's our here's the features going in, which is going to be our pictures, and our labels going out. And then for categories in our list directory, and if you remember, I just flashed that at you. It had face mask or no face mask. Those are the two options. And we're just going to load into that. We're going to append the image itself and the labels. So we're just going to create a huge array. And you can see right now this could be an issue if you had more data. At some point, thankfully I have a 32 gig hard drive or RAM. Even that, you could do with a lot less of that. Probably under 16 or even 8 gigs would easily load all this stuff. And there's a conversion going on in here. I told you about how we are going to convert the size of the image so it resizes all the images. And that way our data is all identical the way it comes in. And you can see here with our labels, we have without mask, without mask, without mask. The other one would be with mask. Those are the two that we have going in there. And then we need to change it to the one-hot encoding. And this is going to take our, up here we had, what was it, labels and data. We want the labels to be categorical. So we're going to take labels and change it to categorical, and our labels then equal a categorical list. We'll run that. And again, if we do labels and we just do the last or the first 10, let's do the last 10 just because minus 10 to the end. There we go. Just so we can see what the other side looks like. We now have 1. That means they have a mask. 1, 0, 1, 0, so on. 1 being they have a mask, and 0 no mask. And if we did this in reverse, I just realized that this might not make sense if you've never done this before. Let me run this. 0, 1. So 0 is, do they have a mask on? 0. Do they not have a mask on? 1. So this is the same as what we saw up here without mask. 1 equals, the second value is without mask. So with mask, without mask. And that's just with any of your data processing, we can't really, if you have a 0, 1 output, it causes issues as far as training and setting it up. So we always want to use a one-hot encoder if the values are not actual linear value or regression values. They're not actual numbers if they represent a thing. And so now we need to go ahead and do our train X, test X, train Y, test Y, train split test data. And we'll go ahead and make sure it's going to be random, and we'll take 20% of it for testing and the rest for setting it up as far as training their model. This is something that's become so cool. When they're training these sets, they realize we can augment the data. What does augment mean? Well, if I rotate the data around and I zoom in, I zoom out, I rotate it, share it a little bit, flip it horizontally, fill mode, as I do all these different things to the data, it is able to, it's kind of like increasing the number of samples I have. So if I have all these perfect samples, what happens when we only have part of the face, or the face is tilted sideways, or all those little shifts cause a problem? if you're doing just a standard set of data. So we're going to create an augment in our image data generator, which is going to rotate, zoom, and do all kinds of cool things. And this is worth looking up, this image data generator and all the different features it has. A lot of times, the first time through my models, I'll leave that out because I want to make sure there's a thing what we call build to fail, which is just cool to know. You build the whole process, and then you start adding these different things in so that you can better train your model. And so we go and run this, and then we're going to load. And then we need to go ahead, and you probably would have gotten an error if you hadn't put this piece in right here. I haven't run it myself because the guys in the back did this. But we take our base model, and one of the things we want to do is we want to do a mobile net v2. And this is a big thing right here. Include the top equals false. A lot of data comes in with a label on the top row. So we want to make sure that that is not the case. And then the construction of the head of the model that will be placed on the top of the base model. We want to go ahead and set that up. And you'll see a warning here. I'm kind of ignoring the warning because it has to do with the size of the pictures and the weights for input shape. So it'll switch things to defaults, just saying, hey, we're going to auto shape some of this stuff for you. You should be aware that with this kind of imagery, we're already augmenting it by moving it around and flipping it and doing all kinds of things to it. So that's not a bad thing in this. But in other data, it might be if you're working in a different domain. And so we're going to go back here, and we have our base model. We're going to do our head model equals our base model output. And what we got here is we have an average pooling 2D, pool size 7.7 head model. Head model flatten. So we're flattening the data. So this is all processing and flattening the images. And the pooling has to do with some of the ways it can process some of the data. We'll look at that a little bit when we get down to the lower level and is processing it. And then we have our dense. We've already talked a little bit about a dense, just what you think about. And then the head model has a dropout of 0.5. What we can do with a dropout, the dropout says that we're going to drop out a certain amount of nodes while training. So when you actually use the model, it will use all the nodes. But this drops certain ones out, and it helps stop biases from forming. So it's really a cool feature in here. They discovered this a while back. We have another dense mode, and this time we're using softmax activation. Lots of different activation options here. Softmax is a real popular one for a lot of things, and so is ReLU. And we could do a whole talk on activation formulas and what their different uses are and how they work. When you first start out, you'll use mostly the ReLU and the softmax for a lot of them, just because they're some of the basic setups. It's a good place to start. And then we have our model equals model, inputs equals base model dot input, outputs equals head model. So again, we're still building our model here. We'll go ahead and run that. And then we're going to loop over all the layers in the base model and freeze them so they will not be updated during the first training process. So for layer and base model layers, layers.trainable equals false. A lot of times when you go through your data, you want to kind of jump in partway through. I'm not sure why in the back they did this for this particular example, but I do this a lot when I'm working with series and specifically in stock data. I want it to iterate through the first set of 30 data before it does anything. I would have to look deeper to see why they froze it on this particular one. And then we're going to compile our model. So compiling the model, atom, init, layer, decay, initial learning rate over epochs, and we go ahead and compile. Our loss is going to be the binary cross entropy, which will have that print out. Optimizer for opt, metrics is accuracy. Same thing we had before. Not a huge jump as far as the previous code. And then we go ahead and we've gone through all this, and now we need to go ahead and fit our model. So train the head of the network, print info training head, run. Now I skipped a little time because you'll see the run time here is at 80 seconds per epoch. It takes a couple minutes for it to get through on a single kernel. One of the things I want you to notice on here while it's finishing the processing is that we have up here our augment going on. So anytime the train X and train Y go in, there's some randomness going on there, and is jiggling it around what's going into our setup. Of course, we're batch sizing it, so it's going through whatever we set for the batch values, how many we process at a time. And then we have the steps per epoch, the train X, the batch size, validation data. Here's our test X and test Y, where we're sending that in. And this, again, it's validation. One of the important things to know about validation is when both our training data and our test data have about the same accuracy, that's when you want to stop. That means that our model isn't biased. If you have a higher accuracy on your testing, you've trained it, and your accuracy is higher on your actual test data, then something in there is probably has a bias and it's overfitted. So that's what this is really about right here with the validation data and validation steps. So it looks like let me go ahead and see if it's done processing. It looks like we've gone ahead and gone through 2 epochs. Again, you could run this through about 20 with this amount of data, and it would give you a nice refined model at the end. We're going to stop at 2 because I really don't want to sit around all afternoon, and I'm running this on a single thread. So now that we've done this, we're going to need to evaluate our model and see how good it is. And to do that, we need to go ahead and make our predictions. These are our predictions on our test X to see what it thinks are going to be. So now it's going to be evaluating the network, and then we'll go ahead and go down here, and we will need to turn the indexing, because remember it's either 0 or 1. It's 0, 1, 0, 1. So you have 2 outputs: not wearing a mask, not wearing a mask. And so we need to go ahead and take that argument at the end and change those predictions to a 0 or 1 coming out. And then to finish that off, we want to go ahead and let me just put this right in here and do it all in one shot. We want to show a nicely formatted classification report so we can see what that looks like on here. And there we have it. We have our precision. It's 97% with a mask. There's our F1 score, support without a mask, 97%. So that's pretty high setup on there. 3 people are going to sneak into the store who are without a mask and thinks they have a mask, and there's going to be 3 people with a mask that's going to flag the person at the front to go, oh, hey, look at this person, he might not have a mask. That's I guess if it's a setup in front of a store. So there you have it. And of course, one of the other cool things about this is if someone's walking into the store and you take multiple pictures of them, this is just it would be a way of flagging, and then you can take that average of those pictures and make sure they match or don't match if you're on the back end. And this is an important step because this is just cool. I love doing this stuff. So we're going to go ahead and take our model and we're going to save it. So model save maskdetector.model. We're going to give it a name. We're going to save the format. In this case, we're going to use the H5 format. And so this model we just programmed has just been saved. So now I can load it up into, say, another program. What's cool about this is, let's say I want to have somebody work on the other part of the program. Well, I just saved the model. They upload the model. Now they can use it for whatever. And then if I get more information and we start working with that, at some point I might want to update this model. Make a better model. And this is true of so many things, where I take this model and maybe I'm running a prediction on making money for a company, and as my model gets better, I want to keep updating it, and then it's real easy just to push that out to the actual end user. And here we have a nice graph. You can see the training loss and accuracy as we go through the epochs. We only did only shows just the one epoch coming in here, but you can see right here as the value loss, train accuracy, and value accuracy start switching and they start converging. And you'll hear converging. This is the convergence they're talking about when they say I know when I work in the scikit with sklearn neural networks, This is what they're talking about, a convergence, is our loss and our accuracy come together, and also up here. And this is why I'd run it more than just 2 epochs. As you can see, they still haven't converged all the way. So that would be a cue for me to keep going. But what we want to do is we want to go ahead and create a new Python 3 program. And we just did our train mask. So now we're going to go ahead and import that and use it and show you in a live action. Get a view of both myself in the afternoon along with my background of an office, which is in the middle still of reconstruction for another month. And we'll call this mask detector. And then we're going to grab a bunch of a few items coming in. We have our MobileNet v2 import preprocessing input, because we're still going to need that. We still have our TensorFlow image to array. We have our load model. That's where most of the stuff's going on. This is our CV2 or OpenCV. Again, I'm not going to dig too deep into that. We're going to flash a little OpenCV code at you, and we actually have a tutorial on that coming out. Our NumPy array, our IM utilities, which is part of the OpenCV or CV2 setup. And then we have, of course, time and just our operating system. So those are the things we're going to go ahead and set up on here. And then we're going to create, this takes just a moment. Our module here, which is going to do all the heavy lifting. So we're going to detect and predict a mask. We have frame, FaceNet, MaskNet. These are going to be generated by our OpenCV. We have our frame coming in, and then we want to go ahead and create a mask around the face. It's going to try to detect the face and then set that up so we know what we're going to be processing through our model. And then there's a frame shape here. This is just our height versus width. That's all HW stands for. They've called it blob, which is a CV2 DNN blob form image frame. So this is reformatting this frame that's going to be coming in literally from my camera. And we'll show you that in a minute, that little piece of code that shoots that in here. And we're going to pass the blob through the network and obtain the face detections. So FaceNet.setImport blob, detections FaceNet forward, print detections shape. So this is what's going on here. This is that model we just created. We're going to send that in there, and I'll show you in a second where that is, but it's going to be under FaceNet. And then we go ahead and initialize our list of faces, their corresponding locations, and the list of predictions from our face mask network. We're going to loop over the detections, and this is a little bit more work than you think as far as looking for different faces. What happens if you have a crowd of faces? So we're looping through the detections and the shapes going through here. And probability associated with the detection. Here's our confidence of detections. We're going to filter out weak detection by ensuring the confidence is greater than the minimum confidence. So we've set it, remember, 0 to 1, so 0.5 would be our minimal confidence, probably is pretty good. And then we're going to put in compute bounding boxes for the object. If I'm zipping through this, it's because we're going to do an OpenCV, and I really want to stick to just the Keras part. And so I'm just kind of jumping through all this code. You can get a copy of this code from Simplilearn and take it apart, or look for the OpenCV coming out. And we'll create a box. The box sets it around the image. Ensure the bounding boxes fall within the dimensions of the frame. So we create a box around what we hope is going to be the face. Extract the face, ROI, convert it from BGR to RGB channel. Again, this is an OpenCV issue. Not really an issue, but it has to do with the order. I don't know how many times I've forgotten to check the order colors when working with OpenCV. Because there's all kinds of fun things when red becomes blue and blue becomes red. And we're going to go ahead and resize it, process it, frame it, face frame setup. Again, the face, the CV2 color, we're going to convert it. We're going to resize it, image to array, pre-process the input. pin the face, locate face, start X, start Y, and X. Boy, that was just a huge amount, and I skipped over a ton of it, but the bottom line is we're building a box around the face, and that box, because the OpenCV does a decent job of finding the face, and that box is going to go in there and see, hey, does this person have a mask on it? And so that's what all this is doing on here. And then finally we get down to this where it says predictions equals masknet.predict faces batch size 32. So these different images where we're guessing where the face is are then going to go through and generate an array of faces, if you will, and we're going to look through and say, does this face have a mask on it? And that's what's going right here is our prediction. That's the big thing that we're working for. And then we return the locations and the predictions. The location just tells where on the picture it is, and then the prediction tells us what it is. Is it a mask or is it not a mask? Alright, so we've loaded that all up. So we're going to load our serialized face detector model from disk. And we have the path that it was saved in. Obviously you're going to put it in a different path depending on where you have it or however you want to do it and how you saved it on the last one where we trained it. And then we have our weights path. And so finally our face net, here it is, equals cv2.dnn.readnet prototext path weights path. And we're going to load that up on here. So let me go ahead and run that. And then we also need to, I'll just put it right down here. I always hate separating these things in there. And then we're going to load the actual mask detector model from disk. This is the model that we saved. So let's go ahead and run that on there also. So this is pulling in all the different pieces we need for our model. And then the next part is we're going to open up our video. And this is just kind of fun because it's all part of the OpenCV video setup. And let me just put this all in as one. There we go. So we're going to go ahead and open up our video. We're going to start it and we're going to run it until we're done. And this is where we get some real kind of live action stuff, which is fun. This is what I like working about with images and videos, is that when you start working with images and videos, it's all right there in front of you. It's visual and you can see what's going on. So we're going to start our video streaming. This is grabbing our video stream source 0 start. That means it's grabbing my main camera I have hooked up. And then starting video, you're going to print it out. Here's our video source equals 0 start. Loop over the frames from the video stream. Oops, a little redundancy there. Let me close. I'll just leave it. That's how they had it in the code. So while true, we're going to grab the frame from the threaded video stream and resize it to have the maximum width of 400 pixels. So here's our frame. We're going to read it from our visual stream. We're going to resize it. And then we're returning. Remember, we returned from our procedure the location and the prediction. So detect and predict mask. We're sending it the frame. We're sending it the face net and the mask net. So we're sending all the different pieces that say this is what's going through on here. And then it returns our location and predictions, and then for our box and predictions in the location and predictions. And the box is again, this is an OpenCV set that says, hey, this is a box coming in from the location, because you have the two different points on there. And then we're going to unpack the box and predictions, and we're going to go ahead and do mask without a mask equals prediction. We're going to create our label, no mask. We're going to create color if the label equals mask L00225. And this is going to make a lot more sense when I hit the run button here. But we have the probability of the label. We're going to display the label and bounding box rectangle on the output frame. And then we're going to go ahead and show the output from the frame, CV2 IM show frame. And then the key equals CV2 wait key 1. We're just going to wait till the next one comes through from our feed. And we're going to do this until we hit the stop button pretty much. So are you ready for this? Let's see if it works. We've distributed our model. We've loaded it up into our distributed code here. We've got it hooked into our camera. And we're going to go ahead and run it. And there it goes. It's going to be running, and we can see the data coming down here, and we're waiting for the pop-up. And there I am in my office with my funky headset on. And you can see in the background my unfinished wall, and it says up here, no mask. Oh no, I don't have a mask on. I wonder if I cover my mouth, what would happen? You can see my no mask goes down a little bit. I wish I'd brought a mask into my office. It's up at the house. But you can see here that this says, there's a 95, 98% chance that I don't have a mask on. And it's true, I don't have a mask on right now. And this could be distributed. This is actually an excellent little piece of script that you could start, you install somewhere on a video feed on a security camera or something, and then you'd have this really neat setup saying, hey, do you have a mask on when you enter a store or public transportation or whatever it is where they're required to wear a mask. Let me go ahead and stop that. Now, if you want a copy of this code, definitely give us a holler. We will be going into OpenCV in another one, so I skipped a lot of the OpenCV code in here as far as going into detail. Really focusing on the Keras, saving the model, uploading the model, and then processing a streaming video through it so you can see that the model works. We actually have this working model that hooks into the video camera, which is just pretty cool and a lot of fun. So I told you we're going to dive in and really roll up our sleeve and do a lot of coding today. We did the basic demo up above for just pulling in a Keras, and then we went into a Keras model where we pulled in data to see whether someone was wearing a mask or not. So very useful in today's world as far as a fully running application.
Sequential models in Keras. So what is Keras? Keras is a high-level Python deep learning API, which is used for easy implementation of neural networks. It has multiple low-level backends like TensorFlow, Thano, PyTorch, etc., which are used for fast computation. So you could think of this as Keras being almost its own little programming language, and then it sits on neural networks. In this case, the ones listed were TensorFlow, Thano, and PyTorch, which can all integrate with the Keras model. This makes it very diverse and also makes it very easy to use and switch around with different things. Keras is very user-friendly as far as neural network software goes as a high-level API. Computational graphs. So computational graphs are really the heart and soul of neural networks. We talk about a computational graph. They are a visual representation of expressing and evaluating mathematical equations. The nodes and data flow in a graph correspond to mathematical operations and variables. You'll hear a lot, some of the terms you might hear are node and edge, the edge being the data flow in this case. It could also represent an actual value. They have, I think in Spark they have a graph X, which works just on computing edges. There's all kinds of stuff that has evolved from computational graphs. We're focusing just on Keras and on neural networks. So we're not going to go into great detail on everything a computational graph does. It is a core component of a neural network is what's important to know on this. So Keras offers a Python user-friendly front end while maintaining a strong computation power by using a low-level API like TensorFlow, PyTorch, etc., which use computational graphs as a backend. So one, this allows for abstraction of complex problems while specifying control flow. If you've ever looked at some of the backend or the original versions of TensorFlow, it's really a nightmare. You have all these different settings you have to put in there and create. It's a lot of back-end programming. This is like the old computers when you had to tell it how to dispose of a variable and how to properly reallocate the memory for use. All that is covered nowadays in our higher level programming. Well, this is the same thing with Keras, is it covers a lot of this stuff and does things for you that you could spend hours on just trying to figure out. It's useful for calculating derivatives by using backpropagation. We're definitely not going to teach a class on derivatives in this little video, but understanding a derivative is the rate of change. So if you have a particular function you're using in your neural network, a lot of them is just simple y equals mx plus b, your Euclidean geometry where you just have a simple slope times the intercept. And they get very complicated. They have the inverse tangent function for activation as opposed to just a linear Euclidean model. And you can think about this as you have your data coming in and you have to alter it somehow. Well, you alter it going down to get an answer, you end up with an error, and that error goes back up, and you have to have that back propagation with the derivative. You want to know how it changed so that you can figure out how to adjust it for the error. A lot of that's hidden, so you don't even have to worry about it with Keras. And in today's Keras, it'll even, if you create your own formula for computing an answer, it will automatically compute the derivative for you in a lot of cases. It's easier to implement distributed computation. So Keras is a really nice way to package it and get it off on different computers and share it. And it allows parallelism, which means that two operations can run simultaneously. So as we start developing these backends, it can do all kinds of cool things and utilize multiple cores, GPUs on a computer to get that parallel processing up. What are neural networks? Well, like I said, there are already, we talked about in computational edges, you have a node and you have a connection, or your edge. So neural networks are algorithms fashioned after the human brain, which contain multiple layers. Each layer contains a node called a neuron, which performs a mathematical operation. They break down complex problems into simple operations. So an input layer takes in our data and pre-processes it. When we talk about pre-processing, when you're dealing with neural networks, you usually have to pre-process your data so that it's between -1 and 1 or 0 and 1 into some kind of value that's usable. That occurs before it gets to the neural network. In fact, 80% of data science is usually in prepping that data and getting it ready for your different models. 2, you have hidden layer performs a nonlinear transformation of input. Now it can do a linear transformation. It can use just a basic Euclidean geometry, and you could think of a node adding all the different connections coming in. So each connection would have a weight, and then it would add to that weight plus an intercept in the node itself. So you can actually use Euclidean geometry. But a lot of these get really complicated. They have all these different formulas, and they're really cool to look at. But when you start looking at them, look at how they work. You really don't need to know the high math behind it to figure them out and figure out what they're doing, which is really cool. That means a lot of people can use this without having to go get a PhD in mathematics. Number 3, the output layer takes the results from hidden layer, transforms them, and gives a final output. So sequential models. So what makes this a sequential model? Sequential models are linear stacks of layers where one layer leads to the next. It is simple and easy to implement, and you just have to make sure that the previous layer is the input to the next layer. So you have used for plain stack of layers where each layer has one input and one output tensor. And this is what TensorFlow is named after, is each one of these layers is like a tensor. Each node is a tensor, and then the layer is also considered a tensor of values. And it's used for simple classifier, declassifier models. It's also used for regression models too. So it's not just about this is something, this is a teapot, this is a cat, this is a dog. It's also used for generating the actual values. You know, this is worth $10, that's worth $30. The weather's going to be 90 degrees out or whatever it is. So you can use it for both classifier and declassifier models. And one more note when we talk about sequential models. The term sequential is used a lot, and it's used in different areas and different notations when you're in data science. So when we talk about time series, we'll talk about sequential. That is something very different. Sequential in this case means it goes from the input to layer 1 to layer 2 to the output. So it's very directional. It's important to note this because if you have a sequential model, can you have a non-sequential model? And the answer is yes. If you master the basics of a sequential model, you can just as easily have another model that shares layers. You can have another model where you have an input coming in and it splits. And then you have one set that's doing one set of nodes. Maybe they're doing a yes-no kind of node, where it's either putting out a 0 or a 1, a classifier. And the other one might be regression. It's just processing numbers, and then you recombine them for the output. That's what they call the Keras API. So there's a lot of different availabilities in here, and all kinds of cool things you can do as far as encoding and decoding and all kinds of things. And you can share layers and things like that. We're just focusing on the basic cross model with the sequential model. So let's dive into the meat of the matter. Let's do a demo on here. Today's demo, in this demo, we'll be performing flower classification using sequential model and cross. And we'll use our model to classify between 5 different types of flowers. Now, for this demo, and you can do this demo on whatever platform you want, or whatever user interface for developing Python, I'm actually using Anaconda, and then I'm using Jupyter Notebooks to develop in. And if you're not familiar with this, you can go under Environment. Once you've created an environment, you can come in here to open a terminal window. And if you don't have the different modules in here, you can do your Conda install, whatever module it is. Just happened that this particular setup didn't have a Seaborn in it, which I already installed. So here's our Anaconda, and then I'm going to go back and start up my Jupyter Notebook, where I already created a new Python project, Python 3. I'm in Python 3.8 on this particular one. Sequential model for flowers. So lots of fun there. So we're going to jump right into this. The first thing is to make sure you have all your modules installed. So if you don't have NumPy, Pandas, Matplotlib, and Seaborn in the Keras, and sklearn, or Scikit, it's not actually sklearn, you'll need to go ahead and install all of those. Now, having done this for years and having switched environments and doing different things, I get all my imports done, and then we just run it, and if we get an error, we know we have to go back and install something. Right off the bat, though, we have NumPy, Pandas, Matplotlib, Seaborn. These are built on top of each other. Pandas, the data frame, and built on top of NumPy, the data array. And then we bring in our sklearn, or Scikit. This is the Scikit setup, S-C-I-K-I-T. Even though you use sklearn to bring it in, it's a Scikit. And then our Keras. We have our pre-processing the images, image data generator, our model. This is our basic model, our sequential model. And then we bring in from Keras layers, import dents, optimizers. These optimizers, a lot of them already come in. These are your different optimizers, and it's almost, a lot of this is so automatic now. Atom is a lot of times the default because you're dealing with a large data. And then we get our SGD, which is smaller data, does better on smaller pieces of data. And I'm not going to go into all of these different optimizers. We didn't even use these in the actual demo. You just have to be aware that they are different optimizers. And the more you dig into these models, you'll hit a point where you do need to play with these a little bit. But for the most part, leave it at the default when you're first starting out. And we're doing just the sequential. You'll see here layers dense. And then if we come down a little bit more, when they put this together and they're running the dense layers, you'll also see they have dropout, they have flatten, they have activation, they have the convolutional layer 2D, max pooling 2D, batch normalization. What are all these layers? And when we get to the model, we're going to talk about them. A lot of times when you're just starting, you can just import cross.layers, and then you have your dropout, your flatten, your convolutional neural network 2D. And we'll cover what these do in the actual example when we get down there. What I want you to take from here, though, is you need to run your imports and load your different aspects of this. And, of course, your TensorFlow TF, because this is all built on TensorFlow. And then finally, import random as RN, just for random generation. And then we get down here, we have our CV2. That is your open image, or your open CV, they call it, for processing images. That's what the CV2 is. We have our TQDM. The TQDM is for is a progress bar, just a fancy way of adding. When you're running a process, you can view the bar going across in the Jupyter setup. Not really necessary, but it's kind of fun to have. We want to be able to shuffle some files. Again, these are all different things. PIL is another image processor. It goes with the CV2. A lot of times you'll see both of those. And so we run those. We've got to bring them all in. And the next thing is to set up our directories. And so when we come into the directories, there's an important thing to note on here, other than we're looking at a lot of flowers, which is fun. Is when we get down here, we have our directory archive flowers. That just happens to be where the different files for different flowers are put in. We're denoting an X and a Z. And the X is the date of the image, and the Z is the tag for it. What kind of flower is this? And the image size is really important because we have to resize everything. If you have a neural network, and if you remember from our neural networks, let me flip back to that slide. When we look at this slide, we have two input nodes here. With an image, you have an input node depending on how you set it up for each pixel. And that pixel has 3 different color schemes usually in it, sometimes 4. So if you have a picture that's 150 by 150, you multiply 150 times 150 times 3. That's how many nodes, input layers coming in. I mean, so this is a massive input. A lot of times you think, oh yeah, it's just a small amount of data or something like that. No, it's a full image coming in. Then you have your hidden layers. A lot of times they match what the image size is coming in. So each one of those is also just as big. And then we get down to just a single output. So that's kind of a thing to note in here, what's going on behind the scenes. And of course, each one of these layers has a lot of processes and stuff going on. And then we have our different directories on here. Let me go ahead and run that. So I'm just setting the directories. That's all this is. Archive flowers, daisy, sunflower, tulip, dandelion, rose. Just our different directories that we're going to be looking at. And then we want to go ahead and we need to assign labels. Remember, we defined X and Z. So we're just going to create a definition here. And the first thing is return flower type. Okay. Just returns it what kind of flower it is, I guess, assign the label to it. But we're going to go ahead and make our train data. And when you look at this, there's a couple things to take away from here. The first one is we're just appending right onto our NumPy array the image. We're going to let NumPy handle all that different aspects as far as 150 by 150 by 3. We just dump it right into the NumPy, which makes it really easy. We don't have to do anything funky on the processing, and we want to leave it like that. And I'm going to talk about that in a minute. And then, of course, we have to have the string, append the label on there. And I want you to notice right here, we're going to read the image in, and then we're going to size it. And this is important because we're just changing this to 150 by 150. We're resizing the image so it's uniform. Every image comes in identical to the other ones. This is something that's so important is when you're resizing or reformatting your data, you really have to be aware of what's going on. With images, it's not a big deal because with an image, you just resize it so it looks squishy or spread out or stretched. The neural network picks up on that and it doesn't really change how it processes it. So let's go ahead and run that. And now we've got our definition set up on there. And then we want to go ahead and make our training data. So make the train data daisy flower, daisy directory, print length of X. So here we go. Let's go ahead and run that. And we're just loading up the flower daisy. So this is going all in there, and it's setting, it's adding it in to our setup on there, to our X and Z setup. And we see we have 769. And then, of course, you can see this nice bar here. This is the bar going across is that little added code in there that just makes it really cool for doing demos. Not necessarily when you're building your own model or something like that, but if you're going to display this to other people, adding that little, what was it called? TQDM. I can never remember that. But the TQDM module in there is really nice. And we'll go ahead and do sunflowers. And of course, you could have just created an array of these. But this has an interesting problem that's going to come up, and I want to show you something. It doesn't matter how good the people in the back are or how good you are at programming. Errors are going to come up, and you got to figure out how to handle them. And so when we get all the way down to the, where is it? Dandelion. Here's our Dandelion directory we're going to build. Jupyter has some cool things it does, which makes this really easy to deal with. But at the same time, you would want to go back in there depending on how many times you rerun this, how many times you pull this. So when you're finding errors going in here, there's a couple things you can do, and we're just going to, oh, it wasn't, there it is. There's our error. I knew there was an error. This processed 1,062 out of 1,065. Now, I can do a couple things. One, I could go back into our definition, and I can just put in here try, and so if it has a bad conversion, because this is where the error is coming from, just skip it. That's one way to do it. When you're doing a lot of work in data science and you look at something like this where you're losing 3 points of data at the end, you just say, okay, I lost 3 points. Who cares? Or you can go in there and try to delete it. It really doesn't matter for this particular demo. And so we're just going to leave that error right alone and skip over because it's already added all the other files in there. And this is a wonderful thing about Jupyter Notebook, is that I can just continue on there, and the X and Z, which we're creating, is still running, and we'll just go right into the next flower row. So all these flowers are in there. That's just a cool thing about Jupyter Notebook. And then we can go ahead and just take a quick look and see what we're dealing with. And this is, of course, really, when you're dealing with other people and showing them stuff, this is just kind of fun where we can display it on the plot library here. And we're just going to go through and let's see, what do we got here? Looks like we're going to do like 5 of each of them, I think. Is that how they set this up? Plot library 5 by 2. Okay, oh, I see how they did it. Okay, so 2 each. So we have 5 by 2 set up on our axes, and we're just going to go in and look at a couple of these flowers. It's always a good thing to look at some of your data. No matter what you're doing, we've reformatted this to 150 by 150. You can see how it really blurs this one up here on the tulip. That is that resize to 150 by 150. And these are what's actually going in. These are all 150 by 150 images. You can check the dimensions on the side, and you can see just a quick sampling of the flowers we're actually going to process on here. And again, like I said at the beginning, most of your work in data science is reprocessing this different information. So we need to go ahead and take our labels and run a label encoder on there. And then we're just going to, LE is a label encoder. One of the things we imported, and then we always use the fit to categorical, y comma 5, x, here's our array, x. So if you look at this, here's our fit. We're going to transform z. That's our z array we created. And then we have y, which equals that. And then we go ahead and do to categorical. We want 5 different categories. And then we create our x, NP array of x. X equals x over 255. So what's going on here, there's 2 different transformations. One, we've turned our categories into 0, 1, 2, 3, 4, 5 as the output. And we have taken our x array. And remember, the x array is 3 values of your different colors. This is so important to understand. When we do this across a NumPy array, this takes every one of those 3 colors. So we have 150 by 150 pixels. Out of those 150 by 150 pixels, they each have 3 color arrays. And those color arrays range from 0 to 250. So when we take the x equals x over 255, range from 0 to 255, this converts all those pixels to a number between 0 and 1. And you really want to do that when you're working with neural networks. Now, if you do a linear regression model, it doesn't affect it as much, and so you don't have to do that conversion if you're doing straight numbers. But when you're running neural networks, if you don't do this, you're going to create a huge bias. And that means they'll do really good on predicting 1 or 2 things, and they'll just totally die on a lot of other predictions. So now we have our x and y values. X being the data in, Y being our known output. And with any good setup, we want to divide this data into our training. So we have X train, we have our X test. This is the data we're not going to program the model with. And of course your Y train corresponds to your X train, and your Y test corresponds to your X test, the outputs. And this is, when we do the train test split, this was from the scikit, sklearn. We imported train test split. And we're just going to go ahead and do the test size at about a quarter of the data, 0.25. And of course, random's always good. This is such a good tool. I mean, certainly you can do your own division. You could just take the first, 0.25 of the data or whatever, do the length of the data. Not real hard to do, but this is randomized so that if you're running this test a few times, you can kind of get an idea whether it's going to work or not. Sometimes what I will do is I'll just split the data into 3 parts, and then I'll test it on 2, with one being or I'll train it on 2 of those parts, with one being the test, and I rotate it. So I come up with 3 different answers, which is a good way of finding out just how good your model is. But for setting up, let's stick with the X-train, X-test, and the sklearn package. And then we're going to go ahead and do a random seed. Now, a lot of times the cross actually does this automatically, but we're going to go ahead and set it up on here. And you can see we did an NP random seed from 42, and we get a nice RN number. And then we do TF random, we set the seed. So you can set your randomness at the beginning of your TensorFlow. And that's what the tf.random.set is. So that's a lot of prep. All this prep, and then we finally get to the exciting part. This is where you probably spend, once you have the data prepped and you have your pipeline going and you have everything set up on there, this is the part that's exciting, is building these models. And so we look at this model. One, we're going to designate it as sequential. They have the API, which is the cross TensorFlow API versus sequential. Sequential means we're going one layer to the next. So we're not going to split the layer and bring it back together. It looks almost the same with the exception of bringing it back together. So it's not a huge step to go from this to an API. And the first thing we're going to look at is our convolutional neural network in 2D. So what's going on here? There's a lot of stuff that's going on here. The default for, well, let's start with the beginning. What is a convolutional 2D network? Well, a convolutional 2D network creates a number of small windows, and those small windows float over the picture, and each one of them is their own neural network, and it's basically becomes like a categorization. And then it looks at that and it says, oh, if we add these numbers up a certain way, we can find out whether this is the right flower based on this little window floating around, which looks at different things. And we have filters 32. So this is actually creating 32 windows, is what that's doing. And the kernel size is 5 by 5. So we're looking at a 5 by 5 square. Remember, it's 150 by 150. So this narrows it down to a 5 by 5. It's a 2D, so it has your XY coordinates. And when we look at this 5 by 5, remember each one of these is actually looking at 5 by 5 by 3. So we're actually looking at 15 by 15 different pixels. And padding is just, usually I just ignore that. Activation by default is ReLU. We went ahead and put the ReLU in there. There's a lot of different activations. ReLU is for your smaller, remember I mentioned atom, when you have a lot of data use an atom kind of activation, or use an atom processing. We're using the ReLU here. It kind of gives you a yes or no, but it doesn't give you a full yes or no. It has a 0 and then it kind of shoots off at an angle. Very common. It's the most common one. And then of course here's our input shape, 150 by 150 by 3 pixels. And then we have to pool it. So whenever you have a convolutional 2D layer, we have to bring this back together and pool this into a neural network. And then we're going to go ahead and repeat this. So we're going to add another network here. One of the cool things, if you look at this, is that as it comes in, it just kind of automatically assumes you're going down to the next layer. And so we have another convolutional neural network, 2D. Here's our max pooling again. We're going to do that again, max pooling. And we're just going to filter on down. Now, one of the things they did on this one is they changed the kernel size, they changed the number of filters, and so each one of these steps kind of looks at the data a little bit differently. And that's kind of cool because then you get a little added filtering on there. This is where you start playing with the model. You might be looking at a convolutional neural network, which is great for image classifications. When we get down to here, one of the things we see is flatten. So we just flatten it. Remember, this is 150 by 150 by 3. Well, and actually the pool size changes, so it's actually smaller than that. Flatten just puts that into a 1D array. So instead of being, a tensor of this really complexity with the pixels and everything, it's just flat. And then the dense is just another activation on there. By default, it is probably ReLU as far as its activation. And then, oh yeah, here we go. In sequential, they actually added the activation as ReLU. So this just, because this is sequential, this activation is attached to the dense. And there's a lot of different activations, but ReLU is the most common one. And then we also see a softmax. Softmax is similar, but it has its own kind of variation. And one of the cool things, you know what, let me bring this up because if you don't know about these activations, this doesn't make sense. And I just did a quick Google search on images of TensorFlow activations. I should probably look at which website this is. But this is the output of the values. So as it adds in all those weighted x values going into the node, it's going to activate it a certain way. And that's a sigmoid activation. And you can see it goes between 0 and 1 and has a nice curve there. This also shows the derivatives. And if we come down, the 7 popular activation functions, nonlinear activations, there's a lot of different options on this. Let me see if I can find the... Oops, let me see if I can find the specific to ReLU. So this is a leaky ReLU. And you can see instead of it just being 0 and then a value between going up, it has a little leaky there. Otherwise, your ReLU loses some nodes. They just become inactive. But you can see there's a lot of different options here. Here's a good one right here with the ReLU. You can see the ReLU function on the upper left here. And then the leaky ReLU over here on the right, which is very commonly used also. One of the things I use with processing language is the exponential one or the tangent H, the hyperbolic tangent, because they have that nice funky curve that comes in that has a whole different meaning and captures word use better. Again, these are very specific to domain, and you can spend a lot of time playing with different models. For our basic model, we'll stick to the ReLU and the softmax on here, and we'll go ahead and run and build this model. So now that we've had fun playing with all these different models that we can add in there, we need to go ahead and have a batch size on here, 128, epochs 10. This means that we're going to send 128 rows of data or flowers at a time to be processed. And the epochs 10, that's how many times we're going to loop through all the data. And then there's all kinds of stuff you can do. Again, this is now built into a lot of Keras models already by default. So there's different ways to reduce the values and verbose. Verbose equals 1 means that we're going to show what's going on. Value, monitor what we're monitoring. We'll see that as we actually train the model. This is what's going to come out of there. If you set the verbose equal to 0, you don't have to watch it train the model, although it is kind of nice to actually know what's going on sometimes. And since we're still working on bringing the data in, here's our batch size, here's our epochs, we need to go ahead and create a data generator. This is our image data generator, and it has all the different settings in here. Almost all of these are defaults. So if you're looking at this going, oh my gosh, this is confusing, most of the time you can actually just ignore most of this. Vertical flip, so you can randomly flip pictures, you can randomly horizontally flip them. You can shift the picture around. This kind of helps, gives you multiple data off of them. Zooming, rotation, there's all kinds of different things you can do with images. Most of these we're just going to leave as false. We don't really need to do all that setup because we already have a huge amount of data. If you're short data, you can start flipping like a horizontal picture and it will generate, it's like doubling your data almost. So the upside is you double your data. The downside is that if you already have a bias in your data, you already have 5,000 sunflowers and only 2 roses, that's a huge bias. It's also going to double that bias. That is the downside of that. And so we have our model compile, and this you're going to see on all the karras. We're going to take this model here, we're going to take all this information as far as how we want it to go, and we're going to compile it. This actually builds the model, and so we're going to run that. And I want you to notice learning rate, very important. This is the default 001. You really don't, this is how slowly it adjusts to find the right answer. And the more data you have, you might actually make this a smaller number. If you have a very small sample of data, you might go even larger than that. And then we're going to look at the loss, categorical cross entropy, most commonly used. And this is how much it improves. The model's improving is what this number means. Or, yeah, that's important on there. And then the accuracy. We want to know just how good our model is on the accuracy. And then one of the cool things to do is if you're in a group of people who are studying the model, if you're in shareholders, you don't want to do this, is you can run the model summary. I do this by default, and you can see the different layers that you built into this model. Just a quick summary on there. So we went ahead and we're going to go ahead and create a, we'll call it history, but we want to do a model fit generator. And so what this history is doing is this is tracking what's going on while it fits the model. Now there's a lot of new setups in here where they just use fit and then you put the generator in here. We're going to leave it like this, even though the new default is a little different on that. Doesn't really matter, it does the same thing. And we'll go ahead and just run that. And you can see while it's running right here, we're going through the epochs. We have 1 of 10. Now we're going through 6 to 25. Here's our loss. We're printing that out so you can see how it's improving, and our accuracy. The accuracy gets better and better. And this is 6 out of 25. This is going to take a couple minutes to process because we are training 150 by 150 by 3 pixels across 6 layers or 8 layers, whatever it was. That is a huge amount of processing, so this will take a few minutes to process. This is when we talk about the hardware and the problems that come up in data science and why it's only now just exploding, being able to do neural networks. This is why. This process takes a long time. Now you should have seen a jump on the screen here because I did pause the recorder to let this go ahead and run all the way through its epochs. Let's go ahead and take a look and see what these epochs are. And if you set the verbose to 0 instead of 1, it won't show what's going on in the behind the scenes as it's training it. So when we look at this epoch, 10 epochs, we went through all the data 10 times. If I remember correctly, there's roughly a gig of data there, so that's a lot of data. The first thing you're going to notice is the 270 seconds. That's how much each of those epochs took to run. And so if you divide 60 in there, you roughly get about 5 minutes worth of each epoch. So if I have 10 epochs, that's 50 minutes, almost an hour of runtime. That's a big deal when we talk about processing. On this particular computer, I actually have, 8 cores with 16 dedicated threads. So it runs like a 16-core computer. It alternates the threads going in. And it still takes it 5 minutes for each one of these epochs. So you start to see that if you have a lot of data, this is going to be a problem if you have a number of models. You want to find out how good the models are doing and what model to use. And so each of those models could take all night to run. In fact, I have a model I'm running now that takes about a day and a half to test each model. It takes 4 days to do the whole data. So what I do is I actually take a small piece of the data, test it out to find out, get an idea of how the different setups are going to do, and then I increase that size of the data and then increase it again, And I can just take that curve and kind of say, okay, if the data is doing this, then I need to add in more dense layers or whatever. So you can do a small chunks of data and then figure out what it costs to do a large set of data and what kind of model you want. The loss, as we see here, continues to go down. This is the error. This is how much error is in there. It really isn't a user-friendly number, other than the more it trends down, the better. And so if you continue to see the loss going down, eventually you'll get to the point where it stops going down and it goes up and down and kind of wavers a little bit. At that point, you know you've run too many epochs. You're starting to get a bias in there, and it's not going to give you a good model fit. The accuracy just turns this into something that we can use. And so the accuracy is what percentage of guesses, in this case it's categorical, so this is a percentage of guesses are correct. Value loss is similar, it's a minus a value loss. And then you have the value accuracy, and you'll see the value accuracy is pretty similar to the accuracy, just rounds it off basically. And so a lot of times you come down here and you go, okay, we're doing 0.5, 0.6, 0.7, and that is 70% accuracy, or in this case 68.59% accuracy. And that's a very usable number, and it's very important to have. If you're identifying flowers, that's probably good enough if you can get within a close distance and knowing what flower you're identifying. If you're trying to figure out whether someone's going to die from a heart attack or not, you might want to rethink it a little bit, or rekey how you're building your model. So if I'm working with a group of clients, shareholders in a company or something like that, you don't really want to show them this. You don't want to show them, hey, this is what's going on with the accuracy. These are just numbers. And so we want to go ahead and put the finishing touches, just like when you are building a house and you put in the frame and the trim on the house. It's nice to have a nice view of what's going on. And so we'll go ahead and do a pie plot, and we'll just plot the history of the loss, the history of the value loss over here. Epochs, train, and test. And so we're just going to compute these. This is really important. And what I want you to notice right here is when we get to about 5 epochs, a little more than 5, 6 epochs, you see a crossover here. And it starts crossing as far as the value loss. And what's going on here is you have the loss in your actual model and your actual data, and you have the value loss where it's testing it against the test data. The data wasn't used to program your model, wasn't used to train your model on. And so when we see this crossing over, this is where the bias is coming in. This is becoming overfitted. And so when you put these two together, right around 5 and 6, you start to see how it does this switch over here. And that's really where you need to stop, right around 5, 6. It's always hard to guess, because at this point the model's kind of a black box. But you know that right around here, if you're saving your model after each run, you want to use the one that's right around 5 epochs, because that's the one that's going to have the least amount of bias. So this is really important as far as guessing what's going on with your model and its accuracy and when to stop. It also is, I don't show people this mess up here. I show somebody this kind of model and I say, this is where the training and the testing comes in on this model. It just makes it easier to see and people can understand what's going on. So that completes our demo, and you can see we did what we were set out to do. We took our flowers and we were able to classify them within about 68-70% accuracy, whether it's going to be a dahlia, sunflower, cherry blossom, rose. A lot of other things you can do with your output as far as different tables to see where the errors are coming from and what problems are coming up.
Companies across the globe are generating data at a rapid rate, and data science is helping them draw valuable insights and make business decisions. Hello everyone. Welcome to this video tutorial on data science interview questions. In this video, we will learn some of the important questions that are often asked in any data science interview. We'll discuss questions related to various aspects of data science such as programming, SQL, mathematics, statistics, linear algebra, and probability. Finally, we'll get an idea about the top machine learning and deep learning interview questions that are frequently asked in interviews. So let's begin. Hi everyone. Welcome to this live session by Simplilearn. Today, we are going to talk about some of the essential programming interview questions for a data scientist role. Now, since Python is widely used programming language for data science, machine learning and deep learning, we will be solving our problems in the Python programming language using Jupyter Notebook. So let's wait for a few minutes for people to join in. Also, if you haven't subscribed to our channel yet, then please make sure to subscribe to it now and stay updated with all the recent trending technologies. And if you want to get the code file that we will use in this session, then please put your email IDs in the chat section of the video. Our team will share the interactive IPython notebook with you. So let's begin with our first question. Our first question is, how do you get a list of all the keys in a dictionary? Now in Python for data science, data structures play an important role to store and manipulate data. Dictionary is one such data structure that is declared using curly braces, and they are written as key value pairs. You can see on the screen I have my dictionary called D, and it is assigned using curly braces. Now to get a list of all the keys in a dictionary, we use the .keys function. Now let me take you to my Jupyter Notebook. So here is my Jupyter Notebook, and you can see my first cell. I have my dictionary defined. So the name of the dictionary is D, and it has the key values. The keys are the country names and the values are the capitals of each country. So I have India and the capital is New Delhi. Then I have USA, the capital is Washington. Similarly, I have Spain, Madrid, and we have Germany and Berlin. Now India, USA, France, Spain, all these are my keys. So to get the keys, I'll use the .keys function. So I'll write my dictionary name, that is D dot, I'll give keys, close the brackets and hit Shift Enter. You can see these are the list of my keys in the dictionary D. Alright. Okay. Now let's move to our next question. So our next question is, what do you mean by list comprehension in Python? So list comprehensions are a short and easy way to define and create new lists based on existing lists. So suppose you want to iterate through a list and find all the even numbers in the list. You can either use a for loop and an if condition as shown here, or you can write a list comprehension to do it in one line of code. You can see this is my list comprehension. So let me show you both the ways. Alright, so here on my Jupyter Notebook, let me declare my list as L equal to, I'll pass in a few numbers, let's say 5, 12, 10, we have 14, 43, 11, 7, 9, and let's say the last element in the list is 6. Alright, let me run this list. Okay, now let me create an empty list. Let's say list 1, and let this be an empty list with square brackets. Then I'll use the looping construct to find the even elements in the list. So I'll write a for loop called for item in my list L. I'll give colon, then I'll give my condition if item percentage 2 is equal to 0, which means if the remainder is 0, then I'll append the items to my empty list, which is list 1. So I'll write list 1 dot append, and I'll pass in the argument my item. Now let me go ahead and print my list. I'll write print the final list using a for loop. I'll give colon, give a comma, and pass in my new list name, which is list 1. Now let's run this. You can see using this for loop and the if condition, I have got all the even elements in my list, which was L. You can see my original list, and 12, 10, 14 and 6 were all the even numbers present in my list. Now this task you can do it using list comprehensions as well. So let me show you how to do that. So I have my list defined. Let me just copy this here. I'll paste it. And now I'll create another variable which is list1. I'll write equal to. Now here, using square brackets, I'll write item for item in L, and I'll give my if condition as if item percentage 2 is equal to 0, then I'll print my resultant list. So I'll write print, let's say, resultant list using list comprehension. I'll give a colon, then a comma, and I'll pass in my new list, which is list1. So here, whatever is there in my square brackets is called the list comprehension technique. Let me just print this and I'll get the same result. So these are my even numbers. Alright, so let's move to the third question. So our third question is, given a list of numbers, find the squares of the numbers using the map function in Python. Now the map function calls the specified function for each element of an iterable and returns a result. So let me show you an example to find out squares of a list of numbers using the map function. Okay, so let's first define a function called square. So I'm using my def keyword and I'll pass in my user defined function name as square, and I'll give my parameter as x, and I want to return the square of x, which is x star x. Alright, and then let me define my list of numbers. So I'll pass in a variable called num, and let's say I want to find the squares of 5 numbers 1, 2, 3, 4, 5. Here I'll pass in another variable which will store the resultant list. So I'll write num underscore squared equal to, here I'll use my map function. So map function takes in two parameters. First it will take in the user defined function name, which is square here, and the list of numbers, which is num. I'll run a for loop. I'll write for, let me just scroll down. I'll write for num in num underscore squared print num. So this is my map function. So it will map all the elements in the list to this function, which is square. I'll just print it. You can see we have the list of squares from the num list, which has the elements 1, 2, 3, 4 and 5. Now moving ahead, coming to our fourth question. The fourth question is on to write a program that will filter out the numbers divisible by 3 from a tuple using the lambda functions. So lambda functions are anonymous functions that are not defined by the def keyword in Python. So here you can see I have the example. So this is a tuple I have defined, and using filter along with the lambda function I am trying to find out the numbers that are divisible by 3, and finally I am printing those numbers. So let's do it on our Jupyter notebook. Alright, so we are on the Jupyter notebook. So first I'll define a tuple. Let's say the variable name is my underscore tup, which stands for my tuple, and using brackets I'll pass in my tuple values. Let's say 5, 12, 10, 18. We have 43, 9, 7, 11 and let's say 6. So you can see these are the numbers present in my tuple. Now I'll create another variable called new tuple, and I'll use my tuple function, and inside the tuple function I'll use the filter function that will filter out only the values that are divisible by 3. And now I'll write my lambda function. So notice this clearly, how to use a lambda function. I'll use the keyword lambda, and then I'll pass in a variable x. Now this should consider only those values that are divisible by 3. So I'll write x %3 should be equal to 0, and I'll give my tuple as the variable here. Alright, now we have declared our lambda function. Let's just go ahead and print my new tuple, which is new underscore tup. So here you can see I have my tuple function. Inside the tuple function I'll use my filter function that will filter only those values divisible by 3, and to filter those values I have used my lambda function here and passed in my original tuple, which is my tuple. It's actually my tup, so let's delete the last 2 letters. Let's just go ahead and print this. There you go. You can see we have 12, 18, 9 and 6 are the only numbers that are divisible by 3 from this tuple. Moving to the next question. So our next question is how to create a data frame from a dictionary. Now to create a data frame from a dictionary, you can use the pandas library and the .dataframe function. Now pandas is a popular library in Python that is used for data manipulation. So let me show you how you can create an employee dictionary and then convert that into a data frame. Okay, so here on my Jupyter notebook, let me go ahead and import my pandas library. So I'll write import pandas as pd, and next let's create my employee dictionary. So I'll write emp, which stands for employee, and within curly braces I'll give my key value pairs. So my first column would be the name of the employee, and let's pass in a list of employee names. I'll write Amy, let's say we have Angela, the third employee's name, let's say we have Samuel, and let Danny be our fourth employee. I'll give a comma. Now the second attribute in our dictionary will be the age of the employee. So my key would be age, and let's create a list of age values. I'm assigning random values to those employee age, 30 and let's say 32. And let's create another variable called city. Here variable refers to the column name of the data frame. Let's say Amy is from New York. Then we have Angela from Chicago. Let's say Samuel is from Boston, and we have Danny from, let's say, Seattle. Okay, so if I run this, I have my employee dictionary created. So if you want to see the dictionary, you can write print and pass the variable name, which is emp here. So this is my dictionary. Now to convert this dictionary into a data frame, you can simply write df, and you can give the pandas library as pd and use the data frame function. So I'll write data frame, and I'll pass in my dictionary name, which is emp here. Let's run it. Okay, so we have successfully created our data frame. Now let me just print the data frame. I'll write df. There you go. You can see I have a nice table here, which is actually our data frame. Here you can see the indices, and you can see our column names as name, age and city, and these are the values or the rows. Alright. Now let's see the sixth question we have. So the question is, what is the difference between LOC and ILOC in Python? Now as data scientists, you would often want to analyze a chunk of data and not all the rows in it. So LOC and ILOC functions can help you fetch specific rows and columns from your data frame. LOC function uses row or column labels to select and slice data from a data frame, while ILOC uses integer index to select specific rows and columns. Remember, ILOC stands for index location. I'll use a car data frame to show how LOC and ILOC works. Now on your screens you can see the data frame. So it has a column called brand, which has different brand names such as Ford, there's Hyundai, Tata, Mahindra, there's Maruti, there's Kia Motors. Then we have the year in which the car was manufactured. We have the number of kilometers the car has run. We have the city and the mileage the car gives. So let me first create this data frame on my Jupyter notebook. Okay. So here on my notepad I have my code written to create the data frame, that is car. I'll just copy this code and I'll paste it to this cell. Okay, let me just run it. So if I go on top, you can see we have successfully created our car data frame. Now let me go ahead and print this data frame. So I'll write print, in brackets I'll give my data frame as car. Let me run it. Alright, so here is my data frame. Now suppose you want to see the data from second row till the fifth row for brand and city columns, so you can use the LOC function. So I want my data from the second row till the fifth row for brand and city columns. So let me show you how to do that. So first I'll write my data frame name, that is car, and then I'll give my function as LOC, and within brackets I'll give my row index values. So I'll give from 2 to 5, which is second row to fifth row, and I'll give my column names as brand. I'll give a comma, and my second column which I want is city. So here I'm using the labeled based indexing. Let me just run it. There you go. You can see we have the information available for the second row, third row, fourth row and the fifth row. Alright. Similarly, let's see one more example for index location based slicing. So suppose you want to see the data from second, third and fourth row for year, kilometers and city columns. So for that you can use the ILOC function. So I want the value for second, third and fourth row, and the columns that I want are years, kilometers and the city column. So for that I'll give my data frame name as car dot, this time I'll use ILOC, and within square brackets I'll give my row values and the column values. Now one thing you should notice here is, if you use ILOC, Python will exclude the last index, which is the fifth row, and similarly here it will exclude the last index from the column, which is the fourth column. If I run this, you get the desired result. Now let's see another example. Let's say this time I want to print the rows that have mileage less than 25 for brand and city columns. So you can use a print function, and I'll pass in my data frame as car and use LOC. Here I'll give my condition as car, and I want my condition, that is mileage should be less than 25, and I want the brand name. So I'll use a square bracket and give my brand column, and I also want the city column. Okay, Let me close it. If you run this, now these are the brand names Renault, Tata and Kia, which have mileage less than 25. Let me just verify this. You can see all these values are less than 25. Similarly, you can use the ILOC function as well. I can write print. I'll give car.ILOC. Within square brackets, I'll give car, and my condition column is mileage. Now this should be less than 25. I'll use dot values, and then I'll give my column numbers as 0, 2. Let me run it. There you go. The same result, we have got it using ILOC function this time. And you can see the columns were 0, 2, which means we wanted the first column, which is brand, and the second column, which was kilometers. Alright. Now moving to our 7th question in the list of questions that we have. The question is, how is list.append different from list.extend? Now list.append adds its arguments as a single element to the end of the list. The length of the list increases by 1 here. And list.extend iterates over its arguments and adds each element to the list. The length of the list increases by the number of elements in its arguments. So let me show you the difference on my Jupyter notebook. Okay, so let's create a list called list1 equal to, I'll create a list, let's say it has some country names like India, then we have USA, and I'll consider one more country, let's say Canada. Okay, now let me print the length of this list also. I'll use the length function for that. Alright, now let me append one more list. So I'll use the append function. I'll write list1 dot append, and within brackets I'll give my new list which has two more country names, let's say France and Spain. Okay, and here let me print list1, and let's also print the length of the list again. I'll use the length function and my list name, which is list1. So just mark we are using append here. Let me run this. There you go. So here you can see my original list had 3 elements, hence the length is 3. Now when I appended this new list which had 2 elements, France and Spain, our size increased by 1 and the length of the new list is 4. Now let me just copy this code, and instead of append let me write extend so that we can see the difference between append and extend. I'll just scroll down, run it. Here you can see our original list had 3 elements, but after we extended our list with 2 more elements, the length of the new list became 5. So these are the 5 elements in the list, and here you can see there were total 4 elements in the list when we appended the new list. Okay, now moving to our 8th question. Suppose you have a car dataset which has a mileage column. You need to create a new field called MLG that will accept 2 values. If mileage is less than 25, then the value should be low MLG, and if the mileage is greater than or equal to 25, then the mileage should be high MLG, or the value should be high MLG. Now while analyzing data, data scientists often need to create extra columns in the data frame to add more values that will help you make your data analysis more efficient. So So this question is related to one such instance or one such idea. So here you can see my data set. It has the brand name, year, kilometers, city, and the mileage column. Now if mileage is less than 25, I'll add the value low MLG to my new column. Else, if mileage is greater than or equal to 25, I'll add high MLG to my new column. So here you can see my final output. Wherever the mileage is less than 25, it should print low MLG, else it should print high MLG. And now let's do this on my Jupyter notebook. So we'll use lambda functions that we learned earlier to perform this task. I'll write a function, let's say f is equal to, you can call this as a function or a variable. I'll give the keyword lambda and use x as my parameter. Now x should be low MLG if x is less than 25, which is mileage here, else if it's not less than 25, it should return high MLG. Now what I'll do is I'll give my data frame as car and I'll create my new column, that is MLG. Then I'll write equal to car dot, I'll give my column name from the original data frame, which is mileage, and I use my apply function and pass in the variable f. Now let's just print this data frame. If I run it, you can see the output here. We have created a new column which is MLG. You can see our new column name was MLG, and these are the results. So for Renault, Tata and Kia, for the last 3 rows, since the mileage is less than 25, it returned low MLG. For the remaining, it gave us high MLG. Now moving to the 9th question. So this is our next question. We want to create a 4x4 matrix and find the sum of all the diagonal elements in the matrix. Data scientists often work with multiple dimensional arrays or multi-dimensional arrays and matrices to build models. This question is related to an operation on a 4x4 matrix. So first, we need to create an array which will be a numpy array of 4x4 shape, and then we'll see how to calculate the diagonal elements or the sum of the diagonal elements. So I am on my Jupyter notebook. First, let's import the numpy library. So I'll write import numpy or numpy as np. Let me run it. Okay, now I'll create my 4x4 matrix. So I'll write m is equal to np dot array, and I'll create my 4x4 matrix. Let's say the values are 1, 2, 3, 4 in the first row, and in the second row I'll pass 5, 6, 7, 8. In the third row we'll have 9, 10 and 11, also 12, and finally we'll have 13, 14, 15 and 16 in the fourth row. I'll just run it. Now if I print m, you can see this is a 4x4 matrix. So this is one way of creating a 4x4 matrix, which is a bit tedious and lengthy. Instead of that, you can also use arange function. So if I write m is equal to np dot arange function, and here I'll give my values starting from 1 till 17. So this will actually exclude 17 and take from 1 to 16, and I'll give my shape as 4, 4. Let me print it. There you go. It has printed the exact same matrix that we saw above. Alright, now to print the diagonal elements, we'll use the diagonal function. So I'll write print m dot diagonal. Let me just run it. So 1, 6, 11 and 16 are my diagonal elements. You can see this matrix. 1, 6, 11 and 16 are my diagonal elements. Now to print the sum of all the diagonal elements, I'll use the sum function. So I'll write m dot diagonal. Along with that, I'll pass my sum function. If I run it, so the sum of 1, 6, 11 and 16 is 34. Okay, so coming to the last question on this interesting session on programming interview questions for data scientists. Our question is, given a vehicle data frame, find the average and maximum mileage of the vehicles using pandas. So here, data scientists use statistical measures to analyze their data, so it is important to have knowledge of the statistical functions in Python. Here is my vehicle data set, and for each brand of vehicle, we want to find the average and the maximum mileage. So let me show you how to do it. Okay. So here on the notepad, I have my code written to create the vehicle data frame. I'll just copy it and paste it on this cell. You can see we have the brand column, the year column, kilometers, city, mileage. Here you can see the different brand of vehicles. Let me just create this data frame first, and let me go ahead and print the vehicle data frame. So I'll write vehicle and run it. So here is the data frame. Now I want to find the average and maximum mileage for each of the brands. So for this, we'll use the group by function and the aggregate function that is available in the pandas library of Python. So let me show you how to do it. I'll give a variable called result, and then I'll use my data frame name as vehicle, followed by the group by function. I'll write group by, and since I want to check for all the brands, so I'll group all the brand of vehicles. Then I'll use an aggregate function which is agg, and within curly braces I'll give my column as mileage. I'll give a colon and pass in mean, which is for average, and I'll use max to find the maximum mileage. Now let's print it. I'll write print. I'll give a message as the average and maximum mileage of vehicles. Let me just print the result. I'll run it. You can see it has resulted in an error. The reason is in vehicle the V is capital. If I run it, there you go. Here you can see on the left we have the brand names. We have Hyundai, there's Maruti and Tata, because those were the only 3 brand of vehicles we had. And for each brand you can see the mean mileage and the maximum mileage. For Maruti it was 26.33 and the maximum mileage is 28. Similarly you can see for Tata vehicle as well. Hello everyone, welcome to this live session by Simplilearn. In our previous session, we looked at some of the important Python programming questions for data scientists. Today, we will learn some of the crucial SQL interview questions for data scientists. Now, if you want to get the SQL script file that we are going to use in this demo, then please put your email IDs in the chat section. Our team will send the SQL file via email. SQL is a widely used language for querying data from databases. It allows you to store, retrieve, manipulate and update data present in the form of rows and columns. Data scientists often work with structured data that is stored in MySQL databases, Microsoft SQL servers, Oracle databases, or even NoSQL databases such as MongoDB. Today, we will look at a variety of SQL questions. We'll be using the MySQL database for our demo. Throughout the video, we'll be using MySQL Workbench and the MySQL command line to solve the SQL queries. Let me show you the database that we will be using for this demo and the tables we are going to use. Okay, so here I am on my SQL Workbench, and below you can see I have a local instance created. I'll just click on it. Now it's asking me to enter the password. I'll give my password and hit OK. Now this will take me to the SQL editor. Now this is the SQL Workbench. So let me first create a new SQL query file. Alright, so first and foremost, let me show you the databases we have. For that, I'll use the command show databases. If I hit tab, it will autocomplete. I'll give a semicolon and hit Control Enter to run this. There you go. Here you can see the list of databases that we already have, and from the list of databases we are going to use the SQL_IQ database. So to use this database, I'll write the command use SQL_IQ. I'll give a semicolon, I'll select this, and I'll click on this execute button. If I run this, you can see now I'm using SQL_IQ database. Now if you want to see all the tables present in SQL_IQ database, we'll use the following command. So I'll write show tables. Now this will list all the tables present inside SQL_IQ database. If I run it, you can see here it has executed successfully and it has given us 7 rows, which means we have a total of 7 tables in this database. You can see there's an author table, there's a table called books, we have customers, email, employee, players, and weather table. So all these tables we are going to use in the course of this video. Now if you want to have a look at the data present in one of the tables, you can just use the select statement. So I'll write select star from, let's say I want to see the data present inside the employee table, so I'll write employee. So this is my table name. I give a semicolon. If I select this, hit the execute button, there you go. It shows me that it has returned 6 rows, and these are the column names. We have the name of the employee, the age of the employee, we have the employee's salary and the employee ID. So there are total 6 employees in the table. Alright, now I can do the same operations on my SQL command line as well. Now let me open the command line first. Okay, so this is the MySQL command line client. It is asking me to enter the password, so I'll give my password first. Alright, now here you can see I have come inside MySQL. Now the operations that we performed on the MySQL Workbench, the same operations can be performed on the command line as well. So I'll write use SQL_IQ. I'll hit enter. You can see the message, it says database changed. Now if you want to display the tables present inside this database, I can use show tables command. I have to give a semicolon and hit enter. There you go. You can see the list of tables we have inside the database. Now if you want to have a look at the content of one of the tables, I can just write select star from, let's say, players. If I give a semicolon, hit enter, you can see the rows and columns in the dataset. Alright, and with that, let's move on to our first question on SQL. Okay, so our question is, what is the difference between where and having clause in SQL? So where clause is used to filter the records based on the specified condition, while the having clause is used to filter the records from groups based on specified conditions. You need not worry, we'll do the demo for where and having clause using the employee table. So where clause cannot have aggregate functions such as count, sum, min or maximum functions. Having clause can operate on aggregate functions. Now where clause is implemented on rows, while having clause is implemented on columns. Now let me show you an example of how a where clause is different from an having clause. So I'll take you to my MySQL workbench. Alright, so we are on the SQL workbench. So suppose I want to get the records of the employees whose age is greater than 30. For this I can use a where clause. So since I want to get the employees whose age is greater than 30, I'll use a where clause. I'll write my SQL query as select star from employee where I'll write age is greater than 30. If I give a semicolon and run this, it will return all the employees whose age is greater than 30. You can see 36, 36 and 35. These are the employees whose age is greater than 30. Now I have intentionally kept some duplicate rows because we are going to use this in our next questions. Again, I can also do the same task using the having clause. So let me just copy this query. I'll paste it here. Now instead of where, I'll write having. So you will see that even this query will return the same result. If I run it, you can see it gives me the same result. Now let's say I want to find all the records where the count of age for all the employees is greater than 1. In this case, I can't use a where clause. It will throw me an error since where clause cannot be used with aggregate functions. So let's try using an aggregate function in the where clause. So I'll write select star from employee where count of age is greater than 1. So the idea is to find all the records where the count of age for all the employees is greater than 1. So if I run this SQL query, you can see it has given me an error. It says invalid use of group function. Now instead we need to use a having clause along with the group by clause to solve the problem. So I'll group all the age values and then find the count of each age value. So let me just paste this, and here I'll edit my SQL query. Instead of where, I'll write having, and just after the table name I'll use the group by clause. So I'll write group by age. Now let's run it. Alright, you can see our SQL query has returned only those employees whose age occurs more than once. Now let me just verify this. If I run my employee table, you can see Angela's age, that is 36, has been repeated twice. You can see Angela here as well, and similarly we have Mike also repeated twice. Alright. Now let's see the second question. Now this is a multiple choice question where you need to answer the correct SQL query based on the question. So the question is, the correct SQL query to select all the records of employees with ARI in their names is. So we have a list of 4 options given, and out of that you need to find the correct option. Now the answer to this question is this. So if you write select star from the table name, which is employee here, where name like, then if you give this condition, it will return all the records where employees have ARI in their names. Now like is an operator in SQL that is used to search a specified pattern. So here our pattern is we want all those employees who have ARI in their names. The first percentage means that the name can have any number of letters in the beginning, followed by ARI in the middle, and the last percentage means the name can have any number of letters in the end. So let's do this on our MySQL workbench. Let me first display all the employees in the table. So I'll write select star from employee. I'll run this. If you see my table, I have one employee who has ARI in its name, and that person is Karin. I now want to get this particular record. So what I can do is I'll write a select query, select star from employee where name, then I'll use the like operator where name like, within double quotes I'll give percentage ARI, again a percentage, close the double quotes and give a semicolon. If I run this, you can see my SQL query will return only Karin. Now let's do one more example. Suppose I want to find the employee whose name starts with D. So the way to do is something similar to what we saw just now. So here in my condition, I'll just replace this with D. This means the name should start with D, and after that it can contain any number of letters. Now let's run it. There you go. So our table had one employee called Danny whose name started with D. Now moving to our third question. So the question is, we want to write a query to find the players with the least number of goals. So there are two methods to do it. One where you can use a subquery, and the other method to use the limit operator. So let me show you both the methods. First, let me go ahead and display all the tables present in my database, that is SQL or SQL_IQ. Alright, if I scroll down, you can see we have a table called players. So I'm going to use the players table to find the player with the least number of goals. So let me show you the first method, that is by using a subquery. So I'll write select star from my table name, which is players, where goals equal to, and in this I'll write my subquery using brackets. So I'll select minimum goals from the table, that is players. I'll close the bracket and then I'll give a semicolon. Now let me go ahead and run this. You can see Matt was the player from Scotland who scored the least number of goals, that is 3. Now let's break it down. So what we did was, first my SQL query found out what was the minimum goal scored by a player. So if I run this, you will see it will return me 3. So 3 was the least number of goals scored by one of the players. Now in my outer query, what SQL did was it searched for those goals where the value was equal to 3. So we wrote select star from players where goals equal to 3. Hence, if I run this, you will find the player who scored only 3 goals, and that player is Matt. Alright. Now the other way to do is using the limit operator. So this is more simpler than the previous method. I can write select star from players order by goals. Now let me first run this SQL statement. If I run this, you can see we have ordered this in ascending order. So the person who has scored the least number of goals appears at the top, and the person with the player with the highest number of goals appears at the bottom. And from this table I only want the first row, and for that I can use the limit operator. So if I write limit 1, it will display only the first row. If I run it, you can see it shows me only the record for Matt. Moving ahead, now let's see the fourth question in our list. The question is, write the SQL query to find the player with the second highest number of goals. Now again, there are two methods to do it. One is by using limit and offset, and the other method is to use a subquery. So let's see both the methods. I'll first write my SQL query using limit and offset. So my query will be select star from players order by goals descending. Let me just run this. Alright, so here you can see my table has been ordered in descending order of goals. So Anthony has scored the most number of goals, then comes Daniel, followed by Sam, and at the end we have Matt, who scored the least number of goals. Now out of this, I want the player who scored the second highest number of goals, which is Daniel. So I want my SQL query to return this row that has player ID 103, name is Daniel, country is England, and goals is 7. For that, MySQL has two features. So I can use limit 1 followed by offset 1. So what this query does is, it will offset one row, that is, it is going to offset the first row, or it is going to skip the first row and then print only the second row, because I have set my limit to 1. So let me just run it. You will see we get the desired result. The player name is Daniel and the number of goals scored is 7. Now the other method to do is using a subquery. Now let me write my subquery. First I'll write my outer query, which is select star from, and here I'll write my subquery select star from players order by my column name, which is goals, in descending order. Here I'll limit it to 2. Then I'll give my alias name as T. Then I'll use order by goals limit 1. Let me just run it first. If I run this, you see here I get the same result. Now let's first break it down. I'm going to run this subquery first. So here I have select star from players order by goals descending and limit is 2. Let me just run it. So the selected SQL query returns the first two rows ordered by goals, and if you see here clearly, we have again ordered the value returned in ascending order, which means from this table, if I order this table in ascending order, Daniel should appear first, and out of that I'm limiting my result to 1, so it will print only Daniel. If I run this again, you can see I have the desired output. Now let's check the fifth question in our list. Given the below email table, write a SQL query to find the distinct domain names from the email column. So if you consider this as my email table, the domain names are gmail.com, yahoo.in, and we have hotmail.com. These are the distinct domain names. Now to solve this task, again we have two methods. Either you can use the substring underscore index function, or you can use the substring function. Now the substring underscore index function returns a substring of a given string before a specified number of delimiters. So let me first use the first method. Okay, so here on my SQL workbench, I'll write select. I'll use the keyword that is distinct. Then I'll use my function, which is substring underscore index. Here substring underscore index will take 3 parameters. The first is the original column name, which is email, followed by the delimiter I'm looking for, that is @. So I'll put @ with single quotes since it is a text or a character, and then I'll give the number of times to search for the delimiter. Here it is going to be -1. So you can either give a positive value or a negative value. If it is a positive number, then this function will return all to the left of the delimiter. If it is a negative number, the function returns all to the right of the delimiter. Alright. And then I'll give an alias name as, say, domain name from my table, that is email. If I run this, you can see I have the list of all unique domain names or distinct domain names that we saw in our table. This is one of the ways. The other way is to use the substring function. Now the substring function extracts a substring from a string starting at any position. So let me write my SQL query. I'll write select distinct. I'll then give my function as substring. Here substring will take in two parameters. The first parameter is the column name, which is email ID here. So I'll write email. I'll give a comma. Next, I want to find my delimiter. So for that, I'm going to use another function called locate. And here I want to locate the index position of @. So I want to give my delimiter as @ followed by the column name, which is email. And then I want to fetch everything after the delimiter, and for that I'm giving +1. Again, let me give a domain name as the alias name from email. If I run this, you will see we'll get all the unique domain names: Gmail, Yahoo.in and Hotmail.com. So these were the two ways to solve the same problem. Now moving ahead, let's look at our sixth question. So our question is, write the SQL query to find duplicate records from a table without using a temporary table. Now, one of the other variants of this question is to delete all the duplicate records from a table without using a temporary table. Now to solve such queries, you can use the group by and the having clause. Let's look at how to do it. So here on my SQL workbench, I'll write my select query as select star, and then I want to count all the duplicate values. Let me give it an alias name as frequency from my table name, which is employee here, and then I want to group by name having count star greater than 1. Let me just run it. Alright, you can see it has returned me two rows. The name is Angela and Mike, and the frequency is 2. Let me just verify this to see all the repeated records that were present in my employee table. So I'll write select star from employee. If I run this and scroll down, here you can see Angela is present here as well as at the bottom. Similarly, we have Mike present twice in the table, and hence our SQL query returned only Angela and Mike because they were repeated twice. You can see the frequency here. So let's now look at our seventh question. Given the below employee table, I want to write a query to find all the even and odd records from the table. So as you can see, there are two ways to do it. One is to use a subquery, and another you can use the mod function. So let me show you both the ways. Alright, so let me run this SQL query to see all the values present in the employee table. So if you see the last column, which is the employee ID column, has all the employee IDs as unique values. So I'm going to use this in my where condition. So to find out all the even records, I'll write my SQL query something like this. I'll write select star from employee, which is my table name, where employee ID. Then I'm going to give my in operator, and inside the in operator I'm going to write my subquery, which is select employee ID from employee, where employee ID %2 is equal to 0. This means wherever my employee ID is divisible by 2, it will return only those records. So let me just run it. There you go. So here we have easily fetched only the even records from the table. Similarly, if you want to get only the odd records from the table, you can use the mod function also. So I'll write select star from employee, where here I'm using the mod function, mod empid comma 2 is not equal to 0. So I'll use the exclamation mark is equal to 0. So if I run this, it will return only the odd employee IDs. You can see it here. So those were the two ways in which you can fetch the even and odd records from the table. Now let's see our 8th question. So here is the question. Below is the customer table. Write a query to get the first purchase of each customer. Now if you look at the table, there are 3 customer IDs, 101, 102 and 103. Now customer 101 made its first purchase on 2nd October 2018, which is this one, and customer 102 made its first purchase on 5th of October 2018. And since we have just one record for customer ID 103, so this is going to be his or her first purchase. So I want to return 101 phone, 102 tablet and 103 books. To do this, we are going to use an inner join. If you can see, I have used an inner join and I have also used a subquery. Let's write this query on my SQL workbench. Okay, so this query is going to be a little complicated. If you have any questions, then please put it in the chat section. We'll be happy to help you. So I'll start with select. I'm going to take an alias name as t dot. I'll write cust underscore id comma t dot purchased at comma. The next field I'm going to select is t dot item from customers as t. Next I'm going to write my inner join, and inside the inner join I'll write my subquery, which is going to be select customer ID comma. I'm going to take the minimum value from the purchased at column, which is my date column. Close this. I'll give another alias as min underscore purchased underscore at from my table name is customers. Then I'm going to group it by 1. Here 1 means the first column that you have put in the select statement, which is customer ID. So I'm grouping by customer ID. I close the bracket, and everything I'm going to give an alias name as t1. Now I'm going to join on t dot customer ID is equal to t1 dot customer ID and my next condition would be t dot purchased at is equal to t1 dot min underscore purchased underscore at. I'll give a semicolon. I would request you to go through this SQL query in a detailed manner so that you understand it line by line. Let me just run it now. If I run it, okay, it has thrown me an error which says table SQL underscore IQ customer does not exist. The reason is my table name is customers. Alright, so let me run it once again. Okay, so there's one more error. It says unknown column purchases at. So we had made a spelling mistake here. It should be purchased at. Now let's try and run it. Alright, there you go. So for customer ID 101, the first purchase was made on 2nd of October 2018. Likewise, for customer ID 103, the first purchase was made on 5th of October. And similarly for customer ID 102, the first purchase was made on 5th of October again. Now moving to the 9th question. So here we have a weather table. We want to write an SQL query to find all the date IDs with higher temperature compared to its previous dates. So if you see, we have a date ID column. We have the date and the temperature. Using this table, I want to find those IDs with higher temperature compared to its previous dates. So if you look for date ID 1, the temperature is 32. For date ID 2, the temperature is 31. For date ID 3, the temperature is 30.8. Now if you clearly notice, for date ID 4, the temperature is 31.5, which is actually higher than the previous date ID, which is 30.8. Similarly, for date ID 5, the temperature is 33, which is again higher than the previous date, which is 31.5. Now if you look at the date values, they start from 10th of March till 15th of March 2020. Now to solve this query, we are going to use SQL joins again, and I'm going to use a function called to_days. Now MySQL to_days function returns the number of days between a given date and year 0. So let's go ahead and write this SQL query. Alright, so first let me select all the rows from the temperature table which we are going to use for this particular question. I'll run it. Alright, there's some error. Actually the name of the table is weather and not temperature, so I'll write weather. Let me run it. Okay, so here you can see these are all the rows present in the weather table, and as I explained, I want to return only the date ID 4 and this date ID which is 5. Now one thing I want to make it clear here, that this date ID should actually be 6, so there was a mistake while creating the table. So please consider this date ID as 6 and not 5. So I want to return date ID 4 and date ID 5. Alright, so let me go ahead and write my SQL query. So I'll write select, I'll write a dot date underscore ID from weather as A, comma, I'll join weather as B, where A dot temperature is greater than B dot temperature, and I'll give my condition, and I'll use the function to_days and give my value a dot date underscore val is equal to, I'll use the function again to_days b dot date underscore val plus 1. Now I would like to know from our viewers, why have we used +1 in the where condition? So please put your comments in the chat section. Let me just run it. There you go. So here you can see my SQL query has returned the date ID 4 and 5, which means these are the date IDs where the temperature was higher compared to the previous dates. Alright. Now coming to the last question on this interesting session on SQL interview questions for data scientists. So there are two tables. One is the authors table and the other is the books table. I want to write an SQL query to find the second highest author who sold the most number of books. Now this is going to be my SQL query. Again, we are going to use joins on both tables author and books along with limit and offset operators. So let me show you how to do it. So first I'm going to join my author table and the book table. So I'll write select a dot author underscore name, comma, I'm going to find the sum of copies sold from the books table. So I am giving my alias name as b dot copies underscore sold, which is my table name. I'll give an alias as sum underscore sold from author as A, join books as B on, I'll write b dot book underscore name is equal to a dot book underscore name. Now I'm using book underscore name as my criteria because book underscore name is the common column to both the tables. Then I'll use a group by clause. I'll write group by a dot author name. Then again I'm going to use an order by clause. I'll write order by sum underscore sold, and I am going to order it in descending order, so I'll write DESC. I'll set my limit as 1 and offset as 1. If I run this, you will find that my SQL query has thrown an error. The reason is we have used a column called bull underscore name, so it should be book underscore name. There was an error here. Let me run it again. Okay, there was another small error. This should be sum underscore sold. Let's run it. There you go. So my SQL query has returned author 3 because author 3 sold the second highest number of books. Now let me just remove the last few lines in the script. Let me just run it now. If I run this, you can see author 1 sold the highest number of books, followed by author 3 who sold the second highest number of books, and then it was author 2 who sold the least number of books. So if I write limit 1 and offset 1, what this line of code will do is it will skip the first row and print the next row. So let's just run it, and you can see it has returned me the author who sold the second highest number of books.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Hi everyone, welcome to this live session by Simplilearn. In today's session, we'll be discussing some of the top mathematics interview questions for data science. These questions are based on various topics in mathematics such as statistics, probability, and linear algebra. So let's begin with our first question. The first question we have is, what is normal distribution? Now, normal distribution is a probability distribution that is used to check how your data is distributed. Your data could be spread out to the left or to the right, but in many cases, the data tends to be around a central value with no bias left or right, as you can see on your screens. Now this is called a normal distribution, where half of the points are to the left and another half of the points are to the right of the center. Now such a distribution contributes to 68% of the data falling within one standard deviation of the mean. Then we have 95% of the data falls within second standard deviation of the mean. So if you add up 13.6% and the 68% plus 13.6%, this will result to 95% of data falling within two standard deviations of the mean. And finally, we have close to 99.7% of the data falling within three standard deviations of the mean. So this is what a normal distribution is all about. Now moving on to the next question. So what are the different measures that are used to summarize a distribution? Now to get more idea about the data and summarize a distribution, you can use three types of statistical measures. The first, we have central tendency measures, then we have variation measures, and finally we have shape measures. Now under central tendency measures, we have mean, median and mode. Now the mean is the most frequently used measure of central tendency in a data set. Let me take you to the Wikipedia page and explain you what mean exactly is. Okay, so here you can see on the Wikipedia page, it has the formula to calculate the mean of a distribution. So this is basically the summation of all the data points divided by the total number of data points. So here you can see an example. We want to find the arithmetic mean of 5 values, which are 4, 36. We'll pick the fourth element from our ordered set of points, that is 6 here, and hence 6 is the median for this ordered set of points. Now if you have an even number of observations, as you can see here, total we have 8 observations. Now the median becomes xn by 2 plus xn by 2 plus 1 divided by 2. So your median becomes the mean of the middle two numbers, that is 4 plus 5 by 2, which is 4.5. Alright. Now the next statistical measure we have under central tendency is called the mode. So the mode is the most frequently occurring value in a set of data points. So here you can see an example. We have a set of data points 6, 3, 9, 6, 6, 5, 9, 3. So your mode is going to be 6 here, since 6 is occurring thrice in the set of data points. Okay. Now under variation measures, we have variance, standard deviation and interquartile range. So first look at what variance is. So variance is the average of the squared differences from the mean. Now this is the formula for variance. You can see xi represents the individual set of data points and mu represents the average value. So mu is nothing but the summation of all the data points divided by the total number of data points. So this is your formula for variance. Next we have standard deviation. So standard deviation is a measure of the amount of variation or dispersion of a set of values. A low standard deviation suggests that the values tend to be close to the mean, while a high standard deviation suggests that the values are very spread out. Now here you can see the formula for variance. Now this is denoted by sigma, and your standard deviation is nothing but the square root of variance. So here you can see the formula for variance. You have xi minus your mu square, which is the mean of all the data points, divided by n. Then we have the interquartile range, which is also known as IQR. So IQR is a measure of variability based on dividing a data set into quartiles. So an interquartile range measures where the bulk of values lie. So the formula for IQR is Q3, which is the third quartile minus the first quartile. So here you can see we have a list of data points. Then we are ordering the data points first, and then we cut the list into quarters. So first you have the Q1, then you have Q2, and finally you have Q3. So for these set of data points, your IQR is going to be 7 minus 4, that is 3. Then we have shape measures. So under shape measures we have skewness and kurtosis. So skewness is a measure of symmetry. Your distribution is symmetric if it looks the same to the left and the right of a center point. Now they are majorly of two types. One is called negative skew, or which is also known as left skew. Then we have positive skewed or right skewed. And finally we have kurtosis. So kurtosis is a measure of the tailedness of a probability distribution. It defines how heavily the tails of a distribution differ from the tails of a normal distribution. So if you consider these distributions, the kurtosis will calculate the tailedness, which is actually these areas of a distribution. Now let's look at a third question. So the question is, create a sparse matrix in Python. Now in numerical analysis, a sparse matrix or a sparse array is a matrix in which most of the elements are 0. Now there are multiple ways to create a sparse matrix. I'll show you two ways to create a sparse matrix. So let me take you to my Jupyter notebook, where I'll create a matrix first and then we'll see how to create sparse matrix out of it. So I am on my Jupyter notebook here. First let me import the necessary libraries. So first I am going to import numpy as np, and then from scipy we'll import sparse. I'll run this cell. Okay. Next let me go ahead and create a matrix. I'll use the np.array function, and within this function I'll create a 3x3 matrix and I'll assign the elements. So my first row will have 1 2 3, next we'll have 4 5 6, then we'll have 7 8 and 9. Alright, let me run this cell. Okay, now let me go ahead and print my matrix. So I'll use the print function, and let's say I'll pass in a message that is original matrix, comma, and then pass in my variable name that is matrix. Let's run it. So here you can see I have my original matrix. It is a 3x3 matrix and has 9 elements in it. First let's see how using dictionary of keys you can create a sparse matrix. So for that I'll write the print statement, and then I'm going to use a function which is called DOK, that stands for dictionary of keys underscore matrix, and I'll pass in my variable name which is my original matrix. So if I run this, you can see I have got my dictionary of keys sparse matrix. Next I'll show you how using diagonal storage based you can create a sparse. That I am going to use another function that is sparse dot dia, which stands for diagonal underscore matrix, and within this function I'll pass in my original matrix variable name. If I run this, you can see we have created diagonal storage based sparse matrix. Alright, now moving to the next question. So given below is a matrix. Now we need to find the inverse of this matrix. Now the inverse of a square matrix A, which is sometimes called as a reciprocal matrix, is a matrix A inverse such that the dot product of A and A inverse is always I, which is an identity matrix. Now in NumPy we have a function which you can see here, that is np.linalg.inv, that helps you find the inverse of a matrix. Let me show you on the Jupyter notebook. First let me print my original matrix. Alright, now here I'll use the function with min, that is np.linalg.inv, inv, which stands for inverse, and then pass me my variable name, that is matrix. If I run this, you can see I've got the inverse of my original matrix. Now moving to our fifth question. So this question is related to probability. You call 2 Uber X and 3 lifts. If the time that each takes to reach you is IIT, what is the probability that all the lifts arrive first? Next, we want to find what is the probability that all the Uber X arrive first. Now this is fairly a simple question. First, let's look at all the lifts arrive first. Then first we need to find the probability that the first car is a lift, which is going to be 3 by 5, since we have 3 lifts and total we have 5 vehicles. Next, we want to find the probability that the second car is a lift, which is going to be 2 by 4. Third, we need to find the probability that the third car is also a lift, which is 1 by 3. Now, arrive first is going to be the multiplication of the product of the above 3 probabilities, that is 3 by 5 into 2 by 4 into 1 by 3, which is nothing but 1 by 10. Next, let's say you want to find for all the Ubers that arrive first. So you need to find the probability that the first car is Uber, which is nothing but 2 by 5, since we have 2 Ubers. Next, the probability that the second car is an Uber is going to be 1 by 4. So the total probability that all the Ubers arrive first is going to be the product of 2 by 5 and 1 by 4, which is also 1 by 10. Now moving to the sixth question. The mean, median and mode of a distribution are 30, 25 and 20. We need to determine if the distribution plot will be positively skewed or negatively skewed. So you can see from the distribution graph, the mean is to the right, median to the middle and mode to the left. So since the value of mode is less than the mean and median, the data will be positively skewed. And similarly, the skewness of the distribution is on the left if the mean value is less than the median and the mode occurs at the highest frequency of the distribution. Now the next question we have is, what are covariance and correlation? So covariance and correlation are measures that help you understand the relationship between two continuous variables. So covariance tells the direction of the linear relationship between two random variables. The direction means if the variables are directly proportional or inversely proportional to each other. So increasing the value of one variable might have a positive or a negative impact on the value of the other variable. Now covariance can take any value between minus infinity and plus infinity. So below you can see the formula to calculate the covariance. So you have summation xi minus x bar or x dash here represents the mean, xi represents the individual points, then this is multiplied by yi minus y dash or the mean of y divided by the total number of observations. Next, we have correlation. So correlation explains the change in one variable leads to how much proportion changes in the second variable. Correlation tells how strongly two random variables are related to each other. It takes values between -1 and +1. A negative correlation means they are inversely proportional to each other. A positive correlation means they are directly proportional to each other. If the correlation coefficient is 0, then there is no linear relationship between the variables. So here below you can see the formula to calculate the correlation. Now moving to the eighth question. So what are the sampling methods used in data science? Now sampling is a statistical technique that is used to select, manipulate and analyze a subset of data points and find patterns and trends in the large data set being examined. Now there are two types of sampling methods. We have probability sampling and non-probability sampling. Now under probability sampling we have something called as random sampling. So in random sampling, every individual is chosen entirely by chance and each member of the population has an equal chance of being selected. Then we have stratified sampling. So in stratified sampling, subsets of the population are created based on a common factor and samples are randomly collected from each other. Now talking about systematic sampling. So in systematic sampling, a sample is created by setting an interval at which to extract data from the larger population. An example could be selecting every fifth row in a spreadsheet of 100 items and creating a sample size of 20 rows for analysis. And finally, under probability sampling, we have cluster sampling. So in a cluster sampling, subgroups of the population are used as the sampling unit rather than individuals. So the population is divided into clusters and a whole cluster is randomly selected to be included in the analysis. Now let's look at the sampling methods that are present under non-probability sampling. So first we have convenience sampling. So for convenience sampling, the samples are selected based on the availability. So this method is used when the availability of samples is rare and costly. So based on convenience, samples are selected. Second, we have quota sampling. So quota sampling depends on some preset standard. The proportion of characteristics in sample should be the same as the population. Next, we have purposive sampling. It is also known as judgmental sampling. You select members of sampling on the basis of the objective of the study. It is very useful when you want to reach a particular or targeted sample quickly. Finally, we have snowball sampling. So the snowball sampling technique is used in situations where the population is completely unknown and rare. Now coming to the 9th question in our list. So explain what p-value tells about statistical significance. So p-value is a statistical test that is used in hypothesis testing. It helps you to decide whether to accept or reject the null hypothesis. The null hypothesis, represented as H0, is a commonly accepted fact. It is the opposite of alternative hypothesis. Researchers and scientists work to reject or disapprove the null hypothesis. They come up with an alternative hypothesis that they think explains a phenomenon, and they work to reject the null hypothesis. For example, null hypothesis or H0 could be the world is flat, and an alternative hypothesis could be the world is round. So lower the p-value, the greater the statistical significance of the observed difference. Now the p-value is just one piece of information you can use when deciding if your null hypothesis is true or not. The p-value lies between 0 and 1, as you can see here. The threshold for p is set to 0.05. When the value is below 0.05, the null hypothesis is rejected. Now coming to the final question in our list of mathematics interview questions for data science. So the question is, what do you understand by type 1 versus type 2 error? Now in statistical theory, the statistical error is an integral part of hypothesis testing. In statistical hypothesis testing, no test is ever 100% certain. That's because we rely on probabilities to experiment. Even though hypothesis tests are meant to be reliable, there are two types. So type 1 error occurs when the null hypothesis is true and we reject it. It is also known as a false positive finding or conclusion. An example could be an innocent person is convicted. And type 2 error occurs when the null hypothesis is false and we accept it. It is also known as false negative finding or conclusion. An example could be a guilty person is not convicted. So here you can see we have a reality where your null hypothesis is true, and here we have the null hypothesis is false, and this is where the type 1 error lies. So this can also be represented as false positive, where the null hypothesis is true and we reject it, and this could be false negative, where the null hypothesis is in reality it's false and we accept it. Welcome to this video tutorial series on data science interview questions. In our previous video, we had discussed the important interview questions on mathematics, statistics, probability and linear algebra that are often asked in any data science interview. Today, we will learn about some of the machine learning and deep learning interview questions. So let's begin with our first question. The first question is, how to detect outliers in data? So in data analytics and machine learning, you often find data points that lie at an abnormal distance from other points in a random sample from a population. Those are called outliers. Now outliers in data can significantly impact any prediction analysis. There are majorly three different methods to treat outliers. First, we have the univariate method. It is one of the simplest methods for detecting outliers. The univariate method uses box plots. A box plot is a graphical display for describing the distributions of the data. Box plots use the median and the lower and upper quartiles. This method looks for data points with extreme values on one variable. Next, we have the multivariate method. So the multivariate outliers can be found in an n-dimensional space having n features. We look for unusual combinations of all the variables in this method. Finally, we have Minkowski error. This method reduces the contribution of potential outliers in the training process. The Minkowski error is a loss index that is more insensitive to outliers than the standard mean squared error. Now moving on to the second question, what is a confusion matrix? So a confusion matrix is a table that is used to describe the performance of a classification model on a set of test data for which the true values are already known. The target variable has two values, positive or negative. The columns represent the actual values of the target variable, which you can see here. The rows represent the predicted values of the target variable, which you can see here. Now there are four important terms that are related to confusion matrix. First, we have true positive, which is this one. So in true positive, the predicted value matches the actual value. So the actual value was positive and the model also predicted a positive value. Then we have true negative, which is also represented as Tn. The true negative depicts the predicted value matches the actual value. Now the actual value was negative and the model predicted a negative value. Next we have false positive. Now false positive is also known as type 1 error. In false positive, the predicted value was falsely predicted. The actual value was negative, but the model predicted a positive value. Finally, we have false negative. Now false negative is also known as type 2 error. So in false negative, the predicted value was falsely predicted. The actual value was positive, but the model predicted a negative value. Now moving to our third question, which is explain the ROC curve. Now the ROC curve is one of the most important evaluation metrics for checking the performance of any classification model. ROC stands for Receiver Operating Characteristic. Receiver Operating Characteristic or ROC curve is a method to compare the diagnostic tests. The ROC curve is created by plotting the true positive rate against the false positive rate at various threshold settings. So here on the y-axis you have the true positive rate, on the x-axis we have the false positive rate. The true positive rate indicates the proportion of observations that were correctly predicted to be positive out of all positive observations. Similarly, the false positive rate is the proportion of observations that are incorrectly predicted to be positive out of all negative observations. You can take an example. Suppose in medical testing, the true positive rate is the rate in which people are correctly identified to test positive for the disease in question, let's say the coronavirus testing. ROC does not depend on any class distribution. This makes it useful for evaluating classifiers predicting rare events such as diseases or disasters. Now moving to the fourth question, we have what are the assumptions for linear regression? So linear regression analysis is used for modeling the relationship between a single dependent variable y and one or more feature or predictor variables. Some of the important assumptions for linear regression are, so first, they should have linearity. So linear regression needs the relationship between the independent and the dependent variables to be linear. It is also crucial to check for outliers since linear regression is sensitive to outlier effects. Next we have homoscedasticity. Homoscedasticity illustrates a situation in which the error term, that is, the noise or random disturbance in the relationship between the features and the target variable, is the same across all levels of the dependent variables. Third, we have independence. So observations should be independent of each other. Finally, we have no multi-collinearity. So there should be little or no multi-collinearity. Independent variables should not be too highly correlated. Now moving to our fifth question in our list of interview questions. The question is, what is regularization in machine learning? Explain the L2 regularization. So regularization is a machine learning technique that is used to reduce the errors by fitting the function appropriately on the training set in order to avoid overfitting of data. So overfitting happens when a model learns the detail and noise in the training data to the extent that it negatively impacts the performance of the model on new data. So here you can see we have a nice plot which shows how overfitting of data can be visualized. and here we have a good fit line over the same data points. So this is also known as the regression line. Now L2 regularization is also known as ridge regression. So ridge regression modifies the overfitted model by adding the squared magnitude of coefficient as a penalty term to the loss function. So on the right you can see a set of data points plotted, and we have our linear regression line, and here we are calculating the cost function for the ridge regression line. So our cost function is actually loss plus lambda into summation of W squared, where loss is actually the sum of squared errors or squared residuals. Lambda stands for penalty for the errors. W is called the slope of the curve or line. Okay, now consider a case where there are 2 points passing through the linear regression line. Now if you calculate the cost function, we get the value as 1.69. So here we have assumed that loss is 0 since the 2 points lie directly on the line. We have taken lambda to be 1 and W is 1.3. So if you use this function or this formula, you get the cost function as 1.69. Now moving ahead, let's consider another situation where we'll calculate the same cost function for the ridge regression line. There is some loss for both the points as they are not on the same line. So here you can see the sum of squared residuals is 0.05, which actually is the sum of 0.2 square. I'm assuming this as 0.2 and 0.1 for this one. So if you square both and add it, the value is 0.05. A lambda is again 1 and W we have assumed to be 0.6. Now if you find the cost function, the value is 0.41. Let's draw the linear regression line and the ridge regression line with all the points. We find that the ridge regression line has the best fit since its cost function is less.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Now coming to the 6th question. What are the different methods to split a tree in a decision tree algorithm? So there are 3 methods to split a decision tree. First we have variance. So reduction in variance is an algorithm that is used for continuous target variables. This algorithm uses the standard formula of variance to choose the best split. So here you can see the standard formula of variance, which is summation of x, that is all the individual points, minus x bar, which is the mean, squared divided by the total number of observations. Now the split with lower variance is selected as the criteria to split the population. Now the steps to calculate variance is, you need to calculate variance for each node, and then you need to calculate for each split as the weighted average of each node variance. Moving ahead, the second method we have is information gain. So information gain is used for splitting the nodes when the target variable is categorical. It works on the concept of entropy. Now the degree of disorganization in a system is known as entropy. So here you can see the formula for information gain, which is 1 minus entropy. Finally we have Gini impurity. So Gini impurity is the probability of incorrectly classifying a randomly chosen element in the dataset if it were randomly labeled according to the class distribution in the dataset. So below you can see the formula for Gini impurity. So we have 1 minus summation of pi whole square, where n represents the number of classes and p of I represents the probability of randomly picking an element of class I. Now moving to the 7th question. So the question is, how do we find the optimum cluster value in k-means clustering algorithm? Now there are 2 methods to find the optimum cluster value. So first we have the elbow method, which is one of the most well known for finding the optimum number of clusters. So in this method you need to calculate the within cluster sum of squared errors for different values of k and choose the k for which within cluster sum of squared errors first starts to diminish. So in the below plot of squared errors versus the number of clusters k, you can see at k is equal to 4, the squared error starts to diminish. So hence our optimum k value is 4. Next we have the silhouette method. So the silhouette method measures how similar a point is to its own cluster compared to other clusters. the average silhouette method computes the average silhouette of observations for different values of k. The optimum number of clusters k is the one that maximizes the average silhouette over a range of possible values for k. The silhouette score reaches its global maximum at the optimal k. So in our case, the average silhouette reaches maximum at k is equal to 2, which you can see here. So our optimum cluster value will be 2 here. Moving ahead, the 8th question in our list is, how does the pooling layer work in a convolutional neural network? So the pooling layer performs a downsampling operation in order to reduce the dimensionality of the feature map. So in the pooling operation, you slide a two-dimensional filter over each channel of feature map and summarize the features lying within the region covered by the filter. It is a common practice to periodically insert a pooling layer in between successive convolutional layers in a convolutional neural network architecture. So the pooling layer operates independently on every depth slice in the input and resizes it spatially using the max operation. So in the diagram shown here, you can see we have a rectified feature map. We are using a 2x2 filter and performing a max pooling operation. So consider this as the filter. If you perform the max operation over the values, let's say 0, 5, 3 and 1. So considering this one, our pooled feature map maximum value will be 5. Similarly, for this chunk of data, it is going to be 7. Next, if you slide the filter over this square frame, you get 8, and similarly here you get 6. So this is also known as a pooled feature map. Moving ahead, the 9th question in our list is, how does LSTM network work? So long short-term memory networks are a type of recurrent neural networks that are capable of learning order dependence in sequence prediction problems. So remembering information for long periods of time is practically their default behavior. Now LSTMs also have this chain-like structure which you can see here, but the repeating module has a different structure. So instead of having a single neural network layer, there are 4 interacting in a very special way. Now you can see these are called as gates. These gates contain sigmoid activations. A sigmoid activation is similar to the tanh activation. Instead of squishing values between -1 and +1, it squishes values between 0 and 1. An LSTM has 4 gates. Now these are called forget, remember, learn and use or output. So if you see this, in the first step, we use the forget gate that decides what information should be thrown away or kept. The information from the previous hidden state and the information from the current input is passed through the sigmoid function. Values come out between 0 and 1. So if the value is closer to 0, it means you need to forget that information, and if the value is closer to 1, it means you need to keep that information. Next, we have the input gate. So the input gate is used to update the cell state. First, we pass the previous hidden state and the current input into a sigmoid function. That decides which values will be updated by transforming the values to be between 0 and 1. 0 means not important and 1 means important. You also pass the hidden state and current input into the tanh function to flatten the values between -1 and +1. This helps to regulate the network. Then you multiply the tanh output with the sigmoid output. The sigmoid output will decide which information is important to keep from the tanh output. And finally, in step 3, we have the output gate. This output gate is used to decide what the next hidden state should be. First, we pass the previous hidden state and the current input into a sigmoid function. Then, we pass the newly modified cell state into the tanh function. We then multiply the tanh output with the sigmoid output to decide what information the hidden state should carry. The output is the hidden state. The new cell state and the new hidden state is then carried over to the next time step. Finally, talking about the last question in our list of interview questions, we have explain the concept of gradient descent in deep learning. Now, gradient descent is an optimization algorithm which is mainly used to find the minimum of a function. In machine learning, gradient descent is used to update the parameters in a model. Parameters can vary according to the algorithm, such as coefficients in linear regression and weights in neural networks. You can see we have these maps, and on the y-axis we have the loss, on the x-axis we have the weight, and here we are trying to find the local minimum or the global minimum. Now this gradient descent method is used to minimize the cost function and update the parameters of the learning model. The gradient always points in the direction of the steepest increase in the loss function. The gradient descent algorithm takes a step in the direction of the negative gradient in order to reduce the loss as quickly as possible. To determine the next point along the loss function curve, the gradient descent algorithm adds some fraction of the gradient's magnitude to the starting point. Now this process is repeated to find the global minimum. And that brings us to the end of this video on Data Science 2022 full course by Simplilearn. I hope you liked it. If you have any queries, then please feel free to put them in the comment section of the video. Thank you for watching.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.